be good enough to produce the displacement. You have to push it at least couple of lattice constant distance. So that need bit more energy. Because of that, typically the displacement energy or ED values taken for metals used to be like 25 electron volt. Approximately it's a 25 electron volt. So this changes from material to material. Suppose when you are doing a calculation like in SRIM calculation, if you typically the values are taken automatically, it's a 25 electron volt as a ED value. But if you want to give a like sometime if you want to do a very specific calculation, you can look at the literature where people might have done some of the DFT calculation and calculate the displacement energies ED values for suppose like zirconia that are O2 display. What is the ED value for zirconium? What is the ED value for oxygen? Specific crystal structure. You can take the input and you can give it as an input for a stream calculation, so that the whatever you produce, the vacancy profile or displacement profile will be more accurate. So this you have to remember. So the threshold energy for our ED or displacement energy for any metal, approximately it is 25 electron volt. Remember, this is a 25 electron volt. So room temperature, if you are looking at the energy, it's a 25 milli electron volt. So that means something like 10 power 3 times larger energy is required to produce the displacement, minimum one displacement from its lattice side. Okay, fine. So in this cartoon, this is a En, this is a neutron energy. When the neutron comes, it produces a primary knock-on atom, and like the primary knock-on atom will have energy of T, and then it will go with En minus T and produces further displacement, further primary knock-on atoms. Okay, it goes on like that. And this knock-on atom produces the kind of displacement cascade. In the displacement cascade, when it is produced, or displacement spike, we can say, and the spike will have a vacancy-rich core and interstitial-rich periphery, you will get it. So this is a typical for displacement spike in metals. And then this is one thing it occurs. Apart from that, this game will have a lot of vacancies and interstitial dislocation, precipitates, impurities, solute atoms, and so on. So all these players play a game in these materials. Like vacancies and interstitials can recombine so that the vacancy number of vacancies and interstitial can reduce one. And there is the other case like dislocations. It can preferably absorb interstitial and not in vacancies. Then on such cases, the vacancy concentration can increase. Then the grain boundary, it's an unsaturated sink where it can absorb. It doesn't have any bias, like it will prefer to take a vacancy or interstitial that doesn't have any bias. So because of that, it can take more number of vacancies and interstitials. It can decorate these grain boundaries. And suppose if you have a material which has some of the gas atoms are produced either by in a neutron where the fission gases are released, like argon and krypton, xenon, the fission gases are released, or when you bombard with ions of like gaseous ions like argon, krypton, inert gas ions. So these inert gas ions, when you bombard it, this inert atom does not chemically interact with this matrix, so that can form a kind of inert gas bubbles. And these bubbles also preferably look for some nucleation site. If you have a bigger precipitates, then the precipitate surface, it start to nucleate and decorate the precipitate with the inert gas bubbles. If there is no precipitate, then it start to decorate the grain boundaries. So it also look for some nucleation site. For whenever something want to form like voids or bubbles, always something which is necessary for the nucleation, we need a nucleation site. And apart from that, during the cascade recovery, it can recombine and it can produce a completely different defect cluster microstructure. And then there are other things like you can see some of the vacancy loop can form or interstitial loops can form. And suppose you have a precipitate where it can absorb the, suppose you have an incoherent precipitate in the sense, you have a matrix, you have a particle, the particle to the matrix lattice constant is very close. then you will form a coherent precipitate. Suppose you have a lattice mismatch is so large, then you will have an incoherent precipitate. When you have an incoherent precipitate, there number of space will be between the matrix to particle will be there that can accommodate the vacancies. So that way one can remove the vacancies in the system. And there will be other cases like either voids can either add more and more vacancies, then the voids can grow, or it can emit the vacancies and it can reduce the void size. And so many things can occur. Apart from that, you will have a matrix like stainless steel. If you take stainless steel, will have so many number of atoms. Some of the solute atoms can trap the vacancies, and some of the solute atoms can come back and join with a cluster and form a cluster with different composition. So all these things can occur in the material. So this is a different. So when you bombard in a material, if you have a generally people do with a very simple system like zinc oxide or bismuth telluride or gold silver alloys. So these are the systems we don't have multiple elements and we don't have much complexity. But when you are going for instead of binary, if you are going for ternary system or a multi-element compounds, then this kind of all things can play a role when you are bombarding with a beam. Otherwise, it is not simple binary element or three element composition. If you have, it may not have much complexity in your research. Okay, so this is a thing. And when you have a radiation damage in effects are concerned, there will be different things can occur when you are doing an irradiation. This can harden the materials. That hardening mainly because of it forms a dislocation loops. And the irradiation creep, it's another phenomena when you are irradiating as well as the loading the specimen. There will be different irradiation creep can change the dimensional changes, but the irradiation creep, the dimensional changes occur. However, the volume is conserved. Whereas in the case of swelling, the volume of the material is or void swelling is concerned, it's also dimensional changes, but the volume is not conserved. The other thing, at a very low temperature, the helium, the high temperature helium embrittlement will be dominant. It can make the materials too brittle. That is where the helium goes and occupy the grain boundaries and the material become brittle. Whereas in the lower temperature, if you are irradiating, then hydrogen embrittlement can occur. Where the hydrogen it forms very, very small bubbles in the brown grain boundaries and the material become brittle. So here in this slide, we can see that there are two. One thing, it's very important. We are going to discuss about one of the radiation damage phenomena, void swelling, not about the irradiation creep. These both are dimensional changes, but in irradiation creep, the volume does not change, whereas in the void swelling, the volume of the material also changes. Okay. Now, why one has to do the void swelling using ion simulation? So this I will come to later about what is DPA. So this we will coming up in the next subsequent slides. So when you take this first two, one EBR2 and HENS, these are all both are neutron sources. If you are looking at the y-axis, the damage rate, if you are looking at that, these are neutron beam, the damage rate is approximately something like 10 power minus 6 dPa per second. So this is the time dPa. Suppose if you are going for proton, you will have something like 10 power minus 5 dPa per second. If you are using electron beam, you will have something like 10 power minus 3 dPa per second. So then when we use the nickel, like 5 mm nickel beam, you will have something dPa rate of 10 power minus 1 dPa per second. So when we do, when we look at this effects, as I said that in the beginning, the neutron used to be highly non-interacting. So this will occasionally produce some of the primary knock-on atoms. So that will produce the damage. Whereas the proton beam, the probing depth will be much larger, but it will, again, the damage production is concerned slightly higher, better than neutron, but it can produce the damage for larger depth. In electron beam, generally the electron will not produce the cascades. Whatever the primary knock-on atoms produced in the neutron case, it will produce large number of cascades. Electron beam generally doesn't produce the cascade. Electron radiation mostly it produces the Frankel pairs. So Frankel pairs, and then as Frankel pairs, number of Frankel pairs keep on increases, then you will start to see a dislocation loops. So loops will be forming. Whereas when you go for high energy heavy radiation nickel with a 5 MeV, which will produce more or less similar kind of damage which is produced in the reactor materials like a primary knock-on atom. So generally this ion simulation is done with a 5 MeV nickel beam. And the limitation, what is the problems? Suppose if I do some neutron irradiation, the material get activated. Handling the material become very, very difficult. And also the reactor is concerned, one day it operates at full power, the next day it may operate at 50% of the power. And temperature and flux, this we will not have any control during operations. Because of that, we will not be able to qualify the material for the reactor applications. So on such cases, whereas when we do ion irradiation, the materials will not get activated, and we can do experiments very controlled manner, like controlled temperature, controlled dose rate, and controlled dose. We can do this experiment. So that way the ion simulation quickly qualify the material for reactor applications. Fine. Now we'll go back to the basics. So in the previous slides, I have discussed about DPA. What is DPA? Okay, DPA, I said that in displacements per atom per second. Okay, DP. So some of you might have come across some of the research papers. The ion, generally they give during ion irradiation, you give a unit of ion fluence in ions per centimeter square. Some cases people give it ion dose in terms of DPA. So what is DPA? Here, displacements per atom. How did they get this number? This end of this talk, you should get that information. How did you do? How do people get these numbers? Okay, so this is a DPA is generally it's just a measure of damage produced in your material. Okay, generally when you have this system where the incident particle with a flux of phi with the energy of EI, the I can be neutron or gamma or ion or electron and so on. So what are the things can occur in your material when it is put you a beam of particles? Either elastic scattering can occur, absorption can occur, inelastic scattering can occur. And suppose if you have a neutron case, then you will have a kind of transmutation of atoms also, it can happen. So when all these things happen, and also we have to look at that the recoils or primary knock-on atoms produced. If your particle has a different incident energy, you will have a primary knock-on atom with different energy distribution also will be there. Number of pK with different energies also you will get it. Okay, so for example, the other thing is like cross section. You all might have come across the term cross section. The cross section is nothing but the probability for that particular event to occur. For example, if you are taking a material like A and B in a given system, where A is U-235 and B is a B10 or boron 10 isotope, if I put a thermal neutron, when you look at that boron 10, the cross section for the neutron absorption will be more, because the neutron absorption cross section for boron is much larger. So when it sees the thermal neutron, it will try to absorb it. So the absorption cross section for neutron with a boron 10 element is much larger. If it see the U-235, it will not do the absorption, but it will do the fission. The fission cross section for U-235 with thermal neutron is much larger. So when we look at the thermal neutron with A and B, when you look at the B, the fission cross section to the A, B with absorption cross section with respect to fission cross section. If you have a more number of boron, then you will have absorption will be more, the fission will be less. Okay, so that is the reason the boron is used as a used as a material for control rod or neutron poison as a boric acid. They use it. So this is the cross section. Okay, the cross section concept will give you the some of the usefulness, because if you just multiply by the flux, you will get the reaction rate. So that is very important. So that way this cross section concept is very useful in this case. Now, when we look at the neutron energies in the reactor, if you are looking at that, the energy will be like you will have a ultra cold neutron to fast neutron with the energy of something like 10 power minus 5 eV to something like 10 power 14 MeV and so on, million electron volt you will have. So you can see that suppose the neutron interact with the nickel 58 and nickel 59. So if you are looking at that, there will be plenty of things can occur. One is this blue color one is the N gamma reaction. When it occurs, it can give you such kind of cross section. When you have a N alpha reaction, the cross section will be like this. So you might have seen there are some of the spikes in this. So these are the called some of the resonance reaction occur in such energy range. So this again you all might have come across in this school itself in the ion beam analysis. One of the experiment is like resonant nuclear reaction analysis. So where such kind of resonance reaction occurs with certain energies below which above which does not occur. So these are some of the resonance reaction occurs in a material. So when you have a solid containing something like n number of target atoms per unit volume, so when a single particle energy EI pass through, then you have a probability the particle interacts with a small thickness like delta x, then the differential probability can be written as n sigma this flux with a cross section for particular event with a thickness dx, or sigma dx we can write. For example, when you have a neutron with the energy En, then it transfer the energy of to the primary knock-on atom E. Then this primary knock-on atom produces the secondary recoils with the energy of T. Okay, so this will keep on produce that. But now the problem calculating displacement damage, we can classify, we can take into two things. One is the finding energy spectrum of pKa created with the neutrons with the solid. Second thing is how much damage a pKa given energy can produce. Okay, so the primary knock-on atom, this is second one only we are going to discuss. The primary knock-on atom can loses its energy via, you all might have come across, like nuclear energy loss and electronic energy loss, the ionization loss. The ionization loss used to be very negligible, so we consider the nuclear energy loss and electronic energy loss. And this is a picture when you can see that the neutron comes and transfer part of its energy to a primary knock-on. The primary knock-on atom produces the displacement spike, and the remaining energy, the neutron goes and produces another primary knock-on atom, and so on. So you can see the path of the primary knock-on atom that will produce the displacement spike. Along the displacement spike, you can see that you will find a vacancy-rich core and interstitial rich periphery. Okay, this is one thing I discussed in the beginning in the cartoon, particularly in the cartoon. So now, okay, primary knock-on atom, how much energy maximum it can transfer to the target atoms? When you are looking at that, generally this will be like 4 m1 m2 by m1 plus m2 whole square. This is the maximum energy we can transfer. T will be lambda times E, where lambda, if you are assuming the collisions are head-on collisions, then you will have something like a maximum energy will be like 4 m1 m2 by m1 plus m2 whole square times of the primary knock-on transfer to the target atom. Fine. If you are looking at the example, suppose if you take a steel, any steel, if you are taking without carbon, the iron will not be considered as a steel. So small amount of carbon will be there always in the material. It will be one of the very important addition. Sometime you will might have seen that low carbon steel, high carbon steel, but the carbon is very, very important. It will improve the strength of the material. So when you have a neutron interacts with carbon, so if you just put the carbon mass of 12 AMU and neutron mass, then you calculate the lambda value, then you will find the number is lambda is 0.28. So it will produce something like 280 keV primary knock-on atom of carbon. Whereas in the case of iron, it will produce 70 kV. Then this further, when it is 280 kV carbon, when it interact with another carbon atom, it transfers 100%. Whereas when with iron, if it interacts, then it will produce 162 kV iron atoms. So this is how this primary knock-on atoms with different primary knock-on atom energies will be produced in a system. So when you have such kind of energy, fine, this is happening. Then what about the electronic energy loss? Whether this will lose some energy by electronic energy loss or not. So generally, when you take a material, the electron density will be much larger than the atomic density. So if it transfer the energy to electronic subsystems or need a receive an energy, typically the average kinetic energy of the electrons in metals will be 3/5 of Fermi energy. This is already known. And the ionization energy will be the balance, 2/5 of EF. So when you have maximum electronic energy loss, the energy transfer to the electronic subsystem is equivalent to like ionization energy. If you are taking, then this will be like you can just you take a electron mass as well as the ion mass, then you will have a kind of formula where lambda me will be simply, if you simplify, because the mass of the electron is much smaller than the mass of your ion. So if you set this formula, you will get like 4 me by capital M times of E. And if you are just take like I, ionization energy is something like 5 electron volt, and if you are setting these values, you will find out there will be something cutoff energy E star, above which the electronic energy loss will be dominant. If you are just look at that, E star will be like 1,000 times of mass number of your ion and the energy. So that is mass number of times keV, above which the electronic energy loss will be start to take up. So for example, if you are taking iron, the mass number is 56, then above 56 keV of iron beam, the electronic energy loss will start to pick up. Below which mostly not, it's 100%, the energy loss process will be via nuclear energy loss. Okay, further to elaborate this this thing, you all might have seen something like called a kitchen piece model in your stream calculation. You click it and you just calculate the damage profile and other things. You use either kitchen piece model or kitchen piece formula, or you will use a full cascade. So when you take a kitchen piece, it's just a binary collision approximation. Okay, so I have told you in the beginning, the ED or the energy displacement energy for a system, ED is energy 25 electron volt, I said. So suppose you have a primary knock-on atom energy. Suppose this x-axis is a primary knock-on atom energy. Then y-axis is the number of displacements produced by the primary knock-on atom energy. Suppose you have a primary knock-on atom energy, like say in the beginning I said that something like 70 keV. Then how many displacements will be produced? So for that you have to get the number, no? So how many displacements will be produced? So minimum will be like ED. Suppose when you are checking the primary knock-on atom energy, 0 to ED, like up to 25 electron volt, the no displacement, zero displacement. Then ED to twice of ED, like 25 electron volt to 50 electron volt, the number of displacements will be only 1. It cannot be more than that. Okay, about twice of ED or 50 electron volt, greater than 50 electron volt, how many displacements will be produced if you are taking? It's like a E by twice of ED. Okay, like if you are taking like a 5 kV, then the primary knock-on atom energy is say 5 kV. Then twice of ED is 50 eV. Then how many displacements will be produced? Approximately 10 displacements will be produced. Suppose if it is a 10 kV, then you will produce 20 displacements will be produced. So this many number of atoms will be displaced from its original site. Okay, fine. Keep on increasing the primary knock-on atom energy, above which energy these displacements will not occur via binary collision approximation. So this will be the E star or cutoff energy. The previous slide we discussed the E star cutoff energy, above which the electronic energy loss will start to dominate. Okay, so fine. So the primary knock-on atom with a different spectrum of energy will produce different kind of damage, and this was simplified by the number of displacements produced by primary knock-on atom with energy was calculated by Nargat-Robinson-Torrance formula, where we will be having a 0.8 times of E by twice of ED, where the E is the damage energy. And this is a very simple formula you have to remember. And then also one has to look at this another graph, the damage efficiency. Okay, pKa energy is produced. Suppose you have a target and you produce with a pKa of beryllium. So the beryllium maximum, this will be the dotted line, will give you the maximum damage efficiency of the system up to that energy. Below which you will have a damage efficiency more. After that it will fall exponentially. If you are looking at the light ion, the damage efficiency falls much smaller energy itself, whereas when you go for uranium, which will have a damage efficiency up to much larger energy, as well as you can see that the damage efficiency maximum will be around 0.7 even at this dotted line. So if you want to produce a more and more damage in your material, then you have to choose a higher mass so that you can produce it in much shorter time scale. This is one thing we have to remember. Generally, the damage caused by neutron irradiation we can calculate by the damage rate, or dPa per second, will be proportional to the lambda times of 5 times of ED, where phi of En is the neutron flux with a different neutron energy, and cross section for the neutron to produce the primary knock-on atom with different energy is En. Then En is the spectrum of energy of neutron, and Den. You integrate over these things, you will get a finite value of a dPa rate. But for simplicity, we can take like a average energy of neutron instead of multiple energy. Assume that reactor produces only monoenergetic neutron, then you will end up with a formula where the dPa rate will be proportional to the phi t. Phi t is nothing but the flux of your neutron beam. Sigma s is your cross section, and Ed is the displacement energy, and lambda is the energy transfer with the neutron with the target atom, and you can get the En is the average neutron energy. So by getting these numbers, you will be able to get the dPa rate for a neutron beam. So this is a one example problem. You can see that the lambda NFE, the neutron, how much the K factor, it's a damage factor it produces. If you are looking at that, it will be like a 0.0689. So this is lambda. And if you look at the problem, you have get the flux of 5 into 10 power 13 neutrons per centimeter square per second. And energy of the neutron is 1 MeV neutron. And then if cross section is like a 3 burns, 3 into 10 power 24 centimeter square, then Ed is 25 electron volt. If you are substituting all these numbers, you will get that something like 8.3 into 10 power minus 8 dPa per second. So remember here the flux is 10 power 13. If it is even 10 power 15, you will have something like 10 power minus 6 dPa per second. So now you can remember in the beginning some slide I have shown that the neutron damage rate dPa per second, typically it will be 10 power minus 6 dPa per second. If we increase the flux, it will be 10 power minus 6 dPa per second. So here, this is the dPa per second. Suppose typical reactor cycle like 1.5 years is the typical reactor cycle. During this cycle, how much dPa will be occurred by the material? If you are looking at that, you convert into seconds, then you multiply this with the seconds, then you will get the dPm. This is 3.93 dPa is produced in a one reactor cycle. What it means, it's approximately 4 dPa. That means what is dPa, displacements per atom, what it measures? It is on the average, each and every atoms in the material is at least 4 times displaced from its original site. Okay, so suppose if you are taking like any material, you will be knowing that number of atoms will be approximately Avogadro's number. If you are taking in a 1 cubic centimeter, then each and every atom, all the 10 power 23 atoms will be displaced at least 4 times from its lattice sites, and it can come back, but 4 times it is at least displaced from its original site. So that is what the meaning of a DPA. Okay, so the damage is produced like that. Okay, so this is a case with the neutron beam. So how will you get the ion beam, particularly the damage or DPA produced by the ion beam? So when you are looking at this is a one graph. You can see that what is the importance of your DPA produced by different beam. As I said, that the neutron used to be highly non-interacting particle. You can see it in this graph. The damage production will be much smaller, but this can go for something like more than 12 micron. Also, it does not alter its any energy. It just goes on like that. Okay, 1 MeV neutron is down and 14 MeV neutron is up, so it keep on goes. Okay, whereas when we use like 1.3 MeV proton beam, it can stop at something like approximately 10 micron depth, but the damage production is slightly larger than the neutron. Remember, the y-axis is in the logarithmic scale. Suppose when we go for a like 20 MeV 20 MeV carbon beam, again you have slightly larger, but it's a 6 micron. It stops. When you go for a 5 MeV with nickel, it will stop at 1 micron. But the damage rate, if you are just looking at the fast neutron in the surface, it's something like a 10 power minus 21 case. In this case, it's 10 power minus 15, something like 10 power 6 times. That means the damage produced by neutron will be produced in much shorter time scale. 10 power 6 times shorter time scale, we can produce such a damage. So that is the one reason people go for ion simulation. We do that. And generally the DPA, in terms of, usually you get the ions per centimeter square, you will measure from your dose during an ion radiation experiment. If you are having these numbers, then if you know the values of like displacement energy, ED value, if you approximate, it's like 25 electron volt. EA is the incident ion energy, and Zi is the incident ion jet value or atomic number value. Jet is the target jet value, and Mi is the incident ion mass, and M is the target mass. And lambda, you know that M divided by Mi plus M whole square. You can just substitute all these numbers. You will be able to get the DPA value. Simple. So this is analytically one can calculate the DPA value if you are not using a SRIM calculation. Suppose if you are using a SRIM calculation, what you can get is you can get the vacancy profile from the SRIM. So that will give you the number of vacancies per ion angstrom you will get in. You multiply with the ions per centimeter square your dose you are measuring, then you divide with your atomic density. Remember, while doing this, all these units should be in centimeter square. Then you will get the number. This is the number of damage or displacements per atom you can calculate. Okay. And when you look at the voids generally it will grow. There are three conditions are necessary for the void nucleation and growth in a material. That is like supersaturation of vacancies is necessary to form a voids. Then we need a sufficient helium. It should be there. It acts as a nucleation site. Then you have to have some temperature, high temperatures, so that the vacancies will be mobile and reach the void, and the void size will grow. So these things give rise to the void's growth. Okay, so the formation and growth of voids, the point defect should be mobile. So for that we need a very high temperature, and also we need a supersaturation of vacancies. Fine. At very high temperatures, the what happens? The voids start to emit vacancies. Then we will not get the supersaturation of vacancies. Then the void size shrinks. Then the void swelling also will be less at very high temperatures. Okay. So how this void swelling occurs as a function of temperature? We will. Okay. First, I will show that. Then I will come to that. This. Okay. No issue. No issue. I will just go through that. There is some confusion. Okay, fine. Okay, what will be the embryo or nucleation of your void size when it nucleates? There are two terms. This formula for the gives free energy for the void nucleation and growth. if you are looking at that, there are two terms. One is this entropy term, which will linearly vary with a number of vacancies present in your void. Okay, this n is the number of vacancies present in your void, and delta is the volume of your atomic volume, and then gamma is the surface free energy of your system. And if you are taking such a formula, if you are looking at that, the first term, the entropy term, it will be just increases with a number. When it increases, it will be like negative. With n increases, it linearly increases in the negative direction. Whereas when you are looking at the second term, the n power 2 by 3, where this will grow like that. So there will be some, okay, sorry, there will be some region. So this, the first term will go like this, whereas the second term will go like this. So when we have such kind of things, so there will be some critical component, critical n star, it will be the necessary number of vacancies are necessary for forming a void. So if you are going slightly away from more and more vacancies added, the total energy of the system start to reduce. So in general, thermodynamically, the system always try to go for a lowest energy state. So this is the critical void size, above which if you are adding more and more vacancies, then the voids will grow, but the free energy of your system reduces. So this is the critical void size. This many number of vacancies are necessary for forming a void size. This will be the embryo of your void. Okay, fine. Fine, this is the thing how we will do the experiments in your lab. So this is our accelerator lab where we have used this one of the beamline. There are two beamlines generally we use it. One is for the center one, that is mostly we use for austenitic steel. The other beamline, ultra high vacuum beamline, mostly we use for the ferritic steel. And generally when we do such kind of experiment, what we do is part of the sample we use to mask it with a mask, and then we bombard the sample. First what we do is we have to do a helium inclusion. So for that we do a different kind of energy of helium with different energies, and produce a rectangular profile of your helium. The helium profile is this, so it will produce the rectangular profile of helium. So this red color one, whatever I am drawing, this is a helium profile. So after producing the helium profile by varying different energies of helium with different ion fluence, we get the rectangular profile. Then we use the 5 MeV nickel ion irradiation to maximize the damage at the center of the profile. This is the irradiation. So first irradiation, we do it with the room temperature where helium incorporated. During nickel ion irradiation, we keep it at different temperatures like 300 degrees Celsius to 700 degrees Celsius. We do that. And part of the sample is masked, okay, with a razor blade. Then after irradiation, you remove the razor. Then you will find that there will be step height increase. So from that, one can measure the void swelling. So by void swelling can be measured by surface profilometry or transmission electron microscopy or positron annihilation spectroscopy. Okay. So the typical energies, and this is we do for a different like a key alpha particle with 200 kV to 700 kV. You do it and get the rectangular profile. Then you irradiate it. You will see that the void swelling can be measured by these formulas, where delta V before and after you can get this number. So if you are looking at the void swelling increases with the temperatures, you can see that this is 500 degrees Celsius, 550, 650, 600, 650. 650 you don't see much void. So the void swelling will be peaked at particular temperatures, and above which the swelling again reduces. Okay, this is the experimental observation. And this case is concerned, we could see some of the TIC precipitates also. These are titanium carbide precipitates. So these fringes are called Moire fringes. This we will discuss it in the next subsequent lecture. We will discuss part 2. We will discuss. And so okay, fine, the void swelling occurs in a material. How to improve the void swelling in your material? Suppose how long? So arsenic steel, suppose if I take a 316 SS, so you will have something like this is the curve. So this is the period void nucleation occurs. Okay, this is the damage dose level. The nucleation occurs. After this nucleation, it start to grow. So you all might have come across this nucleation and growth of any curve, any new phase. If it forms, like if you are doing like that, the nucleation growth will be typical S curve you will see. See, this can be like a time of annealing, and this is the secondary phase. It forms volume fraction of the secondary phase. When it forms, it goes like this. So always you have a nucleation and growth curve like this, but in this case this part of the curve is shown here. So here the voids will be, nucleation period will be something like here. This is the nucleation period, and above is the start to growth occurs. So once the growth occurs, the void swelling will be increasing rapidly. Okay, remember, so if you, how do we push this incubation dose for longer and longer time? So one is the, we can make the different composition of your material. So one of the thing is titanium modified 316SS. That is a D9 alloy. That's what yesterday, the previous slides we have shown. So that will produce the incubation dose up to 80 dPa. And if you are going for ferritic steel, like iron based, this is austenitic steel, which is a nickel, and which is a crystal structure is FCC. If you are going for a ferritic steel where the structure is BCC, then the void swelling will be less. But the ferritic steel has some of its difficulty, that it cannot have a large strength. Mechanical properties are poor. So to improve the mechanical properties, people have introduced the oxide dispersides. The dispersides act as a pinning site for the dislocation. So it will arrest the mobility of the dislocation, give rise to the mechanical strength for the material. So through which one can study the mechanical, through which we can study the swelling properties of your material, improve the material property for the swelling. So this is another example where SS316, you can see plenty of voids where we can find out the void swelling. The delta V by V in percentage we can measure by, where R is the average radius of your void size and N is the number density of your voids. So from that one can calculate the void swelling. Fine, this is a one curve. Here we will, after this we'll give a break, and then we'll, after 5-10 minutes, we'll start again. So here you can see that the temperature of irradiation, if you are looking at that, so generally this void swelling will be maximum between something like 0.3 to 0.5 times of melting point. So either side the void swelling will be less, because at lower temperature when you are doing irradiation or operating the reactor, the mobility of the vacancies will be poor. Hence, you will never form a void. The vacancies will not be mobile, so the voids will not form. So the low mobility causes the low swelling at lower temperature regime. Whereas when we go for a very high temperature regime, thermal emission of vacancies from the voids will start to reduce the void size. So because of that, swelling will be low. And second thing is, I have told you about something like neutron, the damage rate is 10 power minus 6 dPa per second, whereas the ion beam it is like 10 power minus 1 dPa per second. So when we do faster dose rate, will it affect the peak swelling temperature? Yes, the peak swelling temperature will be higher in the case of ion beam. So in our case, our experiments on D9 alloy or 316SS, if you, when we do ion beam irradiation with something like 10 power minus 2 dPa per second, we compare the results with our fast reactor or ABTR results. So the peak swelling temperatures used to be something like 150 degrees Celsius offset. So if you observe a peak swelling temperature with the ion simulation at 650 degrees Celsius, then your peak swelling temperature at the reactor will be around 500 degrees Celsius. So unfortunately, the reactor operates at those temperatures. So because of that, we have to improve the material properties. Okay. So here we stop the lecture and we'll give a break. After 10 minutes, we'll continue in the second part.
There are some questions you want to take now, or
Yes, now itself I can take it,
yeah,
and then we'll go for a break. Because the second
chat
portion will
box.
be
You can see that there are two questions from Mayur Khan. You can just see that
1 minute, 1
how
minute.
we can calculate the primary knob of on-atom energy.
How much radiation damage produced? Okay.
There's one question about that also.
Yeah, yeah. The primary, how we can calculate the primary knock-on atom energy? That is, in the slides we have given, like if you are taking like 4 m1 m2 by m1 plus m2 whole square times of your energy, incident energy, you can just multiply, then you can get this. Okay, this is one way, and that's what we have given it that in that slide also. I can share you again. I can share you on the slide. One
Yeah.
minute. I can share you on the slide. 1 minute. Just, 1 minute. I'll just share the slide and that because it is. So this one you can see that suppose when the neutron, okay, this is the energy of the neutron, say 1 MeV neutron, when this target has a iron and carbon, okay, this 0.28 value we obtained by this formula. When you have a M1 as a neutron mass, M2 is the carbon mass, and calculate this term and multiply with the neutron incident energy, you will get like that. So the factor, the lambda for the neutron with carbon, if you're looking at that, it's a 0.28. So En is the neutron energy of 1 MeV. 0.28 into 1 MeV will give you 280 keV. So this is a primary knock-on atom of carbon with 280 keV. The same 1 MeV energy of neutron falls in interact with the iron atom, then the lambda value will be 0.07 times of En. So that will produce 70 keV primary knock-on atom of iron. However, this is a primary knock-on atom of carbon and iron if the energy is transferred from neutron to carbon and neutron to iron. Further, this carbon, 280 keV carbon, can transfer the energy to a iron. Here, the M1 is carbon, M2 is iron. You take it, and then you will get something like 162 keV of iron atom. So, the energy distribution, the pK energy will have a distribution of energy because it can have a 280 keV carbon, it can have a 70 keV iron, 162 keV iron, it can have a 40 keV carbon, like distribution of energy. Okay, so that is the reason. This is how we calculate the primary knock-on atom energy. And the second question is on the DPA. For DPA means each and every atom in the system is at least 4 times displaced from its lattice site. Okay. Then the other question is TM specimen for stainless steel samples. Yes. This shall I discuss it in the next lecture? Okay. Yes.
That's okay. Yeah.
This
Yeah.
question, TM question, I will answer it in the next class. Okay.
Okay.
So
Okay.
now we'll take a 5 minutes break. Then we will
Yes. Yes. Yeah.
will start again.
Around
Okay.
10:40 we'll meet.
Yes,
10:40.
sir. Yes, sir. Yes, sir.
Okay.
Thank you.
Okay.
Thank you. Bye. Yes. Uh, shall we start again?
Yeah, you can start. There's one question you can see whether it should be
Yes, yes,
answered now.
yes, yes, I will say
At
that.
what distance range
Yeah,
the
yeah, yes.
displacement of atoms
At
are?
what distance the range of displacement of atoms occur? Okay. Uh, this displacement of atom occur through the ion beam path, through cascades, as well as at the end of the range also it produces more damage. So at the end of the range, the more displacement will be produced compared to along the path. Okay, whatever along the path, when you are doing with high energy ionization radiation, along the path, whatever displacement caused by the electronic energy loss will be much smaller. At the end of the range, whatever damage produced by the nuclear energy loss will be much larger. So that's the one thing. And the second thing, the probably the person who has asked the question may have a doubt. Why don't we see it in a experimentally when we see such kind of displacement? You are saying so much damage is produced. We don't see it experimentally in whatever morphology in the sample or microstructure in the sample. The reason is whatever the damage produced, whatever we do calculations of stream and other things, we do calculate the vacancies and the vacancy concentration in the tissues and so on. But what we see, observe it in the TEM or other experiments is the effect. It's not the during the time. The time scale, if you are looking at that, the time scales will be very, very small. The maximum energy, the energy transfer process itself, it will be fast in the beginning. Primary knockout atoms are produced in the time scale of 10 power minus 18 seconds. So on such cases, it's really we are, what we are observing is in the after irradiation, probably a few days and so on, much larger time, we see only the effects, not the during the time. So if we have a experimental tool where we should be able to see the observation in the time scale of less than a picosecond or femtosecond time scale, and also if we are able to see the we should have a recording capability of a microscope with a time scale of 10 power minus 15 seconds time scale. We have to acquire the image, as well as we should have a spatial resolution of something like angstroms or 1 angstrom. Then we may be able to see the displacement cascade itself in the microscope. So this is a very challenging one. So in near future we may not see it. Probably it may have, we may have to wait for longer time to get such kind of facility or experimental observation in your materials. Okay, so now we are going for the second part of the talk. Shall we start?
Yeah, yes, I think yes. Proceed.
Okay. The second part I am going to discuss about the electron microscopy. So these are so exactly around 11:30 I will try to finish it, because subsequently the other speaker will have to speak. So these are very simple concepts: the magnification and resolution of your microscope. So how many times you are able to magnify the given image to the in the microscope, that is the magnification. The other one is the resolution of the microscope. So the resolution of the microscope, generally people have sometimes the misconception, like if I say the microscope resolution is 1.5 nanometer, they assume that we will be able to see 1.5 nanometer particle in the microscope. It is not true. So the thing is, when the two objects are at least separated by 1.5 nanometer or more, it will be seen as a two image, two species. Otherwise, it will be seen it as a single species. So that is the only difference. So the resolution, if I say SEM microscope, the resolution is 1.5 nanometer. It is not that we will be able to see 1.5 nanometer particles. Okay, please keep in mind. And optical microscope has a limitation because of your Raleigh's limit. The Raleigh's limit says that the resolution will be lambda by twice of AN, where the numerical aperture is defined as AN. The AN numerical aperture of your conventional lens will be like n sine theta, where n is the refractive index of your material, theta will be the collection angle. If you are looking at that, best resolution in optical microscopy will be like 0.2 micron. So the shortest visible wavelength, if you are taking 0.47 micron, it will be 0.2 micron, we can get it. But beyond that, we have to do with a better optics. Okay, better optics. So when we do use a shorter illumination wavelength, So when we go for shorter wavelength of illumination, so you have to go for an electron microscope. When you have an electron microscope, the electron wavelength can be tuned by just changing the energy of your incident electron. So this is where the de Broglie wavelength comes, and also the relativistic effects also one has to include it. Suppose if I take a microscope with a 200 keV, 300 keV, and 1000 3 MeV microscope, and if you are looking at the velocity of your electron beam, if you are going for 3 MeV microscope, it will be close to the light velocity like 0.989 times. So generally, the most of the microscope in a commercial microscope used to operate at 200 kV and 300 kV, particularly for material science applications. And when you want to do for a biological science application, electron microscope used to operate at 80 kV and less than 80 kV, mostly 120 kV, 80 kV range. And this is one thing I want to tell you. And the lambda value, if you are looking at that, this will be like a 2.5 picometer. Okay, 200 kV electron beam, if I take it, it's a 2.5 picometer. So if you may ask me the question whether this wavelength is 0.47, then it's a twice less than half of that. You will be able to get the resolution in the optical microscope. Whether it will be possible for this? If it's a 2.5 picometer, whether we will be able to at least see something like 5 picometer, we will be able to get the resolution. But it is not true. We will not get it because the limitation of your microscope for electron microscope, the resolution is 0.91 times of CS and lambda cube whole power 1/4, or CS power 1/4 and lambda power 3/4, where lambda is wavelength of your electron. CS is the spherical aberration coefficient. Actually, this is an approximation is there, because this is not only depend on your spherical aberration coefficient of your electron beam or beam optics, also it depends on the other things like chromatic aberration, and the combination of chromatic aberration and spherical aberration also involved. So it has something like 14 terms, but one of the major terms which affect the microscope performance is spherical aberration coefficient. So this is conventionally the aberrations in electromagnetic lenses are like a spherical aberration coefficient, and then chromatic aberration and astigmatism. So generally the astigmatism is corrected by the corrector lenses. One can do it. The chromatic aberrations, like for a spherical aberration, what it means spherical aberration, when you have a lens, the beam pass through paraxial rays and off paraxial rays, it focuses at different places. So that gives the minimum disk of confusion. So that is one problem with the aberration, spherical aberration coefficient. The other one is the chromatic aberration. If you have a wavelength, your electron beam, they have a two different lambda, energy spread in the electron beam, which will also focus on two different places, which will also produce some kind of confusion, some kind of resolution limit. So the other astigmatism will be like in plane and out of plane focus at different places, also causes the aberrations in your microscopy images. So when we want to go for better microscope, these things has to be corrected. Conventional microscope, this astigmatism used to be corrected by corrector lenses, and the chromatic aberrations we can reduce it by keeping a energy spread low, by either we can go for a cold field emission, or we can have a monochromator. And whereas when we go for a spherical aberration, we have to correct the spherical aberration corrector lenses has to be added, then we can get aberration corrected microscope. The microscope history itself, it has such a long history. In 1931, Max Knoll and Ernst Ruska built a first TM. This is a first TM they have built, and they got a Nobel Prize in 1986. Ernst Ruska got it in it's not for TM, but he got it for scanning tunneling microscope, not for TM. So remember, so this discovery of electron goes back in 1897, and de Broglie come up with the de Broglie wavelength in 1924. Then the progresses, and Max Knoll and Ernst Ruska built the first TM in 1931. So you might have seen this. The first TM was very, very small, and but when the modern microscopes, when you are looking at the electron microscope, you have a similar kind of microscopes are there. I think in USC has the microscope of I think Technic G2 or G3, I think F30. I think they have F30. So it is a microscope. So this will be typical microscope will be like this. And this microscope, high voltage TM, it's a 1.2 million volt high voltage electron microscopes. And this is a scanning transmission electron microscope where the electron source will be at the bottom and the detector will be at the top. And this is a Carl-Zeiss, the first aberration corrected microscope, where they want to isolate the ground vibrations. They have made a special cradle, and they hang the microscope on the cradle so that they can get a best resolution of the microscopes. And these are the geol microscopes. And high voltage TM like 1.2 MeV or 3 MeV TM are very, very rare. In India, we don't have any. And this very high energy microscopes, when you go for like 1.2 MeV TM or 3 MeV TM, in the context of radiation damage in materials, one can not only use for the observing slightly thicker samples, and also one can study the electron irradiation effects also. Like when we do with the 3 MeV electron beam irradiation, it produces the damage also. A large number of Frankel pairs are produced and give rise to dislocation loops. And so one can use for electron irradiation effects. With the in situ, one can study with the high energy electron microscope. But if you don't want to make any damage in your sample, preferably people use to operate microscope at 200 kV or 300 kV. Okay. So the source for the electron microscope, it changes from like ancient days people use the tungsten hairpin like a filament, and then people start to use the LAB6, and then they start to use the tungsten field emission guns, whether hot field emission gun or cold field emission gun. They start to get that. Interestingly, the very important difference is like tungsten hairpin, if it produces 1 electron, LAB6 produce 10, and when we go for FEG, it produces something like 10 power 5 electrons. So because of the brightness of your source, the modern microscope, majority of the modern microscope operates with Schottky field emission or cold field emission. Very importantly, what one has to remember is, I said that when you go for a cold field emission, you will have a energy spread in the electron energy will be something like 0.3 electron volt you will have, whereas in the Schottky it will be around 0.7 electron volt. So if you want to have a less chromatic aberration, then people have to go for a cold field emission. And you don't have worry about the cold field emission, but I want a bit better brightness, then we can go for a Schottky field emission. So this is how the microscope, when they buy it, they choose the option. And whatever we have a microscope, that is Libra 200 FE, it's a special illumination type, where generally when you are changing the brightness in the microscope, the disk, the area of disk where the brightness changes with a different magnification. So whereas the color illumination, they have a additional condenser lens that made that through the sample you will have a uniform transmission. So that is one of the special thing. It's a truly parallel illumination one can get with the color illumination. Conventional illumination will get a nearly parallel, whereas it's a truly parallel, we can get a color illumination. So the Libra 200 FE TEM is concerned, which is having a parallel illumination. So when you look at the microscope, this source side, then you have a 200 kV accelerating tube. This is a 200 kV accelerator. Then you have a condenser lens 1, 2, 3. Then you have objective lens. This is upper pole piece and this is a bottom pole piece. And here you insert your sample. Here the beam is parallel across your sample. Then you have a projector lens part 1. Then you have a omega filter, which will be used for energy or spectroscopy analysis. Then you have a projector lens part 2, and then you have your screen, below which you will have your CCD camera. So this is the parts of your microscope, and you each will have its own role to play it in the observation. Okay, and so this is how the suppose after the sample, the electron beam passes through a specimen, above which you will have a 200 kV electron, below which it need not be always 200 kV electron. It will have a multiple energies. So this energy of these electrons can be analyzed to study the electron energy loss spectroscopy. So this is an in-column energy filter, whereas in the other microscope, they will have a post-column energy filter with like get an image filter. Okay, this is regarding that previous end of the previous talk. Somebody has posed the question: how will you prepare the TM specimens? It's very important. The TM need a very thin specimen, typically 10 to 200 nanometer. Particularly for stainless steel preparation for iron irradiated specimens, it is a bit challenging one in the sense. Uh, you have to have a very thin specimen, and by the same time your sample preparation method should not introduce any artifact in the sample. Suppose if I take a stainless steel sample, you all might have seen the diamond wheel cutter. Suppose if I cut it with something like uh, 500 rpm, I cut it, and then another stainless steel I cut it with something like 25 rpm. Then if you examine with a microscope, the 500 rpm whatever stainless steel you cut, it will have a more number of dislocations, whereas 25 rpm you will not produce the dislocation. So the sample preparation method itself, one should be very careful. It should not introduce any artifact. This one has to remember in any samples, whether it's a be it a semiconductor or insulator or oxides or metal, you whatever the method you use for preparing the sample should not induce any artifact. Particularly when we use the ion irradiated samples, one of the artifacts in your sample preparation by ion milling methods or focused ion beam when you are using, always there will be this beams which itself it will produce some surface damage. Then when you want to observe something, this observed phenomena is due to this your actual ion irradiation effect or it's a sample preparation effects. So such queries also it is there. So one has to be very careful, particularly in the stainless steel samples for radiation damage like white swelling experiments. We prefer to do with the electropolishing method for preparing the TM specimens, not the iron milling or FIB. But the modern sample preparation methods, some of the authors they have shown that you can prepare the specimen by FIB, then you can do a flash polishing. That is, after preparing the FIB prepared sample, you can do a electropolish it in the flash, in the sense high current in a shorter time scale, like 30 seconds or 20 second, 30 second, like that. You flash it with a high voltage, high current in a electrolyte. So through this process, whatever the damage layer produced by this focused ion beam can be removed, and you get a much clearer pictures. So if your sample has large number of damage produced by the ion milling process, then you will see large number of artifact. You will not see the true microstructure of your sample. So these are the difficulties in the TM sample preparation. Preparing cross-sectional samples or the other conventional methods, like you have to put all the silicon wafers together and cut it, prepare 3 mm disc and so on. So it's a long process. So I'm not going to cover the sample preparation here. What is important is how the electron interacts with matter. When the electron beam passes through a thin specimen of your sample, you will have elastically scattered electrons, you will have inelastically scattered electrons, and you will have incoherent inelastically scattered electrons will be there. Also elastically scattered incoherent electrons will be there, and coherent electrons also will be there. So all these electrons will be there. Apart from that, you will have a large number of secondary electrons are produced and X-rays are produced. And so what is elastic scatter or inelastic scattering? When you are looking at that, elastically scattered electrons does not change its energy after pass through the specimens, and this mostly used for a bright field imaging, dark field imaging, high resolution TM imaging. And whereas the inelastic scatter or the electrons loses its energy by some process, like it loses its energy by lattice vibration. That is nothing but phonon excitation or collective excitation of valence electrons, or plasma losses or interband transitions, inertial excitation like core excitation like oxygen K alpha, L alpha, and core excitations can also lose some energy, and Bremsstrahlung background also loses, we can lose some energy. So using such kind of loss process, you can get signals. So these signals mainly used for electron energy loss spectroscopy and energy dispersive X-ray analysis. It will give elemental information in your sample. So inelastic scattering is mostly used for analytical purpose, whereas the elastic scattering is used for mostly the imaging purpose. And in TM I am going to discuss very, very limited methods used in the microscope. In TM, there are many experiments can be done. Something like 60 different experiments can be performed in principle. So whatever we are going to cover will be very few. Okay, if somebody is interested, they have to go through the microscopy textbooks. Okay. And now, these are very, very basic one. Then what kind of contrast you obtain? So when you see it in many journal papers, you see a lot of TM images, and which is mass contrast, which is thickness contrast. This is one thing. So this is one of the example where the Fe3O4 is coated with a carbon, and you prepare a TM specimen, and you can see that this thickness in and around this portion is a uniform thickness, where this is a carbon and this is iron oxide. So this contrast is called jet contrast. When you have a uniform thickness and you have a contrast, then that contrast comes because of the jet contrast or the mass contrast. Okay, the other contrast will be, suppose if I look at this specimen here, you can see here that is a relatively bright compared to here. This is nothing to do with your jet contrast. It is doesn't mean that here iron is there, here gold is there. No, here this is thickness contrast. If your sample is thick, then again the scattering will be more and it look dark. So one is the mass contrast, the other one is thickness contrast. Okay, the other contrast what we usually see, it's called a diffraction contrast. Okay, that we will see it in the subsequent slide. Okay, the modes of operation, when we look at that, we can do electron diffraction. It's one of the very easy experiment people do it. The earlier days we will have a formula. If the electron diffraction is concerned, it will be a very important difference between the X-ray diffraction and electron diffraction is it will just interact with only few planes, something like 20, 25 planes. Whereas when you look at the X-ray diffraction, it will interact with something like thousands of planes, 5,000 or 10,000 of planes. You will get the diffraction signals. Here only we had diffraction from only 20 or 30 planes, and the diffraction pattern whatever we obtain from XRD is much larger angle diffracts, whereas here it will be very, very small angles. So because of that small angles, if you look at that, this is a set of planes. When we diffract a very small angle of theta, and then you can the tan 2 theta can be written as R by L, where L is the camera length and R is the where is the center spot or direct beam to the diffracted beam, what is the distance, that is the R. And if you are simply taking your Bragg's law 2d sin theta equal to n lambda and using this tan 2 theta, this formula, where for small angles the tan 2 theta become 2 sin theta, so it is like R by L. So then if you simplify, you will get RD equal to lambda L. The ancient days when you do a diffraction with the conventional negative, so what we have to note down from the microscope is camera length, then R you can measure it, and then you can get the D value. Lambda is known. If you are 200 kV, then the lambda is 2.5 picometer. And the modern microscope, you need not to note down anything, because this camera length, each camera length is calibrated with the CCD camera. What we have to get is your unit will be in a 1/nanometer. So you measure the unit and take a inverse, you will be able to get the planes corresponding to your sample. So this is one example where samarium cobalt thin films which are prepared by ion beam scattering. In the as prepared sample, we could see the rings which are amorphous, which shows the very hollow rings. But when we anneal out the sample at 600 degrees Celsius, you start to see the sharp lines, which is corresponding to the samarium cobalt 5 crystal structure. Okay, so this what one can see it in electron diffraction. We can get if the sample is amorphous, you get a hollow, whereas when you have a crystalline, you will get a very, very sharp rings. And if you have a nanocrystalline, like this is a tin oxide quantum dots, if you are looking at that, you will get a spotty ring pattern. Whereas when you go for a like gallium nitride nanoparticles, bit bigger nanoparticles, you can see the hexagonal pattern, which is like a single crystalline pattern also you can get. And this is another pattern where we have seen this an aluminum vanadium 4. It's a very, very special case. People who work on oxide system, they will see some kind of charge or ring. Such a charge or ring, when you one can observe it in electron diffraction, if you are do a diffraction very carefully between the main spots, you will see the charge ordered peaks or spots in your sample, or super reflection peaks, you can see it. Okay, how do they analyze your diffraction pattern? So you will be able to get H1 K1 H2 K1 H1 K1 L1 and H2 K2 L3 L2. You can get that HK values will get, but for indexing pattern we have to get the angle between the planes also, one has to match it. And also when you take a cross product of two planes, you will get the zone axis. Then you can simulate the diffraction pattern using different softwares and produce a zone axis pattern, and you can match with your other diffraction spots can be indexed. And very importantly, not the D value alone, we have to match the angle between the planes also must be calculated and analyzed. And this is one of the example where the zirconia is one of the proposed material for inert matrix fuel materials in the reactor as a fuel, inert matrix fuel. So this material, when we do ion irradiation, before irradiation, it's a asymptoted sample has a zirconia. So one can do a RDF or radial distribution, radial profile. So from that we can get the diffraction pattern can be indexed. When we upon irradiation, like krypton ion irradiation, we could see some of the monoclinic peaks, which are no, this is monoclinic. This is some of the star marked portions are coming from the tetragonal phase. So such kind of phase transformation can be studied with a electron diffraction. Or the other cases, like if you are taking a zircon ZRSiO4, you take it and you take it crystalline pattern as a function of 1.5 krypton ion irradiation. You can look at that as a function of irradiation dose. Above certain dose, they start to the precise diffraction spots start to disappear, and finally you will end up with a complete amorphization. So such kind of irradiation induced amorphization or irradiation induced phase transformation, if you want to study, you can use the electron diffraction very easily. Okay, the other imaging like one can use for the bright field and dark field modes of electron diffraction pattern. Okay, electron TM imaging. So when you have a bright field imaging, it's nothing but direct beam imaging, and dark field imaging nothing but diffracted beam imaging. So when you see it in electron microscope, you see the direct beam is at A and diffracted beam is B. So which beam you use it for observing the image? So if you are using the either by inserting objective aperture such a way that only direct beam is allowed to form an image, then it's a bright field imaging. In the dark field imaging, there are two modes of one can do a dark field imaging. One is we can keep objective aperture same and tilt the beam such a way that the diffracted beam has been brought into the center, and you can do a on-axis dark field, or you can move the objective aperture to the diffracted peak, diffracted spot, and allow to form an image. Then you will get a dark field imaging. So off-axis dark field imaging. Generally, we prefer to do a on-axis dark field imaging. Okay. So now, so what is the difference between bright field, dark field imaging? Suppose if I do these are lead nanoparticles, you disperse it on a carbon grid, and if you are seeing, if you are allowing only the image to form from the direct beam, you will get this kind of image. This is a bright field image. When you look at the objective aperture, you put it in the diffracted rings and allowed to form an image. It's not all the particles are white. Whatever particles contribute to the diffraction pattern on this zone alone become white, rest will be dark. So this is how the dark field image is done. The same thing we can, another example, we can see the lead telluride nanoparticles are cuboids. So you can see that there is a center, you have a large number of particles. There will be only, if you look at that, this yellow color marked, these particles form a diffraction pattern corresponding to these two rings. So that give rise to bright, whereas the rest of the particle will be dark. This is one thing. And second thing I want to show you here, in this bright field image itself, you can see same size cuboid, like this cuboid. Okay, this cuboid and this cuboid, more or less both the cuboids are same. As I said that in the previous example, when I discussed about the mass thickness contrast, if the mass and thickness is same, here more or less both are in the same size, but one look dark, one look gray. So this is because of the diffraction contrast, whether the crystal is orient with the beam or away from the beam. So on such cases, the diffraction contrast also give you the contrast. When the crystal is strongly diffracting, that will give a strong contrast like black, whereas the crystal is not diffracting heavily strongly, then you will get a light. So this is a diffraction contrast in your material. Okay, so this is another example where we can see this gallium nitride decorated by platinum nanoparticles. So we could see the bread field image, and we put the objective aperture one of the platinum ring, and we could see that the platinum is decorating the surface of your gallium nitride nanowire. And also we have done with a high resolution imaging to see the platinum nanoparticle on the hazard gallium nitride also. And the dark field imaging, one can use it for the other application. Like this is one of the work which was done in the, not by us, it's a report from where we can study this. Like you take a copper 100 or a copper 110. So it's an environmental TM. It's operated at 10⁻⁴ millitorr. So where the oxygen is introduced and the sample is heated at 350 degrees Celsius, and do a dark field imaging of copper 110, and they look at that how the copper oxide evolves as a precipitate, nucleate, and grow. So when they look at that, you can see that the copper nucleation occurs when you look at the shape of the nuclei is very different from the 100 to 110. So one can study the nucleation and growth of your nanoparticle. One can study with the dark field imaging if the matrix is different matrix compared to the particle. So on such cases, one can do this exercise. Okay, so now we are going for a high resolution TM imaging. So I am not going into the details of high resolution TM imaging, where one can discuss in terms of contrast transfer function, and these are fine details. What I am going to discuss is how HRTM can be used for our material science analysis. That's what we are going to do. This is another term we can call it as a phase contrast image. So whenever you write a electron beam as a wave in a wave form, then you will write like a e power x phi, where the phi is the phase part. So this is a phase contrast image where the phase part of the electron beam is modified when it passes through a specimen. Okay, when it passes through a specimen, because of that, the phase part is modified. It is called a phase contrast microscopy. Okay, so when you do for HRTM, the phase contrast electron microscopy, you can see very, very finer nanoparticles. This is one example where quantum sized tin oxide nanoparticles, one can see it very, very small particles. You can see there are two planes, 101 and 110, with two different angles. If the angle between the planes are 68 degrees, one can very clearly see by the HRTM images. And also these samples, when they heat treated at 800 degrees Celsius. Initially, the size was 2.5 nanometer. Then the heat treated it became like 25 nanometer. Conventionally, they have studied with the optical absorption. They found that the band gap change with the size. So quantum size effects can be studied. And this is again another example for a lead particle. And this is another thing, analysis one can do it when you are doing with the microscope with the FFT. So during an electron microscope HRTM image, you will get the real-time fast Fourier transform image. So after taking an image, you can do a fast Fourier transform. In this case, particular example, where a gallium nitride grown by CVD method, where gold acts as a nucleation site. Whenever gold acts as a nucleation site, when the tip of the wire, you will see a gold head. So this is a gallium gold alloy forms, then subsequently the gallium nitride grows. So when we look at the diffraction, when you look at the HRTM image, when you do a FFT, you get a regular hexagon, and apart from the two spots also appears. So you can put a filter on the two spots and do a inverse Fourier transform. You will see that gold fringes. Whereas when you put a aperture only for the hexagon and do that, then that time you will get the interference pattern only from the gallium nitride. So such kind of analysis one can do. And this is another example where oxide dispersed strengthened steel, one has to use the yttrium titanates as particles, and this yttrium titanates as a dispersite. So we have done some experiments on Y228O7 before and after irradiation. One can see large number of stacking faults are formed. You can see very clearly the HRTM images of the stacking faults forms. This is the case with Y228O7. It's a pyroclose structure. Whereas when we do with a Y2TiO5. Then we, when the same ion addition, when we look at that, we found the face-centered bubble formation. So one can see this kind of information also. So in the same similar kind of material, one is pyrochlore, the other one is orthorhombic structure. In the Y2TiO7, it's a FCC pyrochlore, so the stacking faults are expected in the FCC structure. And we have also calculated the stacking fault formation energy, and this energy might be given by the damage production during ion addition, krypton. So that gives rise to stacking fault formation. Whereas in the case of orthorhombic structure, where the stacking faults are not expected, but the krypton accumulate and form a kind of faceted particles. The faceted particles are formed, but still it is not amorphous. Still you can see that the lattice fringes are seen. This is mainly because there will be some of the cleavage planes where the vacancies will be accumulated and you will get a planar bubbles. So that gives rise to such kind of faceted bubbles. Okay. So when we do HR images, we can do all this kind of experiment. Now we go for the other experiment, which is very unique experiment. It is not done much. So we will discuss something about the electron energy loss spectroscopy. It's a very useful technique, and it's a very useful technique and powerful technique for light element analysis. Suppose if I take like a lithium or beryllium or boron or carbon, if you want to analyze it, this is one of the very powerful technique. And you can see this, there are some red color, yellow color, blue color is there. So I can say that whatever the sharp, this is a typical K edges, we will get a short tooth kind of edges. You will be seeing it in electron energy loss spectroscopy. Then there are something yellow color, delayed one, that is mostly not useful in electron energy loss spectroscopy, I can say. But then the other one is the white line. The two lines, doublets will be there. This will be mostly seen in the 3D transition metals and the rare earth series, 5 of rare earth series. So you will get in a 3D transition metals L2, L3 lines, and whereas 5 of it, we will get M4 5 edge. So these two things are mainly used for the electron energy loss spectroscopy. So this is nothing but you will have a specimen with a say, suppose you 1 minute, just so suppose you have a specimen, like you have a very thin specimen. So you are putting like a 200 kV electron beam with the energy of 200 kV. When it passes through a specimen, so you will get some other energy of your electron beam. Here you will get it. So it will not be like 200 kV. Here it is a 200 kV. Okay, here it's a 200 kV. Whereas when we pass through, it need not be 200 kV. Here it will be low. So if the energy of the electrons after passing through the specimen, it's a 200 kV, then it is a zero loss peak. So if you look at the zero loss peak, the counts will be very large. Then there will be another losses, like suppose you have a plasma losses. Typical plasma losses will be like less than 25 electron volt or 25 electron volt around. So these are the plasma loss peaks. And the electrons with less energy, like 25 EV, means 200 kV minus 25 electron volt, that electrons you collected, and you will get the spectra like this. Then you will have a kind of ionization losses, like carbon KH or oxygen KH. All losses you will be seeing it. But if you look at the counts, the number of electrons after passing through the specimen, if you look at that, here it is 10 power 4, this will be like 10 power 0. So it will fall exponentially. So this you have to remember. So this is actual experimental results which is obtained from our microscope. This is taken for vanadium pentoxide. If you are looking at that, counts is here 10 power 6, and the plasma loss is of the order of 10 power 5. When we look at for this is a carbon, so carbon sp2 sp3 bonds, you can see it here. This is comes from the TM grid, where carbon coated copper grid you said that, you can see that. Then this is a vanadium L2 L3, and you can see the oxygen KH. So if you are looking at that, this gives electron energy loss spectroscopy. So you can see that in 3D transition metals, you can get that L3 by L2 intensity ratio. This is L2 and this L3 intensity. The ratio, if you are looking at that, it changes with the charge state of your material. So for example, this is a VO2 and this is V2O3, V2O5. So if you have a material with a consisting of vanadium, and known calibration is done, L2 by L3 intensity ratio, with a different charge state, you can get a straight line. Then if your compound has like a aluminum vanadium oxide, it is having a different charge state, one can measure the charge state of your oxides. So that way, this is a very powerful tool for 3D transition metals and its alloys. And the other thing we can get for calcium cadmium oxide, you can see that this oxygen KH, how it modified as a function of calcium concentration. So by careful analysis, EL and F, the near edge features, one can get the information about first neighbor and second neighbor information. But these works are, they need very, very detailed work. And the other thing, what we can see is like you all might have seen this like uh, crystal field splitting in your 3D transition metals, where the orbital angular momentum is constant. Or you can see that when you have a 3D transition element, whether it is put it in an octahedral cage or tetrahedral cage of oxygen surrounding, then the whether the orbital t orbitals are in line with oxygen or out of line with with oxygen, so that will split into two T2G Eg levels, so that give rise to splitting in the L2 and L3 intensities. So one can see this L2 and L3 splitting, T2G Eg splitting. Here this microscope, whatever microscope we are used for this experiment, is a 0.7 electron volt. If you have a something with a monochromator, then we can see all three lines together and two lines together. One can easily see it. So in this particular topic, actually, we have also done some experiments with oxide dispersides strengthened steel, where dispersides are mostly Y2TiO5 or Y2TiO7. We have extensively studied with the high resolution TM imaging, with the titanium addition and chromium addition, how Y2TiO5 has formed more. And further, we have done some 3D atom probe tomography experiments, and also we have done ion irradiation and how the particles disappear upon ion irradiation we have done. So it's very important, the stability of these particles and the bond nature, the strength bond, MO bond, metal oxygen bond in Y2TiO5 and Y2TiO7 has to be studied. So here we have used the electron energy loss spectroscopy to study the nature of bonds, and this is what I have discussed about T2G splitting. When it is in octahedral symmetry, then you will get a 3D orbitals goes to T2G and 2T orbitals goes to EG, and splitting occurs. So here one can see that this is a Y2TiO7 and this is Y2TiO5, and this is the experimental cage oxygen cage. One can see that the A1, A2, generally oxygen K, it's supposed to start from 520 and 530, but here one can see that A1, A2 splitting. This comes because of the pre-edge features. These pre-edge features are much stronger in the case of O7 compared to Y2TiO5. So it shows that Y2TiO5, Y2TiO7 used to be relatively more covalent in nature compared to O5. So this is one thing, and also this is consistent with the titanium L2 L3 ratio also. So further we have carried out the calculation. This is a DFT calculation. One can get the information about the charge density difference in Y2TiO5 and Y2TiO7. Our calculation as well as the yields experiment, metal oxygen bond strength, when we calculate, we found that Y2TiO7 will be more covalent compared to Y2TiO5. So we predict this Y2TiO7 particles more in oxide dispersed strength and steel will improve the radiation stability of the steel. So these are the things one can do with electron energy loss spectroscopy. The other experiment one can do with a TM is scanning transmission electron microscopy, where we need a high angular annular dark field detector. So we need an electron source. Then after this is a very powerful technique for observing the phase contrast image as well as the jet contrast image. So the phase contrast image mainly obtained from the bright field detector, and using the dark field detector we can get the jet contrast image. So these are the very modern microscope like a neon, which will be producing very nice results in the STEM mode. But conventionally, this dark field detector, when you are looking at that, suppose the gold particles in carbon film, when you are using the bright field detector, you will get the image where the black particles in a white background. Whereas when you are using a high angular anomaly dark field detector, you'll be seeing very clearly. So this will give a more contrast. So for counting particles, so you may ask me a question whether this is the only application of this, but it is not true. You can see there's this let nanoparticle I have shown you in the bright field image when we are discussing, but the same thing when we see it in a STEM mode, we can get better. And when we see it in a steel, we can see the with reference to the one grain to the other grain, you can get the diffraction contrast also. Grain microstructure one can see, the oxide dispersers can be seen, Z contrast, because the oxide particles are yttrium rich, Z is more, so that will be very clearly seen it in this. And the other thing, like you can see, this is one of the example where we can see some of the gold nanoparticles on a carbon, where we can see when we see it in a conventional silver nanoparticle. In the bright field image, conventionally you don't see very clearly. So here you can see a few atom gold clusters, whatever marked in a 1, 2, 3, 4. You don't see very clearly in the conventional atom image. But when we see with a STEM mode, we can very clearly get that because of the jet contrast. So that way, one can use a STEM detector for powerful jet contrast imaging, and also one can use for different jet contrast. This is one of the thing I want to share you. This is very important in a modern aberration corrected microscope with equipped with the STEM yields. One can see this is the one system like lanthanum calcium titanate, where the point not 2% the calcium lanthanum is doped in a calcium. That is, if you take 1,000 calcium atoms, 2 atoms will be lanthanum. So here, this high resolution STEM mode, they get a very clearly the atomic contrast. And this is a TiO2 lines, and this is a calcium oxide lines. So it goes like this. So alternatively, it built up. And when they do a electron energy loss spectroscopy on each column of atom, like 1, 2, 3, 4, 5, they found that very clearly the column 3, particularly it is a more bright. So by looking at the brightness also, one can see when they do electron energy loss spectroscopy, they can very clearly see the lanthanum M45 edge. So that means below these atomic columns, one lanthanum atom is there. So that start to give your lanthanum M45 signal. So the electron energy loss spectroscopy can be used more powerfully with a STEM mode as well as the conventional TM mode also. And one can use for the electron energy loss spectroscopy used for energy filter TM imaging also. And again, this other example, the other one is on charge ordering. One can see the L2 by L3 intensity ratio. They measured along one particular line. Their charge ordering can be 3 plus 4 plus fluctuation. One can study it in a complex oxides. And so here I stop it. And this is the last one where the conventional microscope, whatever aberration is not corrected, then this is one of the system where barium titanate, if you are looking at that, you will get only the planes of your images. Whereas when you go for a aberration corrected microscope, we can individually the barium atom, titanium atom, oxygen atom can be easily seen. So this will be possible with a aberration corrected microscope. In India, currently there are something like 14 or 15 installations are available in India. So people can approach concerned people and do this exercise. And thank you very much for your kind attention toward this talk. Here I stop it.
Thank you, Amirthapandian.
Any queries?
Maybe you can take some questions which are there in the chat box.
Yes, sir.
Starting from previously, this Ambuj Mishra has asked a few questions, 2 questions.
Yes, yes. Okay, I'll just check the chat box.
How do you prepare TM specimen for stainless steel samples? So this is the first question, I think.
Yeah. So as I said that when we want to prepare a TM specimen for especially for stainless steel sample, when you want to do ion irradiation, then preferably I want to prefer to do a electropolishing method for sample preparation. Suppose if you are not studying the not studying the ion radiation effect on the stainless steel, then you can go for a conventional ion milling and get the morphology or microstructure of your samples. But still, if you are looking for like a dislocation density and other things, better to go for a conventional electropolishing method in stainless steel sample. The second question, one of the question was the magnetic constituent is there in your sample, then what you will do? So this is very important. So sometimes I have also come across people come up with some of the magnetic powder samples if you want to prepare a TM, if you want to see it in a TM. It is a bit challenging because this uh, if you are using like ferritic steel itself, forget about nanoparticle. If you have a ferritic steel, it's a solid sample. When you operate in a microscope, that the ferritic steel itself, it acts as a magnet. So when the electron beam pass through a specimen, that will bend the beam quite largely. Because of that, imaging it takes very difficult and it's a very challenging. So on such cases, one is the magnetic constituent if it is there. And if you want to get the magnetic information, then people should go for a Lorentz microscopy. It's a very special lenses are needed where the pole piece gap is much larger. So that one can use for that. The other thing is like if it is a ferritic steel, then you want to see it, then you have to thin down the specimen less than 25 micron before electropolishing or ion milling. Then probably you can reduce this kind of beam deflection. So that way one can do it. And magnetic nanoparticles, the one method one can do is like you can ion beam resistant glue, you can disperse it and thin it. Again, you do ion milling and see it in a TM. There is another method people usually do. But still, there are some people assume that, like in Japan, I hear that people they do the magnetic.
Of course. I will just leave this on for now for
Yeah,
a few minutes.
no
I'll come
problem.
back in a few minutes. Okay.
Sure.
டீ கூட குடிக்க விட மாட்டேன்றான்ல.
No problem, sir. We can start.
You have another 2 minutes to complete last chip of tea.
Okay.
Good morning.
Good afternoon for me.
Yes.
I just had my lunch
Okay.
during the previous talk.
Okay.
So
I was
Jeroen,
telling him, I am telling.
so Jeroen, it's from sorry, after lunch to lunch, correct?
Yes, this is an inter lunch talk.
Good morning, also.
Good morning.
My stomach is full. Yours will be full later. Yes. Let's see.
And Jeroen, also another typical thing you have not to face, that post-lunch session is little, lethargic. So that trauma will not be there. Everybody will be fully charged probably.
That's good. And actually, the previous speaker, thanks very much for introducing many of the things. I didn't really go in so much detail in my talk, so I can just now very nicely refer to many of the items, like the resolution, the wavelength, and so on, and directly compare protons to electrons. I think it's quite nice. I mean, one has advantages over the other in different areas, but of course the basic principle is very similar.
I think you can start. I
Can we
request
start?
we'll start. Just 1 minute. I'll request Amirthapandian to introduce
Yes.
the speaker. Yeah, thank you.
Yes. Thanks. Thanks for the organizer. Let us welcome Professor Jeroen van Kan. And Professor Jeroen van Kan has completed his doctoral degree in 1996 in the Virgin University Amsterdam, Netherlands. After that, he has worked at NUS, National University of Singapore, for various positions, and he is currently associate professor of physics at NUS, and he is also deputy head for the engineering science program and vice president of Microscope Society of Singapore. His research interests are ranging from ion source development to proton beam writing, nanolithography, and nanofluidics, and various topics. And he has got several awards, and he has given more than 45 invited talks in different international conferences. And his publications are more than 165 scientific publications. And today he will deliver a talk on applications of MEV focused proton beams and proton beam writing and imaging at the nanoscale. It's very interesting topic. Professor Jeroen van Kan.
Okay, thank you, and thank all the organizers for giving me the opportunity to present a completely new form or different form of microscopy to this audience. Although there are a few facilities like our facilities in India, I've actually installed one of them myself in IIT Kanpur. I'm not sure what's the status of that at the moment. And I've seen at least 1 or 2 more of such facilities in India. I hope to demonstrate some of the interesting things you can possibly do with such type of facilities. So let me give an outline of my presentation of this lecture. I will give first a very brief introduction on nuclear microbeams. How do you get nuclear microbeams? Then I will discuss a little bit what you can do with it. Mainly 2 topics. One is proton beam writing, and the other one is nanoscale imaging. Especially proton beam writing have a few more applications, and the nanoscale imaging, I will link a bit back there also to the previous talk. Some of the techniques that we use with proton beams are also used in electron beams. But of course, protons have a slightly different interaction in material, so you get different characteristics. And in some cases, you get very interesting propositions there. Okay, let's have a look. I mean, how can we look at the world? We have seen that also in the previous talk. You can look with an optical microscope. Where standard people reach half the wavelength in resolution. Of course, then you can ask yourself, how come our modern day devices, our phones and our PCs, what type of details do they have inside? What is the size of those details? That's typically on, people talk about even 10 nanometer node these days. And most of these are made with 197 nanometer optical lithography. You would think, how is this possible? But through interference, you can go pretty small in down to the possibly 10 or tens of nanometer size level. So, of course, optical microscopy is standard half the wavelength of light. That's why we saw in the previous talk. You would like to use something with shorter wavelength. Electron beams are very short wavelength, but of course a proton beam, if you look at the equation, has an even shorter wavelength. Here we see some of the applications that work in the macroscale, the intergalactic distances, and then the microscale. Here we see some of the structures that are made, and even go down to the nanoscale, where we have, for instance, nanofluidic structures. Yesterday we saw one very short example of this. I will show a bit more detail how you can work with DNA in nanofluidic systems. If you look around the world and look for focused proton beams, you realize that our center has the best focusing performance in the world. Most labs cannot focus below 100 nanometers, and most not even below 1 micrometer. Is very challenging for most labs. Although there are several maybe can reach a bit below a micron. So here, I'm sorry, I just realized it's a little bit displaced. I'm sorry, your microprobes are in the ocean, but so are most of them. That my map is a little bit displaced. But here you see the number of nuclear microprobes around the world. In Africa, there are only in South Africa 2. All of this is in Europe. And of course, here in Japan, Australia, it's more in Melbourne and Sydney, and in Singapore. And of course, here we see many different labs. But the world premier labs in this field are Melbourne, Leipzig, and as mentioned, we perform way better than the other 2 labs even. And the original microprobes were started in Europe. Oxford is a very strong example for this. We are based here, I put the map correctly, in Singapore, or I'm based currently in Singapore. Singapore, here you see a map of Singapore. I made this actually quite long ago. About 20 years ago, I think I made this map. This is written with proton beam writing in a thick piece of PMMA, a 2 MeV proton beam, which if you use the SRIM simulation, you can then see this is roughly about 60 microns deep. And what you see also, what you will see if you do the SRIM simulation, the proton beam comes in very, very parallel, but at the end of its track, you realize the beam spreads a little bit. You can see this also very nicely in the map here. If you would actually overlay this with a real map of Singapore, it's not correct, because Singapore is a very small country. It's only, according to this map, 600 square kilometers, but currently Singapore has reclaimed land, and this area here now has increased the total land mass of Singapore, and here also a little bit, to about 700 square kilometers. So, and here we see our nuclear microprobe facility. Very similar to some of the pictures we saw before by other speakers. You have also high voltage accelerators in India. Ours is rather special because it's a single-ended machine. In a single-ended machine, your ion source sits in the middle. You generate positive ions through ionization, and then at the positive potential, your ions are fired out. The nice thing is you only suffer from the energy spread of your accelerator, which there is always, it's not perfectly 2.0000 MeV, it's 2 million volts, plus or minus about 10 volts at best performance in our system. Similar accelerators from high voltage would, if you have a tandem accelerator, many people have, would produce similar terminal stability, but if you use it as a tandem accelerator, of course, your energy spread of your ions gets double due to the fact that you use the terminal voltage twice or multiple times. And the other issue there is that you use a stripper gas because you have negative ions coming in, and then you remove the electrons in the middle of the accelerator, and then you accelerate them further because you then at your positive potential, but then your energy spread gets larger. What do I mean with energy spread? What we saw in the talk by the previous speaker, chromatic aberrations are very important if you want to focus down to the ultimate level. So as I mentioned, our system, we have beams of 10 electron volt stability on the 2 million volts. And if you then want to focus your beam, one of the aberrations is the chromatic aberration. So if you have a beam which has a larger energy spread, your chromatic aberration go up and your beam performance is not as good. So that's why we have a rather unique system, because from high voltage they didn't sell that many of this type of accelerators. So if we then look at the accelerator, it's a big machine. It's about 20 tons in total. We bring it through high resolution 90-degree magnets, stabilize the energy, and distribute the beam among many experiments. I will just only now briefly mention them. High resolution Rutherford backscattering with an energy resolution of 1 keV. Then we have a set of nuclear microprobes. This is the standard one, which I've seen also in India in several labs, and as I said, also commissioned some of them. Here we have a cell beam line. I will show some examples of this line as well. These two lines can focus around 20 nanometers. This one sub 100, between 100 nanometers to half a micron at best performance. And this particular beam line, as we saw in the earlier days of this meeting, very interesting is ion therapy for cancer treatment. I will come back to that, but here we have an external beam line where we can irradiate cancer cells and simulate the cancer treatment in very big facilities, which we saw earlier in earlier presentations. That is very useful. Here we have a standard Rutherford backscattering facility. What is required to get ultimate performance of such a system? I was asked in several labs also in India. I made here just a very brief overview of what is needed. One thing which is needed is a high brightness source and low energy spread. The chromatic has to be low, and the brightness is the current density per opening angle. It's not only current density, but it's current density per opening angle has to be very good. And the other thing is you need to have a good lens system. So these are quite well fulfilled in our lab, and also in other labs. But some of the fine details people often miss, and therefore cannot achieve down to the ultimate size. And some of them I've listed here. You need to pay attention to noise, magnetic noise, thermal noise, temperature, as I mentioned, temperature and thermal noise, and so on. All these small details make the difference between 20 nanometers and a few hundred nanometers. As I mentioned, we saw in the previous talk, electrons have how to say, wavelength down to a few tens of picometers. Electron systems, potentially an proton beam can have a resolution, wavelength even smaller than that, by the ratio of the square of the masses, which is roughly 42 times a shorter wavelength. But currently, as mentioned, the best performance is actually shown here in this slide. It's about 20 nanometers. What I did here is I take a very accurate so-called nickel grid. In the previous talk, we looked at transmission electron microscopy images. So what we do here is, what we see here in blue is an image of this grid and a so-called proton transmission image map. So what we do here is we map the protons that are scattered through this grid, and then because this grid is very sharp, the sidewall of this grid is a few nanometers, and then we can deconvolute the beam size. And as was mentioned by the previous speaker, how do you define a beam size? Okay, I define it by imaging this grid and say my step, and I deconvolute this step, this error profile, and then I get the 1 sigma at 9.3 nanometers by 32 nanometers. It's just a definition. Some people take 50%. As mentioned by the previous speaker, but as long as you make sure how you define it, people realize how you do this, then yeah, we have this definition of resolution. How do you better? One thing would be getting a higher brightness source. I'm currently developing this. I don't have time to go in details there, but this would potentially give us the largest improvement possible. There's some other fine details. I will not go in exact details there, but the main improvement would be the improvement of the brightness of the ion source, because then we can achieve better performance. So let's have a look in proton beam writing. Why do we do proton beam writing, and how do we do it? If we shoot a charged particle beam, like there's now electrons, but also protons, into a material, you see all kinds of things happening. You could have proton or particle induced X-ray emission that was briefly mentioned by the previous speaker as well. If you're shooting this charged particle beam, you interact with the nuclei and the electrons, and the inner shell ionization and then back relaxation of the outer electrons gives X-ray emission, which allows you to do X-ray analysis. The nice thing with protons is, when a proton goes in, as mentioned before as well, you see that you hardly produce any Bremsstrahlungs background. Only low energy electrons are generated. And that means your background in your X-ray spectrum is very low, and you can have very low detection limits in X-ray analysis, way, way lower than electron beams. In electron beams, typical limits are 0.1%, and here we talk about 10 ppm or a few ppm at best performance. Then we have Rutherford backscattering. That was extensively discussed. Nuclear reaction is also discussed in earlier talks. ERDA was discussed. As I just now showed, I tried to show to you what is our resolution, and that is done through transmitted ions, and looking at the transmitted ions. Another thing what you could do is you could bring these proton beams into an IC circuit and do ion beam induced charge or current measurements. Some of the examples you can do. You can look at secondary electrons, and you could even look at induced photons. These are some of the examples or some of the probes you can look at. I will not discuss all of them. I just mentioned them here. Just let's focus on the system I showed you just now, which can perform down to 20 nanometers. That's shown here. Here we have this nuclear microprobe with, in this case, quadrupole magnetic lenses. It goes quite different from an electron microscope, because in an electron microscope you could use circle symmetric lenses, but since the ion is 1800 times heavier compared to an electron, you need much stronger fields to focus protons compared to electrons. So we use magnetic quadrupole lenses. Here I list the different beam lines that we just saw in the previous slide. And here I show you some of the application areas we are working on or have been working on. We have also a clean room facility to post-process structures that we make with the proton beam. Yep. So as if you use the simulation packages that were discussed so far, you realize that if you use protons, you see that the electron stopping is about 4 orders of magnitude larger compared to the nuclear stopping. So that means the proton, you can use the SRIM program, you then realize will just go straight through, in this case, a resist material. It will hardly spread because it only imparts energy to substrate electrons, which, if you even calculate head-on collisions, is just 1 or 2 keV energy. But most of them don't have such small impact parameter to the electron interaction. It's a bit larger, of course, most of the interactions. So you would have a much lower energy again. So typically the electron energy is just on the order of a few 10, 20 electron volt. That was, I think, asked a few days ago. How do you calculate electrons? Actually, that you can do through the Casino program, which is shown here. Of course, the issue with the Casino program is it's non-relativistic, so the simulation here is not 100% correct, because if you exceed about 30 keV, as the authors say, you would start to run into issues of non-relativistic effects. Well, you need to take them in. The program only runs non-relativistic, and you need to take relativistic effects into considerations. As mentioned, currently people use use photons, EUV, to make IC circuits, and they use electron beams to make the masks for these circuits. So you could think, would protons possibly not be a better probe for this? You could see, if you compare energy deposition of a proton probe compared to an electron probe in resist materials, these are typical electron beams used to make masks for EUV lithography. They need to go at the ultimate level and make the ultimate structures for the finest detail. But you realize that the electron beam produces a lot of energy deposition around its track, whereas the proton beam doesn't. Within 1 or 2 nanometers, the energy deposition has greatly dropped by even 20 orders of magnitude if you go a little bit further away. If you look at the fine details, I think within a nanometer, it's 2 orders or so. So it very rapidly drops, and this is for a 500 keV beam. So potentially, if you have a proton beam which could be focused to this level, then you could be in business in, for instance, making masks for optical lithography. The issue is, why are we not doing that? One of the main issues is the focus is not as good compared to electrons, because the brightness, as I showed in the few slides ago, of a proton source is about 1,000,000 times lower compared to an electron source. As I mentioned, I'm working on trying to bring this up by hopefully 5, 6 orders of magnitude, being then really competitive to electron beams. So if I can do that, then proton beams could be a very interesting proposition for nanofabrication. So how do we do fabrication? with proton beams. I will just show this very briefly. I don't go in so much detail. So you have so-called resist materials. These are plastics. The proton beam can change them through electron excitation. Very similar to proton therapy. You impart a very little bit of energy to, in this case, a resist material, and then you could use suitable chemical developers and get latent structures. As mentioned, I will not go in so much detail, but what you then have or could possibly get is drill a hole, let's say 10 microns deep, maybe 100 nanometer diameter, and then you can fill this, for instance, with nickel. So then you can get nickel nanowires. Or you can make structures in nickel, which you can use for nano imprinting. Because, as I mentioned, in optical lithography, our people use optical lithography to make all the devices, because electron beam lithography, although it's a smaller spot size, doesn't have the throughput. They need to work with techniques to replicate. In that case, in this example here, they use EUV masks. And so they make with the electron beam a mask and use the mask to replicate. Another way to replicate could be making a stamp, a hard stamp, and use the stamp to replicate structures in polymers in this way. That people have shown also with this type of stamps, replication down to 1-2 nanometers details. So potentially this is a very interesting proposition. Let's show you some examples what we can do with the proton beam. You focus your beam to 60 nanometers to show you that there's no issue in moving of these electrons through the material. You look here, yes, I have 60 nanometers all the way down through the resist. The beam remains focused as we saw in the simulations, and you can get very high, tall, well-defined structures. Here's some other examples in PMMA. The left one was SU8 resist. And here we see a new type of resist, a very high resolution resist, where we can even write structures below 20 nanometers. It's a negative resist. That means I put my protons and I change the molecular structure of this material. And then if you have a negative resist, that means I really have a beam of this width. So as you saw, what I showed you earlier, beam size is around 20 nanometers. Yes, I can use them and make structures down to this level. As if we manage to improve the source brightness for the protons, then we could possibly breach the limit of 10 nanometers and become suddenly, or have at that point, a very interesting alternative to electron beam writing. Here you see the typical energies that are required. In this resist, most optical lithographies cannot pattern HSQ. You actually need wavelengths down to less than 150 nanometers. You see that also because you need to create or give energy to these electrons of about 4 and 8 electron volts. So let's look at some applications. Yesterday we saw also one application where we looked into tissue engineering. I just show 1 or 2 examples here. So what we did is, with the proton beam, we made very accurate nickel masters. We imprinted it in PMMA, and then you see here the imprinted PMMA profiles with this, in this case, a cross section of about 10 microns. And then we use this to seed cells on them. In this case, endothelial cells. You see, normally they have triangular shapes, and if you let them freely move around, they actually change expression and become elongated. So you can really change the expression of these cells in this case. You see here you grow a bit longer, and you can really manipulate the cells that are originally more triangular in shape into long rectangular shape. We have some more examples, but due to time limit, I will not show them. Then we have some interesting examples in fluidics. If you take fluidics, if you calculate the Reynolds numbers, you realize that if you have channels of similar size as we saw just now for the tissue culture, that you get very uniform parallel laminar flow in this type of microchannels. We measured here the flow profile, and you see it's very uniform across. We put here some nanoparticles in this microfluidic system, and they nicely flow very parallel. Here we show the profile of the velocity of the particles. One thing you could then think of doing is particle separation. So what we do here is, in this case, fluorescent particles. We make very accurate structures. In this case, again, we make a mold, and then on the mold, in this case, we don't imprint like I showed earlier, but we cast a polymer, poly-dimethylsiloxane, on there, which we can very nicely bond to glass. So we cast it, then we take it off, we bond it to a plain glass slide, and then we have calculated with this particular geometry, we can let particles travel through, and then you could actually, as a function of size, separate particles. You can see here, you have the 200 nanometer particles would be preferentially here, and in that way you can then let the particles flow through and separate as a function of size these particles. Particle separation, as I mentioned, in the microfluidic flow is very important because your flow is laminar. So if you have a mixture of different particles and you want to separate them, because maybe you have tagged a cancer cell and you want to take them out in circulating tumor cells, then you could possibly do this through a lab on a chip like this. There are other geometries that people use, but this is one example. What we show here is, again, a similar system made by the proton beam. Sorry. So what we do here is we have a so-called particle separator, Brownian motion particle separator. So where we have smaller and larger particles. The smaller particles, the blue ones, we undergo more Brownian motion. So if they undergo more Brownian motion, we force them to only stay at one side. So we let these particles move, but before they reach this sawtooth here at the top, we turn the field, electric field or magnetic field, depends how we do it, around. That means these particles, when they first distributed all over the chip, they only interact, and we set up the system in that way, with the bottom sawtooth. This is a very tall sawtooth. I think it's 10-20 microns tall, and then it only interacts with this bottom sawtooth. The larger particles undergo less Brownian motion, larger particles, less Brownian motion, so we let them interact with both sides. So every cycle, they would go half a step to the left and 2 steps, if you take this as a unit step, to the right. So at the end, they would be here on the right. So you could have a continuous particle separator here. One thing you could think about here would be a DNA particle separation. As mentioned, if you tag, for instance, in circulating tumor cells, your DNA with a particular nanoparticle, I think we can even separate, in this case, 100 nanometers from 130 nanometers, we showed in a follow-up paper. Okay, next, this is all high aspect ratio, very accurate channels. But next, I would like to go into nanofluidics, very similar to what we saw in the example yesterday, I think it was, where this DNA molecule sits on these ridges of about 30 nanometers, it was yesterday. What we did here is we wrote channels in PMMA, and then we develop it like we always do, and then we thermally bond a top on this. And then to show you we have a good cross section, what we did is, after this was again sealed with a top slab of PMMA, we again irradiated with the proton beam, and we can then show you that we have a very good control in this process and get nanochannels, in this case of 200 nanometers by 2000 nanometers tall. So these channels can be used also for DNA separation, because depending on the length of the DNA molecules, you could possibly think about, in this case, entropic traps, DNA molecule separation, as was proposed in the US, MIT, if I'm not wrong. Yeah. So, but you see, if you do this process, proton beam writing, okay, maybe takes half an hour to write such a chip. You saw our big facility. We have more than 20 people using this facility. They say you can have 1 day beam time a week. So I can make a few samples. But my colleague said, I want to have many samples. It's not enough. This process is too slow. So we went into nano replication and tried to optimize this for DNA nanofluidics. I will show some examples of some DNA, of some nano, micro and nano replication, and then come back to the DNA analysis. So here we show a very accurate stamp, a nickel stamp. We can imprint this in PMMA and then go back to the previous process where we bond it, and then we can get nanofluidic lab-on-a-chip devices. So we can then do this in a very fast manner. The other way, instead of pressing it, you could also cast PDMS on it. It's a bit slower, but it also gives you good results. Here I will show some examples that you can possibly think of. You can make waveguides where you can shoot a laser light through it and have this Mach-Zehnder interferometers, or you can have gratings, or you can have micro lenses. I will show one integration of photonics and fluidics here with these micro lenses. Yep. So how do we do it? There's many ways you can do it. If you would do some more studies on lithography, you could think about doing it through grayscale lithography. I will not go in details, but I thought this is actually quite an interesting way of doing it as well. You irradiate with the proton beam cylinders in resist. You need to choose the right resist material, because next what we do is develop it, and then we thermally treat it such that it becomes a semi-spherical lens. So if you calculate the volume of material, because here we have a good contact angle, it remains nicely on the silicon substrate or quartz substrate, depending what's your underlying substrate. But by tuning the diameter and the height of your resist, you can get the exact right curvature of the polymer here. And you could possibly do this through resists, as I mentioned, but maybe other materials have even better characteristics, like polycarbonate. So what you could do is you could put a very thin metal layer on top of this, electroplate it out, and use this nickel stamp for nano imprinting in polycarbonate. And then you see here we form these micro lenses. And then we can put these micro lenses in a laser beam. Laser beam shines nicely through it, but is then focused in our microchannel. As I mentioned, sometimes we want to separate particles in a fluidic system. But sometimes we want to encourage reactions in a fluidic system. So how do you do this? You have laminar flow. So what we could do is we can take these micro lenses, focus it in this fluidic system, and then I think it doesn't play, then I would have to change the screen, so I will not do that. But what we can do is we can rotate this polymer plate here with these micro lenses, and then rotate it in the laser beam. Then you would rotate the microspheres here in the solution. You can grab them through laser tweezing, and then you can rotate it, and then you can really do mixing in your fluidic system, which is quite useful because mixing in microfluidic channels is actually quite a big challenge. Here I show some other example. I'm not sure whether India has a synchrotron facility. I'm not. Singapore has a small synchrotron facility because at some point people managed to get this facility in Singapore. The thing is, with a synchrotron, you could also make very interesting high aspect ratio structures. But in order to make them, you need a very accurate, tall, and parallel nanostructures to be able to then make more use or get more interesting structures out of such an X-ray facility. So what we did is resist processing, and then we finally have a metal structure on a silicon nitride membrane, and then we irradiate with this structure the resist material. X-rays can go in very deep in the material and can produce very nice structures. This is an image of the gold structure we use, our mask. This is another form of replication, a bit similar to optical lithography, but in this case with very short wavelength X-rays, with I think a few nanometer wavelength. And then if you look very carefully, we can have very high resolution here and very smooth sidewalls. If we use this mask in an X-ray exposure, we can actually get very tall, very accurate SU8 structures, in this case produced through X-ray beams. So in this case, just another example of how you could use, in this case, a proton beam fabricated mask to mass replicate structures. Another example here is also, again, a microfluidic circuit where we proton beam irradiate it. We make a master out of a particular resist. I will not go into details of the resist here. And then we have this in MAP. That's a particular type of resist. Very high resolution again. If we then here we zoom in even more, you can see it's really very high smoothness sidewall. We did some investigations on these sidewalls. They typically have sidewall smoothness on the order of a few nanometers. It depends on the resist. I think the smallest we've seen is just 2 nanometers or so, sidewall smoothness. If we then make this into a metallic stamp, because you could do that, then you could try to make that fluidic circuit as I showed just now by imprinting. You see the resolution deteriorates a very little bit, but still it's very high resolution. Our nickel plating facility is also one of the best in the world. This was actually developed by the original DVD industry. Of course, nowadays DVDs are not really used anymore, but those days that was one of the ways people were making DVDs, through making a master and imprinting this into polymers. And so the quality, sidewall quality of this process is very good here. And you can see here the sidewall smoothness of also sub 10 nanometers. So one way of replicating, which we did with some collaborators in Singapore, is actually through injection molding. So here we show replicated structures through, here's the nickel mold, 0.5 micron gaps, 1 micron deep, and then we replicated this in PMMA through injection molding. Injection molding, I guess most people think more about large structures. We show here we can even do this down to 500 nanometers. These are just some examples. We also use this to imprint in PMMA. I think the imprinting could have been optimized a bit better. Next, I come to, I think, a very exciting piece of work on the DNA manipulation in nanofluidic systems. We saw yesterday one DNA molecule. I will show some more interesting examples, I think. So, and now you could ask yourself, how long is my own DNA? If I take just one strain of the DNA, of course you have, I think, 2 copies in every cell. What is the length of one DNA molecule in every cell, each and every cell in your own human body? So you take one cell, take out the DNA, and start to pull. Any idea how long this is? If you really keep pulling, without breaking it, of course, then human DNA ends up to be almost 1 meter. Difficult to show, but like 1 meter long. Your own DNA, each and every cell in your body has 1 meter of DNA. Of course, it's a double strain, so if you would be able to open the DNA, then you would have 2 strains of 1 meter, and maybe you have 2 copies, so then you have 4 meters even. But in principle, it's quite long, so it's a bit challenging to work with that. So at least at the start. So what we currently doing is we use model DNA T4, which is about 60 micrometers in length, or lambda DNA, which is 16 micrometers in length, more or less. So I will show some examples of what you can do with this DNA molecules. As mentioned, we can make very accurate stamps. Here we see a stamp which is made out of SU8 and HSQ. Sorry, HSQ, as mentioned, gives us the best resolution. And it's also a bit stronger, I didn't mention just now. HSQ is actually hydrogen C-siloxane, and the chemical formula is SiOX. So silicon, almost silicon dioxide. So it's a bit stronger, of course, compared to a polymer. So what we then do is we cast PDMS on this, polydimethyl C-siloxane, and then we can replicate details down to even a bit below 100 nanometers. If you look in literature and you ask the best people in the US, in Harvard, they say they cannot do this. They need a modified PDMS. We also now start to use the modified PDMS, but because the proton beam has such smooth energy deposition, such straight sidewalls, we can very nicely replicate these structures on these masters, so we can really manipulate DNA molecules in single at a single molecule level. So here you see the master before casting PDMS, and here you see the master after 200 times casting PDMS. So typically your master can last many replications. Actually, often the master can last longer, but it sits on a piece of silicon in this case, and if that silicon is brittle, I'm not sure how many of you used silicon before, it's quite brittle, so you have to be a bit careful not breaking the silicon. Here we see the microfluidic system under optical microscope image. And here we see an AFM image. AFM is pretty challenging because our channels are very deep. How can I image with an AFM tip? With an AFM tip, this profile of this channel. Here we try to do some imaging of this channel of 105 nanometers. It's not so easy. Then what we can do is we can put in DNA molecules in smaller, one particular lambda DNA, in smaller and smaller channels. What happens if you put a DNA molecule in a smaller channel? It will elongate itself. And that's what that's what you see here. If you go to a cross section of about 60 by 100 nanometers in PDMS, then you can see this DNA molecule is extended to, I think it's about 50% of the contour length. 17 is the total length of this particular DNA molecule. Then what you also can do is you can play with the ionic concentration of the solution in such a channel system. By the way, these channel diameters and in this case solutions are modeled after physiological conditions. So the similar things you find back in the human body. So if you then go to lower and lower ionic strength, you see DNA being negatively charged. It starts to extend as well through self-avoidance in such a channel system. So one thing you can do now is play with this. So we made a cross configuration channel. We pump in the DNA molecules, and you see here the DNA molecules in green. And then we pump in this type of protamine. Protamine can also be found in sperm cells, because in sperm cells, DNA has to be compacted into very small sizes, because a sperm cell is one of the smaller cells. So what we see is when we bring in this protamine at physiological conditions, you see the DNA starts to shrink in the nanochannel, even in the nanochannel of 300 nanometers. So, and it goes down to the resolution limit. We run this for a few different cells, a few different DNA molecules. Next, if a DNA molecule would fertilize an egg, what happens? It comes in a higher salt concentration. I don't have, it's a time-lapse video, so I don't have the video for this. But what we can see here, we bring in a higher salt concentration. So if such a DNA molecule ends up in this higher salt concentration, it starts to slowly, the time scale is here a bit different. In the previous one, it's just tens of seconds, 10, 20 seconds. But here we're talking about minutes, 10 minutes. We can actually follow them even after 2 hours. And you can see the DNA molecules start to extend itself and unravel itself and become, in the analogy of the fertilization of an egg, be ready for replication. So this is very interesting experiments we show here. Another very interesting and possibly useful application, although I think we're a little bit late now, is specifically for COVID, is large-scale mapping. So large-scale gene mapping. There's other applications which can still, of course, be used for this type of experiments. Let me explain first how this works. So this, you can go online and you can, from this company, Bionanogenomics, Genomics Vision, you can buy a system. What they have is many sets of 40 nanometer sized channels. You see them here, they're a few millimeters in length. I think 1 or 2 millimeters in length. And what they have done is they take this double-stranded DNA and put in fluorescent beads on the DNA at specific sites. So if somebody is infected with COVID, you would get a very particular expression somewhere along the DNA or attached to it. So if you would put that into PCR, you can amplify this, and then people say, hey, that person has COVID. What you also can do is, you could, if you know where you have to put these fluorescent markers, you could throw that then through such a channel system and try to image this. The thing is, this technology is based on double-stranded DNA, and it's pretty expensive. We came up with another method. Actually, when this company started to develop that technology, we also were doing experiments on double-stranded DNA with fluorescent tags to it. But we brought it one step further. Double-stranded DNA, if you now denature it and open it, as shown here in the slide, then you could bind a counter linker molecule to it. So this one would bind very specific sites. So you need to make sure that you have, let's say, 20 sites where you bind. Then you have site-specific labeling. You put a very small fluorescent marker on it. Then what happens, it's very similar to what we saw just now in the other example, but there you have double-stranded DNA. Where do you think it's easier to bind fluorescent probes? Of course, on a single-stranded DNA, it's much easier than all the sites are open. So now you have any sites available to you to put these fluorescent markers. So you could then very quickly put such a DNA molecule in a nanochannel. We have one more trick. We don't need channels of 40 nanometers, but we can even use 100 plus nanometer sizes. And then we get full extension of the DNA through this special trick. I don't have time to go in that now. Then we get site-specific labeling. So if you label for COVID, you could get a particular fluorescent signature showing in your nanochannel, and you could very quickly say, hey, this person has COVID or not. But of course, there's many other applications to this. You could think about cancer treatment in gene therapy. There's some other applications that you can possibly think of. There's not enough time to go in all the details, but the strong point in our technology is we can do single-stranded DNA molecules here. And then having site-specific labeling all across the DNA molecule. Next, I would like to go to using the ion beam. Just now we used the ion beam to write structures and use them in this case for nanofluidics and optics. And now I would like to go to fluorescent imaging and other forms of imaging using ion beams. So as we all know, although COVID is bad, but mortality is luckily not that bad. But still, there's many more people dying of heart attacks still every day. So one of the things our group had been looking into in the past is looking at coronary heart disease. So in this case, we use test objects and give them a so-called high cholesterol diet. We all know high cholesterol is bad for you, and then your arteries might calcify and clog up, and that could possibly lead to heart attacks. That's of course something we don't want. But one thing we can do is use our technologies to see at the single cellular level what is exactly happening in such an artery. You see here the build-up of this plaques in such an artery, and then when after a few weeks giving this test subject high cholesterol diet, then we take this artery section and slice it out and look at such a section with our here an optical image. If you would try to analyze this with an electron beam, remember the simulations in the casino in my earlier slide, you would have electron spread, because we're talking here about a section of 1 or 2 cell level thick, so 10, 20, 30 microns in thickness. If you shoot an electron beam through it and you want to have some yield, you would typically have quite a lot of spread in your electron beam. And as mentioned, X-ray analysis would not give you enough yield because of the detection limit, because of the high Bremsstrahlung background. So what you can then do is put such a section after optical imaging into our proton microscope, very similar to the way I measured our beam size. We look at energy loss. So no energy loss because there's no material. A lot of energy loss. It's in yellow, is high energy loss, green a bit less. So yes, here there's more material present in this section of the artery, the problematic section deletions in this case. So fine, other techniques can possibly also figure that out. But what we also can do is then zoom in and look. Here we see the STIM image. And next we can look at the X-rays being generated with the proton beam. So what do we see? We have increase of iron, possibly a bit less copper, increase of phosphorus and calcium. You see here calcium, it's increased. We all know calcification of, we can show that here. There's no other technique that can show this in this type of sections. The other thing is you see zinc is possibly anti-correlated to this. So this type of research gives people very interesting information. I will not go in all the details on this. So people say zinc is maybe beneficial, calcium is a side effect, but it's bad, of course. So let's have a look at coronary heart disease as a function of gender. You can actually even look as a function across the world. But you see, women have much less chance on getting coronary heart disease. I'm sure the statistic's a bit older, but it's still the same. And it's much lower. So why is this lower? Why are women? Why don't women suffer from coronary heart disease as much as men do? So you see here New Zealand, it's particularly bad. I'm not sure whether India is in the map. I don't know whether I have the data for that. Sorry, India is not in the map. But one thing you can see, if you look at the amount of unregulated iron in the human body for women, it's of course much lower, up to the age of about 40 to 50. Whereas for men, it's much higher already immediately from the age of 20. So it looks like there's a possible correlation between this build-up of this calcification and the iron levels. But more research would have to be done on this. One thing what we can do is we can do very high resolution imaging of cells. As I showed just now, we can do whole sections, but we can also do whole cells. We have actually the previous images were obtained in our system with resolution of a couple of hundreds of nanometers, our first nuclear microprobe. But the later generation, as I showed in the beginning, the systems that can reach 20 nanometers can have very nice whole cell imaging as well. Some of you might have heard about the helium ion microscope. I'm not sure whether the previous speaker was briefly mentioning this microscope. I think he mentioned neon microscope, but I think that's maybe still the same type of microscope. But anyhow, if you use helium, you have, again, similar to electron beams, very high surface resolution, but in a cell you cannot look through, which you could do with high energy MEV helium ions. So what we see here is, again, a so-called scanning transmission ion microscopy image, the density map, as I mentioned a few times. So the proton beam coming in, going through the cell, measuring the energy loss, which we see here, the energy loss map, through the transmitted beam. We can also look at backscattered particles. We can do Rutherford backscattering. We can look even at fluorescent particles. So we can look at fluorescent particles. The thing is, you have super resolution techniques available. I'm sure you've heard about it. If you use super resolution techniques, but you put your fluorescent particles very close together in your cell, because whatever you were looking at has high density of these fluorescent particles, you cannot really discern these particles. As was mentioned also by the previous speaker, what is really resolution? What is your real beam size? We have a beam size of 20 nanometers. So we can excite these fluorescent particles in this case, in this cell, with very high resolution. And if we use Rutherford backscattering, we can even triangulate where these cells, where the nanoparticles are exactly. Are they in the nucleus or in the cell membrane? This is possibly very interesting to know if you want to target drugs to the DNA for your treatment of cancer, for instance. And then later, maybe with the nanofluidic channel, want to figure out whether your treatment makes sense. But one thing you could also do is you can see in this type of microscopy whether your particles are in the nucleus or didn't penetrate the nucleus. Here we show some examples of this. Here we go for very high resolution, where we compare the super resolution technique to our fluorescent, proton-induced fluorescent imaging. At the moment, we have about 20 nanometer resolution. With this new high brightness source I'm developing, we hope to break the 10 nanometer resolution. As mentioned also by previous speakers, this is almost my last topic, cancer therapy. We can use ions for cancer therapy. The most commonly used ion for this type of therapy are protons, so-called proton therapy. But carbon therapy, as mentioned by Professor Tourmont, is also very commonly used. Both of them have their Bragg peak, where they deposit most of the energy near the cancer and hardly any on the way in. Of course, if as standard X-ray therapy, you produce damage, but behind the tumor, you also produce damage. So that's, of course, not very good. Let's say the tumor is just behind the eye. Then a patient wouldn't be able to see anymore after this treatment. But if you use protons, and I visited one center in Berlin, they treated, and they're still treating people with protons, and the proton would just stop in front of the cancer. Not in front on the cancer, but the sensitive neurons that sits behind that are still preserved because the proton beam doesn't put energy there if you calculate rightly. And then the patient can still see. Of course, the treatment is much more expensive, but for society, it's of course a great benefit if this person doesn't need to depend on other people because the person turned blind after trying to get rid of the cancer. So one thing, one beamline actually we have set up and we're starting to use is a beamline that can take tissue sections and focus our beam in these tissue sections and investigate how best to use this type of treatment. How many protons should you use or carbon ions should you use for this type of treatment? As mentioned by Tourmont, people don't fully understand this energy deposition process in this cancer type of therapy. So that's why the systems we set up with an external beam in this case are very useful to give an answer here, because you can irradiate this type of cancer cells with the proton beam and figure out what is exactly happening in this expensive cancer treatment. So in that way, you could possibly improve this type of cancer treatment significantly and treat more patients, because I heard in Taiwan where they tried to treat patients without making money, still every treatment, every exposure is about $30,000 if I remember the number correctly, or 30 or 50,000 US. So it's pretty expensive. But of course, if you can make sure patients are still be able to retain their sight, that would be very nice, or kill certain cancers which otherwise are not reachable. So I'm not sure in India, I'm not following it that closely, but as I understand, around the world, about 1,000 of these centers are being set up to treat people that have this type of cancers. So now the question is, as mentioned by Tourmont and by our research and a few more groups, people don't fully understand how this type of treatment works. You look at the general picture, yes, it works, it's better, but it's a bit like trial and error. But that's a bit, of course, people have gained some knowledge in this over the years, but still, it would be very useful if you can take a cell culture of a patient, quickly do an irradiation, and figure out what is exactly happening to such cancer sections. And then determine this patient is very much helped with this type of treatment, or it should be done with so many protons or whatever. Then you can optimize this type of treatments greatly. So with that, I would like to end my presentation and open the floor to questions.
Thank you, sir. So we'll check the chat box if there is any question.
I don't see any. Maybe I missed it. Everybody is hungry.
So may I ask you one thing?
Yes.
The data where you have showed that men are already having iron-rich body naturally. So is it it is naturally it is like this, or what is the reason for it that women are having less iron? But you said that there are more chances of getting the disease on men. So
Yeah, of course, smoking is also men smoke more, so that's another complicating factor. But another the other factor is, of course, women have their monthly period, and then they lose blood, and blood contains a lot of iron, so it's naturally kept lower up to the age of here 40, 50 years, and at that point when it starts to increase. Of course, it's also your diet, and you cannot generalize. That's the same with the cancer therapy. You need to. That's why I said if you try to treat a cancer in gene therapy, one thing is very important there. If you maybe I can not so I can go back to that slide, but it's very important to have a patient-tailored treatment. So you might want to quickly analyze by doing this type of gene mapping whether or not the patient is reacting to the gene therapy. I'm talking to collaborators in Singapore, and they reckon that they can improve gene therapy, which is besides proton therapy, one of the ways people think to go forward with cancer treatment. I think they can improve this form of cancer treatment through very good feedback on this type of knowing what happens to the DNA of the patient. So patient-specific treatment. Same with the iron. Some men might need more iron, but these are just general trends. You cannot always pull through general trends for every individual person. A person to person is different.
And when you are talking about this gene therapy, it is actually relatively a very advanced technique. So the results or outcome of to notice will be taking quite a lot of time. Means how the cells will respond or the gene will respond when it is being changed or.
What I understand from my collaborators, they mentioned that in the case of gene therapy, we would need actually within a few hours need to know whether the patient is responding to the gene therapy. So similar to COVID, you would like to have something that can respond very quickly to or can give you a very quick answer on whether a particular genome sequence is changed or not. So this type of platform could help in that.
Okay, yesterday there was a talk on your patterning simulations by Cuerno. Then you were saying that you will be discussing this biomolecule functionalization on pattern. So do you have some slides on that? You said that you will be addressing those issues.
What I meant is, I meant actually this type of work
where
we manipulate DNA molecules in, as I showed just now, we have looked at many different proteins reacting with DNA molecules and trying to do fundamental studies on that. We have many more examples of this type of work, and the large-scale gene mapping. That's the work we are focusing on.
Okay.
Maybe there was on the chat too short to go in details.
Okay, thank you, sir.
If there is no more question, we'll thank the speaker, and thanks for your nice talk, sir.
Okay, so I hope things are more clear. So if people are interested, we can always see whether there's a possible form of collaboration. One of my former postdocs, I'm not so able to see because this picture is a little bit older. I think she left already at that time. We set up a collaboration. We tried to set up a collaboration with her. She's working also in India at the moment as a professor, one of the institutes. So if there are possibilities for collaboration. You never know.
Okay, thank you.
Okay, thank you.
I take this opportunity to thank Pandian also. So we'll close this session and maybe we'll meet after lunch, that is 14 hours, 2 p.m. Thank you.
Thank you.
Can someone hear me? Is there Asokan or Indira around? This is Alain speaking. Asokan, are you around? This is Alain speaking. What about the attendance? Can you hear me? Ah, thank you, Jalal. Thank you. Jalal, since you are live, and I'm connecting from France, is it the same on your schedule that I'm giving a presentation in 15 minutes? Good, thank you.
Hello.
Hi, Allah. Good afternoon.
Tapo, glad to.
Oh,
I
nice.
recognize your voice.
Yeah, nice to see you virtually, though.
Yeah. By
Everything
the way,
fine?
did you get my slide full screen?
I think you just go for F5 or this. No, right now it's not full screen.
Okay. So you mean that it's? Let me check. I mean,
Down there is a symbol for full screen. You can just press that one.
Do
Or in
you see such animation? Something like that? Do you see it?
No, right now the title slide is there, but all your thumbnail slides are also being seen. So you have to either press F5 or at the top or whatever. Slideshow mode.
I didn't get the point.
No,
you can
right
press
now.
F5.
Yeah.
Function 5. In your laptop keyboard.
So this works, okay?
No. You can see in your screen itself, there is one symbol which shows shown for full screen mode. That you can press. Notes, commentaries. After that, fourth symbol you can see. There is one symbol, no?
See, just before this reduction in view, that minus sign is there. Just left hand side is a cup.
Wait.
Yeah.
Jesus. Why is that so? Do you get it like that?
No. Maybe you can go to the first slide, click again.
Wait, okay.
In your desktop, you make it full screen, then you present it. That's also fine, I think.
Everything. Now you get it?
No.
Yeah, we can see the slides, but only in normal mode.
Only in normal mode. Okay.
Yeah.
Let me get that. Do you get it at full screen mode?
No, I think you should make a full screen in your laptop first, then you present it.
Yeah, what I'm doing at the moment, actually.
Hi, Marcel.
Hi.
Good.
Hi, Tom.
At the moment, you are not seeing the first slide.
No. The first slide is there.
It's the title slide. It's the title slide, Alain.
It's what?
It's the title slide. Is the title slide only is now on display? Yeah.
And now do you get something else?
No, only the title slide.
Oh, Jesus, why is that, sir?
You can go to the slideshow in the top menu and make it full screen. Start from the beginning.
Oh, Jesus.
Alain, you can click on that small symbol before your insertion tab, right at the top.
Hello. Yeah, Ashwan.
Yes.
Ashwan?
Yeah. We'll wait for a few more minutes, then we'll start. You let him make it a full screen. Then we'll see.
And at the moment you are looking at the first slide. Do you see the slide like that?
Slides moving, yes, we can see.
Okay.
Now slides are changing, yeah.
I think Marshall has to tell him how to do it in French.
Yeah, but if I make kind of a full screen presentation, look like that, you don't see or you see?
No,
Here it is not changing, but I think it's okay. It's visible anyway.
Yeah, that means I should not take this way, but I should make
can you check whether you made it multiple screens in your laptop?
it should be like that, right?
Yes, it should be like this, yes.
Okay. Probably I will lose some kind of animation. I mean, kind of, and I have I have a movie at some point. I don't know whether it will work or not. We'll see.
You may log out and log in again. You may try this.
Sorry?
But if you press F5, would that not work?
F what?
F5. Thank.
No, the thing is that I can switch onto a full presentation, but it seems that what I'm doing, when I'm doing that, you are not getting the image. That's what I can do at the moment, for example. Now, do you see SOI wafer or not?
Alain,
Yeah.
regarde les trois petits points en bas à droite. Quand tu baisses ta souris,
Attends,
tu vois le téléphone et tout.
Attends, je sors du diaporama d'abord. Je sors du diaporama.
Oui. Il faut que tu descendes ta souris pour faire sortir quelque chose. Où tu as le micro.
Oui, j'ai les trois petits points.
Les trois petits points, tu claques les trois petits points, puis tu as plein écran en haut, au-dessus. Je sais pas si ça marche.
Là, je suis passé, oui. Oui, j'y suis là.
Bon. Et donc, reviens. Maintenant, tu remets ton système de...
Et oui, mais sauf que là, je ne peux plus passer sur mon truc. Sauf que
Ah,
là,
tu peux plus. D'accord. Bon, bah, écoute,
voilà.
désolé.
C'est ça mon problème.
Désolé.
Voilà, si j'ai ça. Et là, vous voyez ma diapo, là, vous faites quoi ça,
Ah oui, on la voit très bien.
Mais alors, attends. Par contre, je te tiens, Marcel, là de toi. Par contre, quand je passe en plein écran, comme ça, vous ne voyez pas.
Ça change rien. Je comprends pas que ton plein écran ne marche pas. Regarde le diaporama.
Là, j'ai changé de diapo pour toi ou pas?
Non, non, non. Appuie sur diaporama en haut et clique début pour voir.
Oui, hein?
Change rien. Non, non,
Ouais,
sur diaporama. Tu as fichier, accueil, insertion, etc. Puis diaporama.
Just on top of 7, number 7
Okay.
on your.
I think it's, and we could start anyone. Right?
Press on diaporama just below smart card.
Yeah.
And then you can choose the setup of the slideshow. To the left, it's more or less in the middle of the screen, below the word smart card of your title.
Yeah. Yeah.
Diaporama.
I could ask for diaporama, okay, for presentation. But if I do that, for example, here, for example, you see.
No.
Slide.
On top in the orange bar, on top. Go to the orange bar, diaporama, left. Go to the left with your mouse.
Yeah. Yeah, sharing. It's everything tells me it's okay.
Okay, then. It's visible.
Okay, probably. So you can see it now or not? Can you see something?
It's visible, but not in presentation mode.
Jesus. Okay, I take only 2 minutes more.
Yeah, take your time, please.
If I'm going in presentation.
What is this icon on the top of instance? Yeah.
It's okay.
Oh, this is good. Yes, this
okay.
is okay.
It's okay, Alain. Perfect.
This, yeah, this is fine.
Okay, we start. I don't know whether animation will work. Yeah, I think it's this mode is okay. I will not touch anything. Okay. Thank you, everyone. Thank you.
Okay.
I have no idea why it was.
Good afternoon. We'll start our session. I request Dr. Kaviraj to introduce the speaker.
Yeah. In this session of IBMS International School 2020, our teacher is Professor Alain CLAVERIE. Professor CLAVERIE is materials scientist. He did his PhD in the year of 1984 from University of Toulouse, and he was a director of CEMES Toulouse, France from 2011 to 2015. At present, he is engaged in a number of projects in collaboration with semiconductor companies and also works as private scientific consultant. He has Association of India from very early stage. I see that he worked in India in CSIR Chandigarh. So now Alan's interest ranges from the nucleation and growth of extended defects and nanoprecipitates in solids, diffusion anomalies in semiconductors, strain transfer in nanostructures, very low energy ion implantation, and more recently GST alloys for PCM devices, that is germanium antimonotelluride alloys for phase change memory devices. Today he will give two lectures. First one from local time 2 o'clock to 3 o'clock, the smart cut technology and industrial success of ion implantation, and the second is thermal evolution of defects in ion implanted silicon. So I request Professor CLAVERIE to deliver the lecture.
Thank you very much. Good afternoon to all. Frankly speaking, I do regret not to be with you in India at the moment. What I love to do in December in principle, but this year it was obviously not possible. First, my name is my given name is Alain. My family name is CLAVERIE, and I'm French, as you can hear. And I'm French coming from the south, that is close to the Spanish border here. And this place for a long time has been seen as very much connected to Spain. And what I can tell you about this city is that the very first important thing is that it's a place where we do not play football, but where we play rugby in place. Toulouse is very proud of hosting one of the good rugby team there. And it's a nest of the Airbus industry along with Hamburg. And so since India is a very good customer, I'm glad to tell you that. And also this city of Toulouse is hosting the CEMES, a laboratory of the National Center of Scientific Research, known for its bull here, and of which I had the pleasure to be its director a few years ago. Okay, so today I will be talking on the way and the material science aspects of technological process, which is aimed at fabricating the so-called SOI wafers. SOI stands for silicon on insulator. And basically in modern microelectronics, one of the starting material is not a bulk wafer, but a SOI wafer. And SOI wafer consists of 3-layer structure. On the base, you have a substrate, which is basically there just to handle the stack. And then after you have on top, you have a thin, more or less thin top silicon film, which stands on top of a buried oxide. And this is all structure made of a nice thin silicon layer on top of an insulator, this box, and the whole thing on the base or under substrate, which is named silicon insulator wafer. So actually, in modern microelectronics, depending on the application, these wafers are used either for the new generation of fully depleted transistors, or for radio frequency, or for power devices, or even photonics, and very importantly for making images. In all cases, the only thing is that you changes the respective thicknesses of the top films and on the buried oxide films, depending on how much of silicon you want that on top, and how much how thick you need the insulator to be below this active layer to isolate it from the rest of the world. So this is a very generic type of wafer, and you can buy that on the market today. If we take only one type of application, for example, the first one, which for fully depleted SOI transistor, the idea there is not to have a transistor sitting on top on the bulk wafer, but just to have a very small transistor, which consists in everything is optimized so that the channel is extremely small. You see, buried between the source and the drain. And the very important thing is that this channel is isolated from the rest of the wafer. So you can see 1 TM image here. Here you have the gate, and you see this box, the insulating layer here is typically something like 25 nanometer. And in modern technology, the top layer for fully depleted transistor is something like between 8 and 10 nanometer, which is extremely small. And you can see it here is a gate. And by the way, you see my arrow?
Yes, we can see it.
Okay,
Yes,
so this is the channel is just here, okay? And in this case, what you need is that you need to have a very thin layer. And actually, the same wafer that I use not only for planar transistor, which is the bet of the European industries, but also even if you make some things more exotic, or a thin-TET or a 3-gate transistor, in principle, I mean, it's a good idea to use these SOI wafers, okay? So, few numbers, I mean, that's an enormous market. I mean, these SOI wafers are developing very fast. Most of the industrial players, they tend to build their devices on that. And it is, the forecast is that
yeah.
There's some problem, I think.
Are you facing any problem?
I think he may not be knowing it.
Yes, yeah. He may not be knowing it. There is some problem.
Looks like his connection has troubles.
Yeah. Yeah. Dr. Ashan, is there any way to?
We don't have any way. I think he is having only chat box only we can write.
Yeah. Shall we write?
Yeah. I think now he has learned. I think he has left the meeting and he'll come again.
Yes, he's coming back, trying to come back.
Now he knows, looks like.
Yes.
Hi, Abdullah, good afternoon.
Afternoon.
I think it's computer, he may be rebooting it.
Yeah.
One minute. Hello.
Yeah, hello.
We'll ask Marshall to call him over phone from there. That may be the better choice.
I don't have it. Hello. I'm going to try to find his phone number. I don't know what it is. I have to find it.
Okay, sir. Yeah, please.
Marcel, I have Alain's number. I can give it. I mean,
Sorry?
So
I
type in
have
your
Alain's phone number, so I can give it to you.
in the chat box. You can type.
Yeah.
Okay.
Yeah.
I have to look the chat box. Okay.
Give me a few seconds. Please.
Yeah. I get it.
Okay.
Marcel, I have posted in the chat box. It's there.
Yeah,
Yes,
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 already
yes.
got it. Yeah.
Okay, great.
Bon. Alain, on ne t'entend plus. Pour l'instant, son téléphone est coupé, ce qui ne m'étonne pas. His phone is just in a message situation. So I have to try another possibility. Sorry, but for a moment I don't find his phone number.
Topo, is that number you can? Is that same
No,
number?
he's not answering. He's in a message mode.
Okay. So, yeah, Ashokan, Dr. Ashokan.
Yeah, Kaviraj, what we'll do is we'll advance one of the talk. There is a demonstration talk now.
Yes,
Then,
that is what I was trying to.
Yeah. So then you can join later.
Yes, yes. That is the Saif and Umapathy stuff.
Yes, Umapathy. He'll be joining another 2-3 minutes.
He is already there, but he will be preparing for the demonstration, so it will take some 2-3 minutes time. In between, Marshall sir, if you could contact Professor Allen, then let us know.
I will try to, and I will give you an information. Yeah.
Okay.
Thank you.
Sorry, but
no problem, sir. Actually, participants are already logged in, so we have to find some way to get them engaged. Actually.
Okay. Okay. So, hear you later.
So all the participants now will be having, in 5 minutes, we will be waiting for Alan sir to join. If not, if he still has some problem, then we can take this schedule of demonstration, which is scheduled at 4:15, demonstration of hands-on training, RUMP and SIMNRA. So this we will be taking now. So I hope you all have got that file which I sent you through email. RUMP file, zip file, so you get that thing handy, and some downloads we have already told you to do it on your PCs. So we will be shortly beginning that demonstration. So write in the chat box if you are all ready with the software.
So, Indra, you and Dr. Ashokan will be managing this part.
So Umapathy has just to start it. So we will again be bothering you once Alan sir will be back with us.
Yeah, that I know. But this one I don't have to be.
Joindre Alain d'une façon urgente.
Yes, sir.
Mais je n'arrive pas à le joindre. J'essaie de trouver un autre numéro de téléphone. Merci. Ce n'est pas grave du tout.
Bonjour, enregistrez la forme que... Oui. Bonjour, enregistrez la forme que le numéro demandé n'est pas...
So, Umapathy, you can update us whenever you are ready.
Yes, madam.
Professor Tulemon.
Oh putain, il est pas.
No.
Umapathy, you can make it full screen.
So now,
Yeah.
sir, is it visible?
No, it's black. I think you have to select the screen.
Bonjour madame, excusez-moi de vous déranger, Marcel tout le monde ici du CIMAP à Caen. Je cherche absolument à joindre Alain CLAVERIE au plus vite, mais son téléphone portable est en messagerie et je voudrais savoir s'il y a moyen d'avoir son numéro de téléphone personnel pour pouvoir le contacter.
Yes. Okay.
Je m'excuserai de vous demander ça, mais il devait faire il fait une conférence actuellement, mais il est complètement coupé. Alors,
D'accord. Est-ce que vous avez ce numéro-là? Donc, 06.
Alors, j'ai ce portable. J'ai essayé sur son portable et il est en messagerie. C'est ça le problème.
D'accord. Et sinon, j'ai son poste fixe.
Ben, je pense qu'il est chez lui.
Ah, ben, j'ai que ça. Ou sinon, est-ce que vous pouvez lui envoyer un mail? Ça sera peut-être plus simple, il pourra vous répondre.
Je vais essayer de lui envoyer un mail. Je vous remercie. Écoutez, excusez-moi de... Excusez-moi de vous avoir dérangé. Au revoir, madame.
La bonne adresse? Excusez-moi.
Je pense que j'ai la bonne adresse puisque je l'ai contacté il y a 2 jours.
Ah bah super, alors voilà, ça sera peut-être plus simple, du coup.
Merci. Au revoir, madame.
Bonne journée à vous.
À vous.
Au
Au
revoir.
revoir.
So, Marshall sir, any update? You could try to reach.
Hello. 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 Am I audible?
I think you have to come a little bit closer to the mic.
Okay.
Yeah, make it full screen and then you can start, I think.
Hello. So now it is okay.
You continue, I think.
So basically, I'm just a RUMP second half. These two are two different softwares. So before going for the software, so we'll have some 2-3 minute discussion regarding what it is planned for. Some echo. Hello.
This echo is coming from your side only. Maybe you are using the speaker.
Merci de laisser un message après le bip sonore. Une fois votre message enregistré, vous pouvez raccrocher ou taper dièse pour le modifier.
Alain, c'est Marcel. Essaye de me téléphoner. Merci.
Umapathy?
Allô?
Allô, je cherche à voir Alain CLAVERIE. Est-ce que je me trompe?
Oui, effectivement.
Ah bon, bah, vous m'excuserez.
Je
Merci.
vous en prie.
Au revoir, madame. Excusez-moi de vous avoir dérangé.
Je vous en prie.
Marshall, anything positive? Umapathy? Marshall, could you talk to him or no? Umapathy, you can start, I think. Your volume, audio is not coming. Saif, can you help Umapathy?
Sir, I am already with him, and we are
Okay.
trying to see what is the problem.
Okay. Thank you.
Hello, sir. Yeah.
Muted, okay? Muted.
Hello, sir.
Please speak from phone.
हेलो सर अभी आ रहा है आवाज
Now it is fine. I think you start presenting and start the demonstration.
Enregistre ta forme que le numéro demandé n'est pas attribué. Bonjour. Enregistre ta forme que le numéro demandé n'est pas attribué.
Can make full screen, Umapathy?
Hello. Sir, am I audible now?
Yeah, you are audible. Now you make a presentation. Make it full.
Okay, sir, I will continue with this.
Yes. But screen has not come yet.
Yes, yes. Fine. Sir, is it okay screen?
It's not full screen. You have to make it full screen.
Okay. Thank you, madam. Thank you, sir.
Yeah, not yet full screen.
Sir, basically, I'm not able to hear. So you can leave message here in the chat box.
Okay. The full screen is not seen.
Using mobile. But screen is
F5.
connected to PC.
F5 we can press.
Yes, sir. Good afternoon.
Yeah, make it full screen.
Yes, sir.
Okay.
I'm presenting through screen. So this is the demonstration and simulation for RUMP and SIMNRA. So is voice okay?
Voice is low. It is very low. Increase your audio is very bad.
And now?
Now, yeah, you continue. If any problem, I'll take. Yeah.
So you can look into the screen. Yes. So yesterday also I just discussed 4 concepts, that is kinematic factor, scattering cross section, energy loss, and energy loss. So these 4 mathematical formulas we need for this. So K is for your identification of the element, scattering cross section for your yield, that's your composition, energy loss, d by dx, that will give, and struggling also. So I will take an example how it is important here. So yesterday somebody asked how it is yield is related to count. So we have this yield formula. Generally, it is fed into the program. You can see, you can read. I have taken it from it.
Umapathy, your audio is slightly low. Can you talk a little bit louder?
Yes, sir.
Yeah.
Okay. Hello. Sir, now is it
now it's fine.
Clear?
You continue. If any problem, I'll tell you. Okay.
The yield we can get, that is normalized yield. What we see in the RUMP plot, it is normalized yield. How it is normalized is counts into correction divided by your charge into detector solid angle, then your delta E. Okay. So delta E is change in your yield. So this is the information that is there. Okay. So you can.
It's not the full screen again.
Yeah,
now it's full screen. Yeah. Okay.
So you can look into the internet. So I've shared some web page also. You can go on checking that one. This there. So and this is, it gives an yield that is absolute dependent on cross section. You can see here. So you can, I will show you how to get this thickness and where you get total integrated counts in atom per centimeter. Okay. So these 2 formulas and how it is fed. Okay. How do the software recognize that this information is already there? So when you open your RUMP front page, so you can see this. So it has atomic data fed, cross section data fed, and your stopping power, energy loss, and your density is also there. So it is basically relying on these 4 sub programs. So when you open any file, so you can see these are experimental parameters recorded during your experiment. So when you do RBS, we record with an software RC43. So we feed these values so that it is going to your file. Okay, you can see that helium beam, it is +1, geometry is general, theta is 7, energy is 2 MeV, date is also there, and conversion factor is there, that is energy per channel, and omega, this is your detector solid angle, and you have charge, and this complete swallow is for complete. Okay. So how to read your sample? This is more important. So which is first layer, which is second layer, what happens in case of your implantation sample. Okay. So let us go to the first example. This is silicon substrate. You can see here. There is a film BaTiO2. So we don't know the composition. How to read it? So this is my direction of incident helium beam. So it hits here, and it is energy backscattered helium are collected. So how it reflects is this. So these are coming from the surface, and these are from your. So information is this is the layer 1, and my layer 2 is silicon. That is substrate. That is very simple. Okay. So similar way. So I have taken one more example. So sometimes you may get confused implantation. Even the implantation does not make a thick film or thin film. It is a Gaussian distribution. So now you have to split your sample into multiple layers. So here, if you put some carbon implantation of some 100 MeV, so it will go and land somewhere here. So first region, if I don't say layer, I can say it as a region. So that will not be having the carbon. In the second region, it will be a carbon distribution. It will be Gaussian distribution, and third region will be the silicon. Suppose if you are doing in RUMP, you can directly give diffusion equation or implantation. If you are following SIMNRA, you don't have that option diffusion. You have to give roughness. That is, you have to make layer 2, region 2 as combination of carbon or nitrogen or with silicon. This example we can say. So more information you can see in this paper. So this one is 1986, very old, and this SIMNRA manual. So this is another key code is RBX code. So this is both for RBS, ARDA, and channeling. And you can see this paper also. This is on how accurate this your RUMP. And you can also refer this paper, International Atomic Energy Intercomparison of Ion Beam Nanoscale. So you can see all the names here. Doolittle name is not there. Nowadays Thompson is looking after it. His son. So here many Mayor is SIMNRA, Kota is there, SSSB is there. So they have different concepts. Beyond this, there are many other softwares. So you can also use them. So right now, I am familiar with this RUMP and SIMNRA for RBS analysis. So anybody having any doubt in starting this? So madam has mailed in previous mail attachment with the file.
Dear participants, are you following? Please write in the chat box so that he can continue. Okay, Umapathy, you can continue. So they have some of them are following. Yes. Who are not following, please raise your queries if you have any.
Okay, so let me take an example. So my data is somewhere saved in the desktop. That is, I have saved in the name of IBMS. Okay. So if you have installed it, so you can go search here. So you will find XRUMP, RRUMP. As such, there is nothing different. It is this you can directly open it. So XRUMP. So if you have opened it RUMP, so the only difference that you find, you don't have this option 2 degree. Okay, you can minimize this. You can still open XRUMP. That will be more easy. So since it is an demo, so it will save my time. Okay. let me back this screen.
Yeah, this is better if you go to maximize the screen size. Yes.
Yeah, this one laptop is small, but here it looks big. Okay. Now you have opened your main screen, so you can see the loading atomic data, declared data, that is your cross-section data, your energy loss, and atomic density. So you can see information. This is a RUMP RBS analysis simulation package, version 4, other information. Okay. So now I will take one or two examples. Maybe you can follow. So now how to find the folder. So this becomes very challenging for those who are not familiar with the programming or those who have not operated this. So if you have using RUMP, you have to type where is the file. So since I'm using XRUMP, so you can click here, file, click here. Now you can see change the directory. So click on it. Now you can see the option. So you have complete information. It is on the desktop. So here. So click on it. Yes, here it is. Fine. So now I have opened it. Let me repeat it. File. Change the directory. Now find the desktop. Here is the folder. So here. Okay, fine. So now you have selected your folder. To check where is your actually working, type LS. Fine. You can see this is user, admin, desktop, IBMS folder. You have these many files. So if you want to filter only RBS, so it has 1, 2, 3, 4, 5, 6 RBS files. The RUMP can only read .RBS. Okay. So let me take an example of first thing. Let us start with this 20 nanometer Ni crystalline .RBS. How to open a file is type XEQ. So these are based on commands. If you are familiar with the programming, you may easily recognize this. If you are not from programming background, it may be difficult. You have to remember this. These are somewhat different. XEQ is execute. Okay. Then you type your file name. So I will type 20. So I have to type all the things. For that, I will just press the tab. Okay. So it's showing there is another file with 20. Okay. XNRA file. I think your folder don't have XNRA, which is SIMNRA file. You again press it. Now I have it. If you are not able to use it to write properly, give the wherever apostrophe is there, wherever full stop is there, use it. Then press enter. Okay. So once you see follow, that is your file reading is completed. That your file is executed. So you can check this as this info. You type AC. This will give you all your experimental recorded parameters. So this part is over. How to read your file. Now how to plot. Now so you can write plot or PL. Okay. Or if you don't remember the command, you type question, this question mark, and you click it. You have all the commands inside your screen. Now you can select. So since I'm very much familiar, since I'm using from last 5-6 years, so I will go PL1. That is plot 1. Okay. Yeah. Now you will have a new window that is graph. Yeah, I will keep this side. This side. Fine. You can see here it is channel from 100 to 600 and 0 to 100. This is normalized. So we need to plot it proper. So you can see that this energy is somewhere 0.6, but we keep it. Check. So you have 0 to 2048 channels. I will set to set X region, right REC 0 to 2000. Okay. Then replot. Plot. Now you can see this is almost at 0. You will be having very high. So I'm interested to say from 500 to 2000. So these are 500 plot PL1. So why this PL1? So I have read only one. I have executed only one file. That is the main. That is active buffer. That is 1. Okay. That is PL plot 1 refers to this. If I have the next file when I execute 2, so you can open this or the next. Now, so this is somewhat okay. First thing what you need to do is turn on your R2 ID on, so that which reads your ID information. So this is the information. Here it is. Okay. So AUT4 ID on, so that you are not confused. Which file? So again, yeah, it reads the
Umapathy, can you bring your mic little bit closer? Your mic is a little bit far away. I think people are finding it difficult to get your voice properly.
Yes, sir. Now,
little more, one more try.
hello. Now I'm using mobile.
Yeah, it's better.
Okay.
Yeah.
So if you are okay with this line thickness, it is okay. Otherwise, you can LINEW line width 5. Okay, that will be, I think. Okay. So now you can see that is overlapping. So I need to increase this Y. So last command which I wrote region 500 to 200 for plotting in X. X is default. Now Y is not default. You need to write region Y 0 to. So I will write 7. Okay. So again, then plot 5. Okay. So this is okay. Up to here, you are able to follow. Somebody is able to follow?
Yes, sir.
Okay. So can I start simulation?
Sir, how to save this file, sir?
You want to save this file?
Yeah.
Okay. So I will take this how to save this file in the how to save this file in the end. So once you complete the simulation, I will tell you.
Okay.
So RS in a short quick, you click here. Okay. So this select, open your Word and paste it. RS click here, save as. It is an EMF file that you can open in a page.
Okay, sir. Thank you.
So let me start the simulation. So now you are only in the plotting window. So you can enter simulation by giving command sim. You can write simulation full, but sim itself is okay. So here you can see the many letters are in the caption and their number. You can write the full or you can write the short. For layer you can write LA. For simulation you can write sim complete. Or for next you can write any, and another one is profile. You can write profile, show SH is show. So I'm entered sim. Once you entered simulation, you can see that this is in the sim command. So this sample is I wrote in the information there in your previous text file. This sample is nickel deposited on silicon. My first layer is nickel. So I will give LA1. Okay, then I will write thickness. TH stands for thickness. Then I will give thickness, say I don't know now. Randomly I will give some 50 nanometers. Then you need composition. CO stands for composition. Then I will say nickel is, that is 100%. That is what? This complete. Then I will go to the. So this slash mark is for continuation. The next LA2 thickness. Now layer 2 is your silicon substrate. This is very thick, and 2 MeV helium can go up to 7 micron. So I will use 5 micron. You can give 5000 nanometers, or you can give 5 micron. Composition is silicon 1. Okay. This complete. You can check sim show simulation and flow. So what information you have fed is layer 1, that is nickel, layer 2 is. So now I will go compare both simulation as well as Excel. COMPA. Okay, compare. So now you see a red line and a black. Red line is your simulation and black is your Excel. Okay, now you can see many things. So what are the things generally we need to adjust or we need to modify? These are experimentally fed parameters, but so you can see that there is a difference. So this is the charge. You can see here is charge and E conversion, energy conversion. So energy is 2000 keV and number of channels is 2040. Energy per keV is your energy 2000 divided by 2040. That comes to 0.99. And this is FWHM. That is here it is 15. Standard it is 15. It is taking as a default. Now since our system is old and detector is also old, so we need to slightly increase. And this is detector solid angle as a 6 for 3.6 exposure. And theta is general. You have to change this. Fine. In case there is a mistake, sometimes we are running multiple energy, then data may be misspec. You need to check and fit. Okay. So you can see there is a lot of mismatch. First thing that you need to set is your ether. So first letter, this is your energy per channel. This is again offset. This you can increase or decrease. So depending on your surface area, which is on your surface. So E is 0.991. So I will not change this one. Second term. So now again I will compare this. Yes, this is somewhat very near. So I can increase. Okay. So compare. Fine. Now it is working. Second thing, so only this has to be done with respect to your surface element. First thing is you have to identify your surface element and then you have to don't randomly do it, so you will not be able to match. So still you can see this is not matched. Now you have to understand this is an energy dependent phenomenon. Only surface element calibration has to be done with the surface. So now, so when I always open in RUMP, there is some difference in your charge. So it is 8. Let me change the charge CH to 9. Yeah, it is good. So if you want, you can give further. Or it did not recognize. So if you don't give in a proper way, you will see this red colored unrecognized RUMP command. So you need to give it proper. So CS and now you compare. Now, so this I can recognize this thickness I have given is more. Now I need to fix. 1 thickness 40. Yes, it's okay. Fine. So you can see that these are not matching. Here it is not matching. This is because of your struggling. Again, you need to consider your FW, bad resolution. So FWHM was earlier it was 15. standard that is provided by the detector. Now I will keep between say 20 to 25. So I will keep it 25. Maximum you can use 25. Don't use beyond 25. You're going beyond 30 and 40. That is your detection very bad. Okay. Still, this is not matching. So what I will do is I will decrease further the layer. Layer 1 thickness. Yes. So you can recognize this. So you are outside the string. So it is not recognizing. Most of you, when you start in the beginning, you will face this. So you will not be able to understand why it is not recognized. Right string, enter. Now you are inside the string. Now you come. Right? Now you compare. Here it is. So this is okay. I need to increase the thickness. So what I will do is I will use 35. Again I will compare. Yes, it is matching. Huh? So you can cross check this. This is only one element in your film. So you can write return. Read is for return. CSI 6. Return 6. So this command will give you yield. Okay. Area under the curve, that is total number of backscattered helium count. That inversely will give you the atom per centimeter. Okay. Then you will have a cursor like this. You click in this region. You click in this region. Yeah. Now you type nickel because you are selected it for nickel. Yes, you can see it is 2.9 into 10 to the power of 17 atom per centimeter square. So when you have in atom per centimeter square, divide it by density. Then you will get that is 32. My simulation, it is coming somewhere around 35. So if I can further refine it, it will be around 30, 34. Your error will be less. So now you have simulated. Yeah. Okay. So you can see this is simulation. This is the file that is fed. So many students will be asking how to change this file. Okay. So you write buff. So buffer. So it will show how many files you have. Right now I have only executed only one. That is 1. Okay. So how to read is PL1. That is plot 1 or POINT at without space 1. So you can check. Yes, my directory star is in the main buffer. That is 1. Right? DES3. DES3 is for description. I'm writing in this short. Now you can change the file. So basically, you have 20 nanometers this time and written for LT and RT. Okay. Now I'll rewrite it. It's 30 nanometer nickel on silicon. Fine. So come. Yes, this is right. Okay. So if you want like this, it is okay. You want to change this one. This is the default file that has taken. Then you need to go point at 0. 0 is your simulation file. Temporary file emp.rbf. Point at 0. Enter DESP. That is your description. Now you can write simulation. Okay. Then compile. Let us make one mistake. So when you compile it, you see only a red file, that is your simulation. You don't have your experimental file. Now you have to go back to point 1, that is file 1. Okay. So then you default readable file is simulation. So if you are at point 0, only simulation file it will be. Okay. If you are at point 1, it will read your experimental as well as simulation. Okay. So this completes the simulation. Now you can look here how to save. Okay. So here is the window. Here, render to clipboard. Yes, click here. Open your any Word file. So I will continue in this one. Then paste. Here. Okay. So this is one way. Suppose here if you are using Ubuntu and it may be difficult to upload this file, you can select this one. So you will have EMF file. Okay. So you can save. So I will use this as simulation 1. You can save. Right. And more important is type AC and then in. So all 3 commands I am writing in the same. Okay. This will read your file name. This is your actual simulation parameters, which one you have changed, and this is the information that I have fed. So take your cursor, copy this. Okay. Just Control C, open your Word file, go below, then save. Control paste. Okay. This file you can save. So once you keep it saved, whenever you want to, you open and you can refer. So finally, your thickness of your film is 35 nanometer. Error will be there, of course. Okay. So you can see, you can furthermore refine it. So I'm not going to much deeper refining it. So you can reduce the thickness. You will have the best fit, or you can change this value. So you can, but don't randomly change this value. This first value, you can change this one. Nothing to do. Fine. So can I go to the next example?
Umapathy, again your voice gone down.
Yeah.
So
Okay.
just to see that mic, I think you were using the headset or what?
No, sir. I'm using mobile.
Huh? Mobile. Okay. Maybe little bit closer if it comes, it should be possible.
Okay.
And the someone wanted to know they are not able to open the data file in the chat box. Just to see whether you can, whatever you have done so far, can you just briefly outline to them?
Okay. So you can type this. So here are the list of all the commands right now I have used. Okay, you can take one screenshot. So I've used these many commands. So basically it is there beyond this. So what you can do is go here and you can copy all this. So these are recent few commands. I think these are not much commands, you can recognize this. Once you start with, you make a note in the paper, then you can. Okay. So I will move to the next sample. So analyzing it. Okay. I will type LS to filter out. So these are, yeah, screen is not much clear, but I think letters are limited.
Maybe you can maximize the screen, the corner, yes.
But I can maximize letter size.
Okay, now it's better, I think.
It's okay.
Now it is bigger than previous one. Okay.
So now I will take next example. Okay. And I'm going for AU1 glass total length. Okay. So I have also wrote, so what is the combination of your total length? So now X, E, Q, A, then just press it up, you will get it. So you can read these parameters. It is measured at 2 MeV helium plus, and your FWM is here it is default, it will be 50. Conversion, energy conversion is here 1.00456. So from A to D you get energy conversion is you have an MCA, have an electronic field that is 2048 channels. So each of these channels corresponds to 1, and this channel number of channels remains same, but you can increase the energy, that will be redistributed. Suppose you are doing 2 MeV, the channel numbers will be same. If you are doing a 4 MeV, channel numbers will be same. Energy per channel will be different. So now let us go to the next example. So you can see in the background once I plot it. Still I'm using PL1. Earlier also I used PL1. So let me check first. So now I have executed two files. One is your 20 nanometer Ni pristine, and second one is your 6.1 RB. That is, inside I did not say that still it is reading A1. Okay. Fine. Now the star is here. Here it is. Okay. This is one. PL1 refers to your A1 class. PL2 refers to your 20 nanometer. So suppose if I cross check it, yeah. Okay. So if you want to both PL1 over 2, OV stands for over. You have both in one. Okay. So when you want to compare multiple sample data, you can. Now I will go to PL1. So since if you want to use the new screen, you can use this. Since I'm familiar, I'm continuing with this. So let me check what are the information I have already fed in the previous simulation. Okay. Then we'll go to the simulation. Show is again, it will show what is there in the simulation. Now you have fed the previous 35 nanometer nickel and second layer is the nickel. So now the sample is totally different. Now I need to change LA1. So thickness I will keep the same. I will change the composition. So let me give thickness also. Thickness 50 nanometer. Composition. Now I will give AU. But there is already nickel. So we need to delete that one. So I will take to the next time. Enter. So it is complete. Now your goal is fed. Now so again LA1 composition nickel 0. Okay. Then yes, you have removed your nickel. LA2 is not silicon. Now you need to give composition of soda lead. Okay. So I remember the composition. I will directly pick it. Okay. LA2 thickness 5 micron. Composition silicon 0.25. Oxygen 0.6. Na 0.1. Ca 0.03. M 0.01. Al 0.0. You can remember if you can open in your shrimp and you can get this information in compound directly. So this is total and class. Common information is there. Now, so what information I have fed is AU, and second it has 6 elements: silicon, oxygen, Na, Ca, Mg, Cl. Yes. So many factors it has considered. So now you can see somewhat not fitted. So it looks that layer 1 may not be 15 nanometer. It can be less than 15. L1 thickness comes 10 nanometer. Yes, you are inside the same. Then it is fine. Okay. So this is the substrate. So always try to match your charge with your substrate. So don't match with your film or your whatever other elements are there. Try to always match charge. Okay. Here it is 8, maybe 1 more. CS9. Yes. So you can give S9. Fine. Exactly matching here. You can see this is not matching to some bad resolution. Okay. Yes, WSM. I think this is the class. Fine. So this is still not matching and this is okay. So this scale I need to increase reason y 0 to so I will decrease thickness of the layer L1 thickness 5. So here it became 50. Okay, you can check. So I need to decrease 5. So bad resolution. So you can integrate the role of 25. And so yeah, match. If you want to increase here, region region. So you need to specify 550,000. This is X region Y 0. Yeah, it is. Now I did not mention here, so it is reading from 500 to 200. Region 500 to 2000. So don't feel bad in between if you are stuck not able to process properly. So now I have told you how to change this file name. So I will not tell this. Now I will continue. Saving, I will again repeat it. Click here, render to the clipboard, click, then open a Word file, go here, control C, paste. Okay. So information you can take ASP in 2. Fine. You can copy this to your mouse. Control C, copy. Okay. Go to new page. This information you will read. So you can cross check. Let's see. Fine. Point 8, I'm doing some error and I did not fit it well here also. So it depends on your resolution. Always the best result that you can get is best resolution. So is it okay up to second sample? Okay. So I will take the third example. CD CiO2 with RPA. XEQ, that is to open a file. CD, you can write to, I will put a tab. Yes. This rate, follow, read, reverse, complete information. So since I have used it, I need not to plot. If you set 500 to 2000 ideas, if you want to open a new screen, again you have to follow from the beginning. Now, close. So here it is AU, but this may not be all this. What I will do is I will clear this and open a new tab. I will. Okay. So because you have these elements, you need to remove these elements. So you will be confused in between when you type composition and thickness. Sometimes if you don't give it properly, so this will consider as an element. Your TH became your thulium and your CO becomes cobalt, and you need to remove them. This will is a common error. So shall I continue with this simulation or should I open new window? Okay, so I will continue with this. Then show. Okay. So first I will plot it. Layer 1. So layer 1. So this information I know, this is PDTiO2. Oxygen may not be exactly 2. So we have to check. So LA1 composition thickness, I will keep it some 50. And composition, I will give PD1, PD followed by space. Each command is followed by space 1 and oxygen 2. So I am randomly given, I don't know. Later I can cross. Okay. Yeah, it's not inside the thing. Enter. Okay. Now it's check. You have previous goal here. Remove LA1 composition AU 0. Okay. LA2 is not soda lime glass, which is silicon. So I need to remove other elements. 0, oxygen 0, CA 0, AL 0, MC 0, MA 0. There's still I did not remove LA 2. So I think I did not give proper command. It was still in the layer 1. I was trying to remove these elements from the layer 1 and they are not there. So you need to specify you remove from the layer. Okay. So let us I have removed all the other elements. Now I have removed oxygen from layer 1 also. Let me add a portion oxygen. Okay, fine. So as I described in the previous, you need to check all this charge. This charge should be from your substrate, not from your film. This is 10. This may be different for different. Sometimes we keep it 12. Sometimes I use it 8. Sometimes we keep 15 for carbon substrate or silicon carbide. I keep it 15. Okay. So this is thumb rule for this one is your substrate count should be 1000. So that's how it reduces your statistical performance. So you can see here normalized is if you want to go for count, you can write RAW. Fine. You can see now it is count. Reason 02. Reason is Y02. If somebody wishes you want to continue in count, you can continue. In normalized field, you write normalized. Here in normalized 02. I did not do. Okay. Reason I am writing. Yeah, done. Reason I am 2%. So reason why 0. So these all red color is unrecognized command. So that means it is warning you this is illegal implementation, so you can just take it. Right? So now so you can see that this surface is exactly matching or not. So earlier all the samples. So in general the data that I provide are from our lab, it will be calibrated except in few cases there may be slight variation in your calibration because when you are running for continuously 3-4 days, your energy may be changed, we may tune in between, or your offset may change. So yeah, fine. So I can continue. So I will increase layer 1 thickness, say 150. See, I have done this simulation. So I remember I am doing it. You can change slowly. Fine. So you can see here, this is not matching, this is not matching. This. Let me take charge. Here it is 10. Yeah. Okay, FWSM 25. So don't go beyond 28. That means now you can see that you can also check what is this element, provided it is taking information for your tool. So you want to check for 3 MeV, feed it 3 MeV or insert EL, the type element, what element you want, TI. So this is your TI, EL, PD. This is your oxygen, EL, O. EL, silicon, yes. Okay. So you know that which is not matching here and which is matching. So go to now you have I have given PD and TI in equal composition. I need to change. So PD has to decrease and your TI has to. So I will keep PD constant and T. So let me type properly. LA1 composition. PD I am keeping constant. TI, so I will keep it 2. With respect to 2, when it is 3, oxygen will be 4. TI would, that means oxygen also will change to 4. Okay. Somewhat good. So you can see this reason oxygen. So oxygen having less mass, that your backscattering will be less, and this reason it becomes not much sensitive. Here you can see that there is a difference. This is matching, that is thickness that you are given is matching, only composition just matching. So LA1 0, I am just reducing oxygen from 4 to 3. Then it is an oxygen deficient now. Still, if you want to further refine it, you can see here it's exactly not matching. You can expand EXP, or you can plot region say 500 to 2000. Okay. 2500. Okay. Let's see how good it is matching. Yes, it is not matching. So let me refine it properly. ECONV 0 point. This is only for the surface. You cannot do it for the silicon because it is in the second layer. The incident energy for silicon is different. Okay. Incident energy for your surface element, that is for your PD is different. 979. I will keep it same. So I will increase it. 5. 5. 100. LA1 thickness. So I have given 150. I will get 140 nanometers. I need to further reduce. Okay. So this fits. Reduce 5 more nanometers. So you have a best match. Okay. Other information. So one more thing.
Hello, Umapathy, Indra here. आपका अभी कितना? How much time is left?
How much time I have left?
You tell that how much you want to discuss more. How many files?
Other speaker has come. He has come already. Alan has come.
So later.
In 10 minutes you can complete. Umapathy?
Yes, sir. Yes, sir.
Okay. Okay.
So this is okay. So I will continue with SIMNRA. I'm using SIMNRA 6 in this version. So most of you might have using SIMNRA 7. So this is simple. This is not much difficult. You don't have to remember anything or command. Okay. So when you open it, you see. Okay. You can read file, edit, setup, target, reaction, calculate, tools, plot, option. So how to open this file? I will take fast. You have to remember. By opening it, this same as your original, you can open it, but it is spread with your good data. Okay. So this version is 6.2, older version. Right now, which you have downloaded is 7.2. That is advanced version. Fine. So you can see read spectrum. As now you need to specify to your folder. Yeah, data file, text file. Okay. So I will take the same example of the first one. Okay. So this is 5 more. You can expand it here. You have an option plot. You can unzoom. You can plot X. You can plot Y. You can auto scaling your system. Okay. So file is okay. If you want to save, you can save as. This is save NRA file. So if you want to copy, edit, you can copy data also. You can plot in origin. You can copy page. Copy page. Okay. This is copy this page. So when you plot, paste it, you can see fine. So next. So these two are important. So setup and target. Setup is your experimental setup. Click on this button, you will open. So now it is default fed with 2 NVV. So incident angle is 0. That you can keep as it is. It is 14 degree or 165. So okay, the total will be 180. Calibration offset earlier used 80. That is 30. Okay. So it will be slightly different from RUMP, not much 5. Okay. So you can keep 1 or 0.99. This is your particles in the charge. So how to know this? Calculate. You have a particle calculator. So how much you have said, that is helium collected is 10. You can click here. Okay. So I'm not changing. I'm saying defaultly feeding because I have less time. 25. This is okay. Fine. Now you click reaction. So there are 2 shortcuts here. Target is this one. You click target also, it will be same. Okay. Sorry. Setup. So setup, here it is, and the short form is here. The next one is target. You can click here or you can click here. You will have. So now you need to define your layer. This is layer 1. That is, you have to give thickness in atom per centimeter square. Okay. So now I don't know. I will give some random. Okay. 500. Then you have to define it. Number of elements is 1. So you will see that is the box. Thus you can give layer 1 is equal and this concentration is 100%. Then add next layer, layer 2. Okay. If you add elements, you can add here. Since my example has only 1 element, I will do this one. Okay. So next layer. So this is substrate. So that will be very thick. I will give this element 1. This is 100. If you don't click properly, it shows red color and it's right. Yes. Fine. Okay. So reaction and then you have to connect. Okay. You have a shortcut here. Use the first one. Second, third will have more error because it automatically starts simulating on its own. You try to fix on its own, you will have more error. Okay. So click this calculate first. Calculate spectrum or the first. When you click it, then you have cross section done. It is selected. Number of elements is 2. Okay, that is this is for your silicon. Next section will be your nickel. So this is selected. You have Rutherford and non-Rutherford. If you are using version 7, you will have sigma calculator, non-sigma. So Rutherford, it is default. I am not disturbing. Fine. So this is basically your charge. So where is this charge? Click here. Minimize. Okay. Again here. decrease this level. So you can do it in a single screen now. You can calculate charge and put. You don't know, you can randomly. And once you 1 or 2 times you do it, so this will be a point. You can use lesser than this. So your substrate charge is matching, but this is not matching. This is because you have given your input layer 1 as 4. So click again target, have this shortcut, go to layer 2, then layer 1 and 4. You can just side combine. This is more 300. I will reduce further. 5. If it increase, there may be some offsiding. One. So that is the so it's not exactly matching because it may be having some surface oxygen which is not seen. Or else you can decrease the resolution. So now this file as it is you can save and reopen. You need not to go for copying. Okay. You can cross this, you can cross this, you can file, save as RNA. Whenever you want, you can open. So trial 1. So if you want to copy this, you put this information. Again, you want to convert this into nanometers, so you are into nanometers. Click here and there. So this is layer 1 target aerial density. So this is the information. Go here, click, calculate density. So what is this? This is nickel. So in case of nickel, type nickel, it will give you nickel information. See, 1 E15 atom per centimeter is equal to 0.1095 nanometer. So you have 280 into 10 to the power 15 atom per centimeter. Multiply with this term, you will get that, and it will be very close to your information. So can I take next example very fast? Yeah, I think yes. So I will use this. I will open a new file. File, read ASCII file. Yes, you have SIMNRA data. Open it. You can read text file. Okay. So the folder that I have sent you is so this one. So when you open it, you find .txt file. TXT file. You can see here. TXT file, TXT file, TXT file, TXT file, TXT. Open it. File, read, ASCII. So open here, text. So I will take. So this is different energy. So I have taken this example. I will. Okay. So since I have not considered in RUMP, this is calibration sample. This is industrial standard sample. So it has to like this. So I know this is the standard sample. This is a tungsten silicide. It is had tungsten and silicon on the surface. Then you have a buffer layer of SiO2. Then film. So let me see this fast. I'm not disturbing here. Only it. So then go to target. Layer 1. It has unknown thickness. That is the starting is 3000. It has number of elements 2. So 1 is tungsten. So let me see, say 6 tungsten 3. Add the next layer, which is again 2000. I don't know right now, but you can do it. This is buffer layer and solution. will be 6. So it is total 100%. When you consider concentration, it will be 1. If you click on this, so rest of will be 100%. The next layer, layer 3, that is silicon, that I can give very thick, I have given 50,000. One that is silicon, that is 100%. So let me compare it fast. Yeah. So this is of a Rutherford cross section, all Rutherford cross section. So when you are going for resonance reaction, you have to select very particular. So now your charge is very high. Come here, 8, 6, 7, 1. Yeah, some more. Okay. So now you need to match this. This is your silicon substrate. This is your buffer silicon. This is your silicon. So if you understand the theory, you will be easily able to recognize which is from your substrate, which is from your buffer layer, which is from the silicon. So I will increase to 2. More, I can keep 1. So there is a huge offset. It can be used in different conditional seconds that are randomly. So now I did not put any offset value. Yes, they match 7. Yes, 1. Yes. Now your layer 1, this is layer 2. Let us start finishing from or completing from your layer 1. Layer 1. So tungsten I have given 3, 4, it is 4. So let me reduce it to 3 and silicon 0.7. Let it compare. Yeah, it's somewhat very near. So I can go to 2, 5 and this is 7, 5. You can blend. Composition. So if you have okay, so I did not make it 100%. Yeah.
Umapathy?
Yes, sir.
Maybe I think you can wind up because he is waiting for quite some time.
Okay.
Yeah, okay. You can summarize it and close.
Okay.
Yeah.
So now you can do only one correction I would like to add is when you calculate a compound, you need to calculate density. So click here, go to density, and when you have two elements, you get this tungsten as well as silicon. So you will get this. These many atoms is equal to this nanometer for tungsten. Again, you add with the silicon. That will be. In case of only problem that you face is with case of optics. So this will be. Now you need to change this density 1.10, 1.104. Use this. Okay. So use this result, you will be able to. So you will get exactly the thickness as that you have your SIMNRA directly nano. So I can close this. I think it's recorded. You can get this recording later. And I will make some short videos.
Thank you, Umapathy. And maybe you can share your, we have already shared your email to all the participants. So if anyone has some clarification or doubt, they can contact you directly. I think now we can proceed for the next talk. This whatever first talk which is disturbed. Now we can try the talk.
Okay, this is Alain speaking. Is it my time?
Yes, you may start, please.
Okay. Okay. Do you see my slides?
Kavira, are you going to introduce him?
He's already done. He's
Okay.
in the middle of the.
I will. Question is that do you see the first slide there?
Yes. Yes, it is visible.
Okay.
It's okay. We can start.
Okay. first of all, I want to apologize because I'm very sorry. I was cut. There was some windstorm, small one, but enough to have a shutdown of power. So telephone, internet, everything. So I deeply apologize. By the way, I don't know exactly where I was cut. I assume that you remember. Probably you have seen this slide. Is someone able to answer?
Yes, sir. Yes, sir.
Did you see also this one?
Yes.
And so I think I was somewhere here, right?
Yes, you just started this one. You can proceed.
Okay, thank you very much. I needed to get the overview. So what I was saying is that it is about the fabrication of SOI wafers, and this is mostly done using hydrogen ion implantation. And what I was trying to say is that I know that this community is very much on irradiation, but here we are talking about implantation. That means that what is of importance is where the ions stop in the matter. And if you take a few tens keV hydrogen implantation here, it's 40 keV. I mean, what you see is that with this implant, you are able to localize very precisely in the depth of the material the hydrogen concentration. And because in this regime, the hydrogen implantation is somehow light ion implantation. Light means in reference to the naming used by Linda Schaff-Schayot. That means it's mostly ionization processes along the track, and the damage is produced just in the end, just before the ions come to stop. That is when the nuclear interaction are favored. Okay, so what I mean here is that it's highly localized, and you have very little damage in the first pass of the profile. Okay, and okay, I don't know what I have this stuff here. Okay, let me get rid of that. Okay, now what if you implant a few hydrogen at some high dose into silicon, and then you make some annealing afterward? What you have is just what we've seen before. Again, let's see. You very oxide layer. I implanted through the oxide. I'm getting the implanted hydrogen. Then during annealing, what I see, I have some stuff there doing some kind of bubbles. We'll talk about that. And in the end, what you see the deformation at the surface. In real, this is the same image of the surface. This is a very well-known phenomenon, blistering due to proton implantation. And so this was known by the nuclear community as a drawback of proton irradiation. And what we have to keep in mind is that we have this blistering because it is due to stress selection, due to something pushing up on the surface. Okay, but now the idea is that if you try to prevent this surface deformation, you put on top a rigid stiffener. That is, either you have something, you make a deposit, or you make some bonding on the surface. Then, and this is what I'm showing, but this time the wafer was split. Okay, rotated. Let's see again. Implanted is on top here. It was implanted and then bond. And then, because of this stiffener here, I mean, you cannot have any deformation of the surface. And instead, what you have some fracture propagating along at the depth or where the hydrogen was implanted. And so this thing is just split, and you are left with a structure which is made of silicon, oxide, and silicon, which is, apart from the roughness, is a SOI material that you want. So the effect of the stiffener is to prevent the out-of-plane deformation. You don't have any surface relaxation, and now the material makes some fracture by the propagation of microcracks, and we'll be discussing about that. And actually, this is what you can get if you make some deep implant or you have a stiffener. You will see that, I mean, actually, you have some exfoliation locally, okay? And so this is the depth where the hydrogen was implanted and the material was lifted off. And so if you are clever enough, you can use this phenomenon to fracture the whole wafer. Okay, so this is a working principle of the smart cut process, and this is used actually by to transfer silicon. I will be talking about that mostly today, but also silicon germanium, gallium arsenide, indium phosphide, gallium nitride, metals, niobates. Actually, this idea was patented by Michel Bruel, a French scientist. And the funny thing is that this guy has been working for 15 years in nuclear material, and he knew about this blistering, and he joined a SOI group at CEA and made the link and say, okay, what was a problem with nuclear material might be a solution for semiconducting materials. And finally, this patent was taken by, at the time, a small company, Soitec, who grew a lot the last years, and is now providing the industry with this SOI wafer. I would like to add that actually India is kind of active in the science behind the smart cut process, and not to give all names, I would just say cite Professor Rajendra Singh at IIT Delhi, who got first experience when he was with Professor Geselle in Germany, and now is developing this smart cut on the exotic semiconductor like indium phosphide, gallium, indium arsenide, these sort of things. Okay, so that's the process now. How it is done is that you take two wafers, okay, you oxidize, or at least one, you may oxidize both, then you implant one through some thin oxide, and then you have the implanted region there. Then you flip over this sample, and you take this one, then the wafer, you bond them on top of each other. Then you do some annealing, and during this annealing, you fracture the layer here, and so you are left with the top material here, okay? And you have this SOI structure. And the good point is that the material that you have sliced here, you can even send it again to be sliced again, okay? You can recycle it, okay? And every time you just input one handle wafer, which will be just there for mechanical reasons, okay? So it can be used to transfer silicon, but it can use also to transfer materials which are, say, for example, impossible to grow by epitaxy. So there are three key steps in this process. The first one is ion implantation. The second is wafer bonding here. And after wafer bonding, you have this annealing, and this annealing is will focus on that. Is something is happening during annealing which make these bubbles, and ultimately which will fracture the material. And there are main different advantages of this process is that actually the silicon region on the top layer is almost defect-free, because there are not too much ion implantation damage in there. It's mostly ionization. And so you can also adjust the thickness of the transfer layer just using, by playing with the ion beam energy. And it's, of course, an industrial process. That means that, okay, you can do that at the laboratory level. That's a good news, because if you have a small clean room, you can do that in the lab. But also it's an industrial process. That means that you can have high throughput. For example, in some places in Soitec, they may have 6, 10, 12 ion implanter working in parallel and producing hundreds or thousands of wafers per day. And the last point, it's totally generic, that okay, main business today is on SOI, which is silicon wafers, but you can use this process to transfer expensive or exotic materials. For example, at the time today, focusing on piezoelectric materials. Okay. So my proposal is to take you through some trip. We'll look at defects as implanted wafers, strain in these wafers, what's going on during annealing, what about the strain evolution, the complexes, different extended defects that we can see, and we'll see how they evolve, how we go from platelet to micro cracks, this and that, and we try to build up a possible scenario to understand how we go from point defect to the fraction. Do you see everything well, and can you hear me well?
Yes, everything is fine, please.
Okay, so we go on. Okay, so we make this ion implantation, this proton implantation, and now we are looking before annealing of what kind of defect we have. But the good thing about silicon is that we know silicon since a long time, so we have plenty of data, and this helps a lot. So if you look at the sample by looking at the point defect or complexes, you have two main techniques. One is Fourier transform infrared spectroscopy, another one is Raman. And in both cases, you will get kind of complicated spectra with different signatures. These are the signatures of different complexes, which are well known in silicon. This is not the case in other materials. And to make it simple, I would say that on the left, most of these defects are vacancy hydrogen complexes. This is something which is very important, is that hydrogen loves vacancies. And when you make an implantation and where you have interstitial vacancies and hydrogen, the very first thing is that hydrogen is very mobile, even at room temperature, and that is literally jumps onto every available vacancy. And in the end, you are left with complexes which can be vacancy rich. That is, you have 2 or 3 vacancies and 1 or 2 hydrogen atoms, or on the right side, which are hydrogen rich. That means basically you have 1, 2, 3 vacancies, and you have more hydrogen than vacancies in these complexes. And basically you see almost the same kind of thing by Raman and infrared. And what is important is then you see that the main complexes are something like VH4, VH2, that is kind of hydrogen-rich complexes. Okay. If you look at strain, actually, this is a cross-section TEM image of that. So you see that was a surface you implanted there, and you have a damaged layer here where the hydrogen was implanted. And if you look, I will not detail, but these are strain images which are obtained by holography. And what you see here on the right is the in-plane strain. And you see that there is no strain. But if you look at the out-of-plane strain, you see that it's red. That means it's a lot of out-of-plane strain. So, I mean, the crystal looks very much like a pseudomorphic layer, okay, where you see that everything in plane is okay, but the material relaxes by straining of the lattices of the planes, depending on the fact that you have hydrogen or not. You can link these things, and you can demonstrate either by taking the X-ray or by plotting the strain profile that you are getting through this holographic TEM image. What you will get is mostly the same result, is that the vertical strain profile that you are getting is actually the same, or it mimics the hydrogen distribution. So this is clearly, you see the strain where the hydrogen stands. Okay, you can even simulate this thing by putting in your crystals some small subnanometric pressurized defects, and they deform individually. And the crystal, if you put a population of them, you are able to reproduce what you observe. Okay. Now, which are the defects which are important, and in which concentration they are? Actually, if you look at this table here, you will see that you have many candidates, okay? And it's more or less what we see in the Raman or infrared spectra. And this was done by ab initio calculation to the idea was to calculate the energy which was gained by forming these different defects. So when it is strongly negative, that means that it's very favorable. And of course, you see that the most favorable thing is to, of course, to recombine your interstitial and vacancy. But once this is said, you see that forming some classical defects are not so favorable, while if you see at these complexes, V2H2, VH4, V2H6, they are extremely favorable. That means that the system loves to form complexes with few few vacancies and several hydrogen atoms. Okay, so from that was an idea developed by Cherkashin, was to take advantage of the XRD spectra and the SIMS profile, and the fact that you could calculate also the quantum of deformation that could be brought by each of these complexes. Okay, because you know, for example, you can calculate the V2H6 complex deform locally the crystal by this amount, and putting all these things, experimental and theoretical, together, you can deduce actually what are the concentrations of the complexes that you are forming, depending on the hydrogen concentration that you have in your material. That is as a function of the dose, but also as a function of the depth position. And here I want to make a point that when you make a soup where you put together hydrogen, vacancy, and hydrogen, you form complexes. But for example, if you fabricate for some concentration here this amount of concentration of V2H6 complexes, if you double the dose, do not double the concentration of these complexes. It is not linear. Okay. On the contrary, you can see that depending on the concentration, on the beginning, you see that you can form some complexes, but if you increase the concentration of hydrogen, these complexes are no more favorable, and instead you have some complexes which likes to be formed when the concentration of hydrogen is important. And also you see that one complex is actually not complex. It's the single interstitial hydrogen remains in concentration, remains constant. Okay, so what we learned from that is that after implantation, hydrogen, interstitial, and vacancies, they recombine together at room temperature, and they form hydrogen-rich complexes like V2H2, VH3, VH2, and this and that. There is one stable body-centered interstitial, and also what you see is that you have the increase of the concentration of certain of these complexes during annealing. And interestingly, you see that there is one guy, the V2H6, which has a superlinear increase with concentration. Okay, that's a red one here. And you see, and we already can infer that this one is a very important, is a VIP, and is probably responsible for the observed deformation. Okay, now, actually, that was as implanted. Now we look at after annealing. So I'd say moderate annealing. That is typically you do something at between 300 and 400 degrees. But you have the strain here in red. And if you look at your strain after annealing, and you see that it's getting localized, it's no more homogeneous, it's getting heterogeneous. You suspect that you have defect there because you have discrete deformation fields. Okay. And yes, you have objects. If you look at that by TEM, you will find these sort of objects here that you can see. They appear very small here, okay? And we name that platelets. Actually, you see them here in cross-section, so they appear like a straight line, but in reality, they are disc-like defect, two-dimensional object, like a plate, okay? In high resolution, you see something which is kind of amorphous and light inside here in comparison with the material outside. And okay, we are good at crystallography, so we realize that we have two families of defects, some were lying on 111, some lying on 001. So putting crystallography there, you understand that you may have up to 7 variants of this defect. Okay. Now, where do they come from, these defects? Actually, if you look at what's going on during annealing, actually, this is the infrared spectra or the Raman spectra that you were getting before annealing, but the one that you are getting after annealing. And you see two main things. One is that actually you go from the left to the right. And to make it simple, initially you had many vacancy-rich complexes. And during annealing, you tend to go into hydrogen-rich vacancies with very strong signatures of VH3 and VH4, and also you can note the overall decrease of the signal of the integral, and this is mostly because we are losing the signal due to the bonding of silicon with hydrogen and probably the formation of H2, which we can confirm because that's much higher for much higher wave number. You can, for long annealing, for example, you get this red peak here, and which is typical of the free hydrogen gas. Okay, and for short annealing, you see that this peak shift and gives such a peak here, which is ascribed to hydrogen gas, but in a complex environment. And you can see that putting together FTR or Raman result, you can see also the same thing, but here you have multi-vacancies. Here you have, on the right, you have hydrogen-rich, and you will see that from as implanted to anneal, you switch from many vacancies to many hydrogen. So initially, you had mostly multi-vacancies and mono-vacancy complexes. In annealing, what you see that you decrease the vacancy-rich. You have much less of this SEH111, and you have alternatively, you have an increase of hydrogen-rich, and you make also SEH2, which is a signature of internal surfaces. It is what you obtain when you cut or where you make SE100 surfaces, and then you passivate them by hydrogen. And we also note the formation of H2. So for this reason, we now understand what are the platelets that we are forming. The platelets, it has to be, and this is something important in ion implantation in general, is that very often the people, they talk about precipitation, impurity precipitation, but most often it's co-precipitation. It's that you need the co-precipitation along with vacancies. Because for forming these platelets, like many precipitates, okay, first thing is that you need the vacancies to make room. Or I would say here we need different things. You need the ECH2 to debond the plane, that is to separate the layer from the neighbors. And then you have the vacancies to make room. And now you stuff your defect with H2, which will make the pressure inside. So you may have this presentation here of platelet here on 100 or on 111. So important message that probably I will give another time is that like many defects, many extended defects, there is no, you should not think about the nucleation. Nucleation, I mean, it is not something which happened that suddenly a platelet appear, but instead it's probably an evolution path where we, from hydrogen-rich complexes, we tend to form platelet by adding more vacancies and more hydrogen to these defect complexes until they become visible by TM, where we name that platelets. So it's a bit like different defects in silicon, of which I will probably talk later on. Okay, another thing also to insist that it's a precipitation phenomena is that this is a typical SIMS profile. And so in black, you see the hydrogen profile before implantation and the SIM profile that you have after annealing. And there are always always many comments on this sort of themes when people say, oh, it's going against a fixed law, for example, yeah, because I mean, you would expect that diffusion generate or smooth the gradient, and you see that actually it is not the case. That is, this does not obey to the fixed law, but it's typical of precipitation because I mean fixed law apply to mobile spaces, and in this case we have here what we have a precipitate phase, and this precipitate phase tends to pump the hydrogen, okay, to cluster it, and this is the reason why you see that I mean the profile is getting sharper, what is a signature of a precipitation phenomenon and not about diffusion. Okay, so it is not, as you, contrary to what you could read, it's not something about uphill diffusion or whatever. And also another comment why you see this thing diminishing is decreasing. It's not because we lost or because there was some exhaustive diffusion of at the surface, because again the gradient would be different. But it is just because we're making hydrogen gas, and SIMS is not good at all to measure the concentration of hydrogen when you make puffs of hydrogen, because when you come to analyze this region, I mean, you open the platelets and suddenly the gas goes out into the vacuum chamber, and what is in the end difficult to analyze. So this is a classical SIMS showing a precipitation phenomena, the co-precipitation of hydrogen and vacancies. Okay, so what about these platelets? During annealing, actually what you see is that on the beginning, as some given temperature as a function of time, you see they are small in the beginning and they tend to increase in size, and until they appear kind of big, you see them. This is nice. You see we are very close to the fracture here. You see the different platelets, they tend to align. Of course, we are close to the projected range of the hydrogen there. And the interesting thing is that, okay, they increase in size, okay, as you see here. But if you make a good analysis on plan view sample, you will also measure the density, and you will show that the density decreases, okay? And now if you look at the total volume, which is occupied by the platelets, okay, that is the surface they occupy by surface unit, you will find that this is constant, more or less constant, okay? So it increases in size, reduces in density, but the volume fraction or surface fraction remains constant. And this is really like it's the signature again of the Oswald ripening, okay? So what is Oswald ripening? And I will spend 1 or 2 minutes to talk about that because it's very, very classical in ion implantation, that when you implant some impurity, you get precipitates, then you anneal and you see this precipitate growing. And so there are many, many things which are said that they are coalescing or whatever. In general, they do not coalesce because coalescence requires the motion of precipitate, what is energetically quite difficult to obtain, require lots of energy, while for less amount of energy, you will activate another phenomenon, which we will be talking about now. When you have a precipitate, everything is based on the analogy between a precipitate and a droplet of water. Okay, so when you have a precipitate, sorry, it goes too fast. When you have a precipitate, the Gibbs-Thomson equation tells you that any precipitate, like in a water droplet, is in dynamical equilibrium with a supersaturation of the same species, making the precipitate, but distributed in a matrix around. For a water droplet, this is named vapor, but in a solid, it's a supersaturation. That is, you have impurities in concentration larger than the equilibrium, the solid solubility limit, okay? And of course, if the binding energy or the formation energy is larger or the binding energy is smaller, that means, I mean, you increase this equilibrium supersaturation. In other words, for a water droplet, I mean, this formation energy is given by the curvature of so when they are small, you have a huge supersaturation. When they are large, you have a smaller supersaturation. So now you see the system, okay? And now you have the Fick's law, which tell you that the nature doesn't like this gradient and will do its best to reduce it. And so for this reason, we will have a flux of matter from the high supersaturation region to the low supersaturation region. And this will drive the growth of the precipitate, okay? So have a look here. We have a small precipitate, okay? This is a gradient saturation here. You have a large precipitate here. Okay. And because you have a population, you have a mean field in the middle. And so actually what is going on is that the small one is not talking to the large one, but the small one is talking to the mean field, and the large one is talking by the mean to the mean field. And so this is how it will work. But you will have emission from the small, you will have capture from the big. And in the end, your whole system will evolve. Okay? So now if you take the formalism, mathematical formalism of the reservoir ripening, you will expect that the growth flow will be such that that actually it's the square of the or the square of the radius of your precipitate that we evolve as a function of linear function of time, while actually the density will evolve as a function of the inverse of this time. Well, what you can check readily by looking at the evolution of the size and density of the platelets during annealing. So this is Oswald ripening. Now the good news is that okay, we know a couple of things with Oswald ripening, and we'd like to model that. If you want to model actually what that situation, you make an analogy. You can say, okay, we know dislocation of these platelets more or less are like dislocation loops, because in interstitial vacancy dislocation loop, in principle, you have this negative deformation, negative strain here, and an interstitial dislocation loop, of course, is a contrary. And so these platelets, because of gas pressure, they exert some pressure onto the crystal, and so it's quite similar to what is done by. It's quite similar to the result of dislocation loops. And for the reason we make some analogy, and we say that a platelet is somehow like a dislocation loop. The only thing that is missing is that we need to get this Berger vector. And actually we can get that by making TM simulation and deducing that, or measuring it directly, again, by measuring the strain field around of the platelets. This was done by holography. And you can get the effective Berger's vectors, and it tells you something which is very interesting, that you can deduce from this Berger vector, you can deduce the actual hydrogen pressure within the defect, which is absolutely enormous. Now, since we have this Berger vector, we are able, to simulate the growth. And here it's a comparison between all these. These are size histograms, okay, of platelets, and how they evolve as a function of time, as a function for a given temperature. And you see a comparison between the simulation and the measurement, and to make it short, it works very well. So that means that the classical theory of Oswald ripening is able to simulate the platelet growth. What does that mean? That means that actually that's the system, how the system evolves from the top, instead of having round shape from the top, you see that's this shape, but that's a general evolution. What is very important is that the growth is driven by the interchanging of the vacancy and the hydrogen these defects are composed of, and they are the only source and sinks of hydrogen. So when you are entering the Oswald ripening regime, you can think that almost all the hydrogen is contained in the platelets, and only those which are traveling in the crystal to go from one to the other. This is marginal, okay? But they supersaturate the crystal around them. Okay, so that was moderate annealing. if you insist and you wait for longer time, or you anneal a slightly higher temperature, what you see that these platelet, they tend to disappear or tend to coalesce, or I don't know exactly, but they make cracks. That is, the size is changing. Now we are getting objects which are more in the micrometer regime, okay? And now you can detect them not only by TM, but also optically, because there are several micrometers in diameter. And so you can look them by optical interferometry, but you need, if you through silicon, for example, or if your top layer or your stiffener is just SiO2, which is transparent, you can make that by optical microscopy, okay? And you can see these micro cracks here. These are the micro cracks you see from the top, and they are located at the protecting range of the hydrogen member. Okay, and if you make some micro Raman on one of these micro cracks, you immediately see they are stuffed with a molecular hydrogen. Okay, now how do they evolve? Here you see a sequence where it's going during annealing. It's some sort of annealing. In situ annealing seen by infrared, and what you see is that you see the different micro cracks, and in general what you can evidence is that during the process you see that some of them they disappear. What is always very surprising, that is the capacity of silicon to heal from such defect, because getting rid of the vacancy atom hydrogen, it comes back to perfect crystal. Why some of them they grow? Okay, this is grow, and here you see some coalescence. Okay, true coalescence, but it's not migration coalescence, but there is some kind of interaction, and you see from 2 cracks you get only 1. Okay, if you make the analysis again of the size and the density evolution as a function of time, and also the volume which is occupied by these micro cracks, the big surprise also is again, this is also conservative ripening, okay? That is for a long time period. 100% here means fracture, okay? Means when you arrive at a time where your material is fractured. But from the beginning, it's totally conservative. At some point, very close to the end, what you see is that you diverge, okay? And something catastrophic is going on here. So surprisingly, microcrack also undergo conservative ripening, but there is something else in the end, mechanical coalescence, okay? Because probably few large microcracks behave differently. We'll see that. Look, this is one in situ optical microscopy. Also, you see this coalescence, propagation. Okay, so there was a debate, a discussion about why this coalescence, and so we made the analysis of many of. Basically we have tried to analyze the correspondence between the size of the cracks and the distance between them, and try to figure out if we could get a criterion for defining a fracture. And actually, it works. Let me see. We get this coalescence only for large microcracks, which are separated by less than 1 micrometer. Okay. So what we understand is that in the first step, the microcracks, they grow by Oswald ripening, that is pure diffusive phenomenon. Okay. This is okay. We know how to simulate that. But after some time, when some of these microcracks are large enough, fracture occurs, and this appears as a catastrophic coalescence. Okay, so the question is, okay, we had at the beginning we had large platelets, and after we have large microcracks, and so how do we go from one to the other? So the first idea was that maybe it's a normal destiny of a platelet to become a microcrack, but actually, if you look at the growth flow, it does not work. because we know the size and the density of the platelets. We know the size and the density of the cracks. We know the growth flows, and actually we can prove that the microcrack cannot be the result of the growth of a platelet, because there is a factor of about 1,000 in between, which does not work. And also we have a problem of the density, because when we go from one to the next, actually there's a 10,000 difference in density between the platelets and the macrocrack at the onset of the transformation. So we have to think of something different. It is not gentle transformation. And that's where in situ TM can be good, because by ex situ, what we are doing annealing. This is plan view TM, so we see the defect, we see the platelet from the top. You see the size is 200 nanometers, so these are about 10 tenths of nanometers. These are the platelets. Okay, what we see here is a strain field surrounding them, and when we increase the time, they tend to reduce in density, increase the size, and suddenly, after some time, we see these large objects here, which are the microcracks. And so, well, how do we go from here to here? Time for the movie. You can have an ice cream. Wish it works. Oh. Yes. So you have plenty of platelets and you have the microcracks. Look, these microcracks growing. You will see some appearing and nucleating here. Oh. They nucleate, they grow up. This guy is growing here. Okay, you see some of them, they grow. Okay, okay, let me go there. What the interesting thing is that when you look at the movie, you have plenty of platelets there, and most often when you see the formation of a microcrack, inside the microcrack or around inside up and down, you see that it's black. But it seems that all the platelets which were standing there, they have disappeared during the formation of the microcrack. Okay, you can have again, if you have not finished your ice cream. Look, this one is growing. There will be some nucleating here. Okay. Okay, some is growing. This one is growing also, and you see how black it is inside. And apart from one or two, but in general we see much less contrast due to the platelets. Okay, so the microcracks, they spontaneously nucleate in platelet-rich regions. They further grow, and so it's probably more collective interaction between dozens of platelets. Okay, it's not a normal evolution. So to make this clear, we made an analysis about the ratio of the distance and diameter as a function of depth to see whether we could find a criterion to explain where this coalescence, this nucleation of microcrack could take place. And actually, we can show that the microcracks, they appear when the ratio between the distance and diameter is about 1, which is good to know, makes sense, because the stress exerted by a platelet is by 1 over R. And so this agrees quite well with mechanical simulation. That is, when you have two platelets which are close to each other, or a population of platelets which are close to each other, basically what you have is you start to overlap the stress fields, and these stress fields, they sum up, and this is the collaboration or the cooperation between two neighboring platelets, which allows to open silicon in between and making a large one. And of course, if you have a dozen or 100 of those guys in a region, you have a spontaneous nucleation of a large microcrack. Okay, so we have seen that actually that's a complex phenomena because we start with point defects, we have precipitation phenomena, we make platelets which are precipitates, they evolve during annealing, that they fabricate nano cracks, then micro cracks, and eventually in the end it goes to fraction. Okay, so we have a scenario which is like this one, involving different type of physics, I would say. Again, on the beginning, what we do is that we have a soup, we have a mixture of interstitial vacancies and hydrogen. These guys, they make complexes together. To make it simple, in silicon interstitial, they go their own way, but hydrogen jumps on the vacancies. They make these complexes, and also they make some debonding of the silicon by passivating silicon bonds. And so the whole thing makes the platelet, taking the vacancies to make the room, hydrogen to make the molecule, some of hydrogen to make the passivation of the silicon. And see, these make your platelets. Once you have these defects, they grow by conservative Oswald ripening, like most precipitates in materials. And after some time, you have the collective interaction, mechanical interaction of platelets, and this allows the nucleation of microcracks. And by this process, you transform about 10 to the 3 or 10 to the 4 platelets into one microcrack. Okay. Following that microcrack, they start to go first also by Oswald ripening, but at some point, some large microcracks, they undergo coalescence, only a few % of the population, and this at some point initiate the overall coalescence, which we define like fracture. May I know how more I have, please, Chairman?
Yeah, Ashokan.
Yeah, you can continue. I think next talk also is there, no?
Yeah, can you just tell something?
5:30 you can go, I think.
Break we can.
So I have 5-10 minutes to finish with this one, right?
You can take your time. Then we can have a few minutes break. Yeah. Okay.
Thank you, the audience. Yeah. Thank you. Okay, so as I told you, that the difficulty is understanding the whole process and optimizing the process is that you have different fields together. On the beginning, you need to be good in atomistics. After, you need the thermodynamics. Then after, you need the help of some mechanics. Then after, you are again in thermodynamics and again mechanic. So that's really complicated. Phenomenon which require multi-scale simulation. And at the moment, it is not done. Okay, I think I will go to conclude this talk. I think that this hydrogen implantation, beyond the process of fabricating, allowing the fabrication of these SOI wafers, which are at the core of today and tomorrow silicon technology, I think as a material scientist, I insist that it's a beautiful example of precipitation phenomena in solids. Okay, like very often, I insist the word precipitation should actually be replaced by the word co-precipitation, as very often to precipitate, you need first to make room. That means that you need the collaboration of the vacancies. Okay, so it's a co-precipitation process. And after, it's a complex interplay between thermodynamics and mechanics. I would say that in terms of diffusion, we understand quite well what's going on. There is still much to do, especially about mechanical interaction, because for example, we are to simulate the collective interaction between the microcracks and the starting of the fraction. And so, and most importantly, we know so much about silicon and so little about all of the materials that okay, for your scientists, still there are plenty of things to study, there are plenty of things to model, and I thank you for your attention.
Yeah. Okay, so
I will be happy to answer to questions.
yeah, yeah. Any question from the participants? This in chat box, I don't see any question, but okay. So Ashuvan, so we can take some break.
Yeah, we can take maybe 10 minutes break.
10 minutes break. So we can start at
4:50.
4:50. Okay. So yeah. Yeah. Can I ask one question? Can I ask one question?
Sure, you're welcome.
Yeah. So actually, in industry, I mean, what is the temperature they use to do this debonding and?
Sorry, I didn't get the question.
Yeah, I just wanted to know, and actually in the industrial processing, what is the temperature that they use to do this delamination and whatever?
I mean, it can be between 350 and 500.
So,
okay.
Okay. So first they bond it with, okay. Yeah, please go ahead.
If you at low temperature, it takes time. I mean, it's very much like a precipitation, selectivity of precipitation. If you anneal at low temperature, it will take time, and the roughness of it will take time, but the roughness of your transfer layer will be small because you have an excellent localization of the platelets. Now, if you increase the temperature, it will go faster. But the surface will be rougher because basically will nucleate the depth distribution of your platelets and of your microcracks will be larger. So selectivity is provided also is helped by temperature. If you wait, thermodynamics is nice.
So in the to optimize the throughput of the company, and they must be optimized the time and temperature.
Absolutely, but you have to keep in mind that there is of course some finishing steps, some CMP, some oxidation. Everything depends on the thickness that you want in the end. Okay. I would say that they more or less transfer always the same thickness, but the fact that you will provide a wafer with 10 nanometer thick top layer or 20 nanometer or 100 nanometer thick layer will be made not by the transfer too much, but by the finishing steps.
And the last question from my side. What is the kind of accelerator this company will be having?
What is the kind of
implanter?
Okay, they are different. I mean, I'm not giving brands, you know.
No, just energy.
These I would say a classical 200 kV machines. Okay. Which are optimized to deliver high current beams of hydrogen. I would say that it's normal. I would say it's normal at the industrial level. It's a normal implanter, but the only thing is that everything is done to have high current beams because I mean the more time you spend at ion implanted, on the ion implantation, the more expensive will be your material. Ion implantation weights by about between 20 and 30% of the cost of the overall process.
And this, is this they do in 4-inch wafer and 6-inch wafer?
Yeah, it's a class. Today it's mostly 300 millimeter.
Okay. So the beam is scanned over the wafer.
Yeah, I mean both. Actually, the sample is on this new generation ion implantation machine. Both the beam and the wafer they
Okay, thank you very much. If there is no other question, so let us take a break for 5 or 10 minutes, and we'll come back at 4:50 here. Okay, thank you very much.
Tu m'entends, Marc?
Moi, je t'entends.
J'ai les problèmes de savoir ce que vous voyez pas. Tu vois mon écran là?
Attends, je vois ton écran, oui.
Et là, tu me vois changer de slide?
Oui, sans problème.
Bon, je vais rester comme ça parce que...
Oui, mais ça marche bien.
Bon, merci.
Ouais. Bon, écoute, j'espère que tu n'es pas trop mouillé.
Ouais, j'ai eu un coup de stress tout à l'heure. En plus, je me sentais comme un gamin morveux. Hein. Tu commences un truc.
Non, mais je vois très bien ce que tu veux dire. Oui. Non, tu parles. On n'y peut rien. Hein. La nature, elle est ce qu'elle est. Hein.
Non, mais bien sûr. Mais bon, Bah, tu prépares un truc au dernier moment. En plus, je n'en étais même pas rendu compte. C'est ma femme qui rentrait avec un papier en me disant.
Ah d'accord. Je sais pas, j'ai pas réussi à te contacter. Je sais pas qu'est-ce qui t'a contacté.
Non, j'ai pas été contacté. J'ai pas été contacté puisque je n'avais ni téléphone ni internet.
Ah, c'est ta femme qui m'a dit que tout était cassé, quoi.
Voilà, c'est ça. Elle est arrivée avec un petit papier en me disant.
D'accord.
Je sais pas ce que tu fais, mais il n'y a pas internet. Je regarde.
Bon, allez. Non, c'est intéressant.
Ouais. Okay.
Donc, comme je te dis, je vais pas aller jusqu'au bout parce que.
Non, mais bon, tu connais ce truc-là.
J'ai d'autres obligations. Dire que je connais, non. Soyons clairs. On est quand même limité dans toutes les connaissances que l'on a.
Oui.
Voilà. En tout cas, c'était intéressant. Ok, bah écoute, bonne chance pour la suite.
Oui, bien sûr. Et j'espère te voir bientôt, Marcel. Bon courage à toi.
Oui, j'ai compris, mais tu sais qu'à 77 ans, je commence à souffrir de conduire de longues routes.
Voilà, je sais. Écoute, je t'ai ouvert, j'ai fait une opportunité, maintenant on fait comme on peut, tu sais. Voilà.
J'ai vu. Et tu as compris que j'étais intéressé parce que j'étais dans le milieu quand j'étais jeune. Pour te dire, j'ai appris à écrire en écoutant le français dans le sud de la France, j'écrivais bien. Et puis quand je suis parti dans le nord, ils ne prononçaient rien. Que des fautes d'orthographe. Allez.
Okay. Excuse me. Yeah, it's already now 4:50 here, so we can start the next topic.
Okay.
Alan, you may please start.
Okay. So you see my screen again?
Yeah. Yes, we can see.
Okay. So it's me again, and this time I will talk about the evolution of defects in ion implantation, in ion implanted silicon. Evolution, it's thermal evolution. And as I talked a lot about vacancies in my first talk, I will focus mostly this time on interstitial defects. Okay, and I will try also to make a link with some of the questions that you can find in the nuclear material community. Okay, so I mean, why there was such a work on silicon interstitials in silicon is that the silicon community, one thing for the industry is that what drives microelectronic evolution is the possibility to simulate the process and to infer the characteristics of the devices that you will eventually fabricate. What I mean here is that we do not start by fabricating a device, but in principle, we start to explore using simulators. The first one is a process modeling simulation. It's the first step. Then from this process modeling simulation, you get the material and the doping and all that. Then you go into another simulator, which makes the device modeling, which is able to give you the characteristics of the device that you are planning to fabricate, and eventually you will go to fabricate these devices. So that's the reason for working on interstitial, but was in a more general framework covering, including the needs to get models to simulate all the processes, and this model they should be based on physics. Okay, so I mean, this whole story started more than 30 years ago when there were reports that okay, one very important point in silicon is to be able to predict, to fabricate and predict dopant extension or junctions, and so you are to be good at simulating the diffusion of dopants. And there were first reports at the end of the 80s that, for example, here you have SIMS profile of boron, and this you see the first one. This one is a boron profile after implantation, and actually because you want to activate these dopants, so you need to put some annealing there. And during this annealing, what you could see is that this tail, that is this diffusion of boron. Okay. So what is interesting about this diffusion is that, as you may see, the first thing is that at the equilibrium, under equilibrium condition for such an annealing at 800, we should see no diffusion. So the first thing is that we have an enhanced diffusion, it's very strong diffusion. And also what you can see is that how it evolves. It's very strong on the beginning, but it's not constant. It decays with time. So because you have a very strong shift after just 35 minutes, and after it's getting less and less. So it's enhanced and it's time dependent. Okay, so that's the reason why it received, and there is thousands of papers dealing with transient enhanced diffusion in silicon. Okay, so and it was established that there was has something to do with the presence of extended defects in the implanted region. So we need to talk about boron diffusion, because I took this example to only one to make you understand that the first thing is that what about diffusion in semiconductors? The first thing is that you have to forget about the simple application of the Fick's law, which tell you that in principle, I mean, in a liquid or in a metal or in a gas, I mean, everything is very simple, because the Fick's law tell you that if you have a region of high concentration and a region of low concentration, I mean, you have a gradient, and that you will have a flux of dopant going from this region to this region. But actually, this works in a number of materials, especially in gas, in liquids, or again in metals, for example, for interstitial species in metals. But by no way it does not work in silicon with dopants, because silicon, like many other semiconductors, is a covalent is a covalent material in which everything is detected by electrostatics. Okay, in general. So what is very important is the electric charges. And so to make it simple, I would say that actually the situation is very much the same, that you want to deal with boron diffusion, but actually, I mean, the boron atoms, they cannot move themselves. They need to wait for the bus, okay? And the bus is a silicon interstitial, are the silicon interstitials. What I mean there is that the diffusion of boron has nothing to do with the fact that we have plenty of guys waiting here and no one waiting on the left, but it has only to do with the frequency at which the buses, they pass by, okay? So in silicon, boron, like many dopants, they diffuses only by pairing with point defects, okay? And in the case of boron, it's only pairing with a mobile silicon interstitial atom, okay? So boron does not diffuse in silicon. I mean, it's a pair of boron and silicon which travel together until they separate, okay? So the important thing is that the diffusivity of boron in silicon is proportional to the concentration of silicon interstitial. That's the reason why it is so important to know the concentration of interstitials and vacancies in semiconductors when you are making any process. So at equilibrium, everything is simple, because in a real crystal, you do have interstitial and vacancies which are provided by thermodynamics. In other words, it's just the fact that you exchange enthalpy against entropy, and then as a result, any crystal at a given temperature is full of self-interstitial and vacancies. And so this is this equilibrium concentration of vacancies of interstitial which drive boron diffusion. But you have many processes. Ion implantation is one, oxidation is another one. It can be stress also. They will impact this concentration of interstitial, and by the way, they will impact the diffusivity of dopants. So if you want to simulate, that was the motivation of the silicon community is you want to be able to simulate the diffusion of boron of any dopant as a function of time, and for a given temperature, you need to be able to describe the way the value of the concentration of interstitial as a function of the depth, as a function of the time, and for a given temperature. So by what we mean, but what you need is to establish a relation between the concentration of point defects free to move and the evolution and the characteristic of the extended defects. So relation between free interstitials and clustered one. Okay, beyond silicon, there could be the message I'm trying to give here as something is probably also addressed to other people in metals or in nuclear material, for example. I was always stricken to see that in nuclear material, there is always debate about, okay, when you irradiate some of this material, you are getting uranium oxide or surrogates, for example, you start to see dislocation loops, and there is always a big debate and papers to discuss how this defect they nucleate. And the problem very often is that, okay, when you imagine a dislocation loop, you need to imagine some structure, and you need to introduce a Berger vector, so something which defines the extent of the deformation generated by your defect. And from this Berger vector, you get the formation energies of the defect. And clearly what you get, any that you try to reasonable Berger vector, but you try to put there in correspondence to the structure that you are trying, that give you formation energy which are too large at small sizes, so that actually the dislocation loops would be unstable. They could not nucleate. This is an example here where you have the formation energy of the defect as a function of the number of atoms they contain. So everything is fine when you have large defects, which these values are very reasonable. But when you get smaller and smaller, I mean, you have a huge increase of this binding energy, which is totally not realistic, and which comes from the fact that at some point you have a very strong contribution of the elastic energy to the overall energy of the defect, and that's okay if you can share this enormous amount of energy between many atoms. But if you want to assume the same structure with a very limited number of atoms, you see that it is not reasonable, because you cannot share such a large energy between such a small number of atoms. So there have been many tricks. Some people are trying to make tricks with the Berger vector, but I want to insist that the solution is not tricking, but just it reflects the fact that most probably, I mean, the dislocation loops do not nucleate by themselves, because the crystal can find alternative geometries better than the dislocation loops to cluster. So do not trust that nucleation loop nucleate. Okay, so that would be some goal of the talk, to answer to those questions for these people. Do the dislocation loop nucleate from point defect? What kind of defect of dislocation loop we have, faulted or prismatic? What are the growth mechanisms? Sometimes people they jump onto coalescence, and I will show that coalescence is not a mechanism for that. And what is the problem also with the formation energy? Because in silicon, actually, we had the same questions in the past, mostly from '95, and I think that we got the answer 10 years ago, that is now more than 10 years ago. So I will make a short review on the work performed and main findings. Okay, so first thing is how to create a supersaturation, how to generate silicon interstitial in silicon if you want to make an experiment. If you want to make any supersaturation of interstitial in any material, you can follow the same rule. The first thing is a dopant implantation. Why is that? Because, I mean, when you put your dopant, okay, they are depth distributed, but you need some thermal annealing, and the goal of this thermal annealing is to have this boron, which is most probably is an interstitial site, to allow him to jump onto a substitutional site. But by doing that, it makes a kickoff, and it just generated a symmetrical interstitial. Just so when you activate dopant, you generate silicon interstitial supersaturation. You can also make it directly, because if you are in silicon, you make silicon implant into silicon. That's a very clean experiment, and you are sure that you have excess silicon into your silicon matrix. problem is that you are restricted to low doses, because if you insist with the dose, at some point you will get an amorphous layer. Okay, and so all will be lost there because you will have a relaxation. So this works, but only for small enough doses, so that you are not amorphizing the layer. You have another possibility, is that you can take advantage of some knowledge about the nuclear stopping and the formation of Frankel pairs. You are at that school. I guess that you heard a lot about this. For the purpose I'm following, what I want to stress is that when you make, okay, you have a nuclear collision, you make a vacancy and you make an interstitial, that is common sense, but of course the vacancy stays where it is, while the interstitial propagates, and in general it propagates mostly in the direction of the incident ion. So in the end, you are left with some kind of spatial imbalance, okay, between interstitial and vacancies, because what I will show there, if you make any implantation or irradiation, we'll see above or not later, but here is a germanium implant, for example. I mean, you have your damage. So if you make some stream or Monte Carlo simulation, if you ask it to draw the vacancy profile, you will have that. If you ask to have the interstitial profile, you will have almost the same profile. But actually, if you trust in physics and you trust in making a difference, you make the difference between interstitial and vacancy, and you are left with this curve, which shows you that true that they are very similar, but actually that they are also different, in the sense that I would say that in the first part, okay, of the layer, it's a vacancy rich, while in the deep part is mostly interstitial rich. Okay, and this you access to that, because in general, if you do that, the material gets amorphized, and so you are left here. The vacancy rich region disappear because it relaxes into the amorphous state, but you have this region here. This is the interface, this is a crystal, and you have a region left where you have silicon excess interstitials. And you can measure them because you can measure the strain they create, okay? So you can fabricate excess interstitial concentration above 1% in this region, which is kind of high concentration. And also at a decent surface from a recombining surface, because if you would be creating them very close to the surface, they would probably disappear. So I'm doing that, these guys, I'm having this interstitial, but somewhere here. Now, again, okay, you know that Monte Carlo simulations are very nice, but they work at 0 degree Kelvin. So in real life, you have sun temperature in your room. It is so-called room temperature. So in silicon, I'm making vacancies and interstitial during an implant, but they do not survive as such. It is well known since 40 years that they recombine. The main thing is that most of them, they annihilate because they are not so far from each other and the silicon interstitial can diffuse. But in the end, when everything is finished, you are left with two types of defect, mostly devacancies and the devacancies, and the interstitials. Of course, they can be charged depending on the doping of your substrate. So, I mean, from E to V, you go to I2 and V2. And so in any irradiated silicon crystal, you don't have interstitial and vacancies, you have de-interstitials and devacancies. Okay. Actually, if you want an image on that, I mean, you should not believe that you have interstitial which are as rigid or as nicely identified as in this picture, but instead, again, this is covalent material, all the binding, all the bonds are very strong, and so you have a rearrangement of all the thing, and instead of these 6-member rings, you have 5 alternating 5 and 7-member rings, and if you count all the atoms there, you will find the interstitial, but it is not as obvious that it is here. Okay, now, if you anneal this layer, okay, I have an amorphous layer, so I suspect that I have some interstitial rich things, the region here. I make some annealing, and so as the annealing proceeds as a function of time, you see here is something like 450 degrees, and you see that, I mean, the amorphous layer reduces. So what you see is that the solid phase epitaxial regrowth of the crystalline layer up to the end where everything is crystalline. You see that's perfectly crystalline, but you see a band of defect, which is just below where the interface between amorphous and crystal was previously. And now if you look at these defects from the top, that is in plan view, because in cross-section you see just a band there, it does not tell you so much, but you look at in plan view. Now, depending on the temperature, you may have many different defects. Actually, to make here, you have differences in temperature, differences in annealing time, and you see that for low temperature and or short times, you have very small defect, while at high temperature for a long time, you have a large defect, and you see that are not all the same. So we have many different defects. In general, these defects are named in literature end of range defect. End of range because they appear there by the end of the range of the implant. Okay. So end of range defect, contrarily what you can read somehow in the literature, they can be found only after a layer has been amorphized. Okay, so this defect actually, if you look at them carefully, if you increase the thermal budget, they have different size, they have different shape, they are different type actually. They start to be very small, very tricky, almost impossible to visualize with a TEM. But when you anneal a bit further, you get elongated defect, kind of one-dimensional defect, rod-like defect. Here you see that you have another class of rod-like defect, and this one seems they are transforming into dislocation loops. Here you may have dislocation loops such as like that. This one perfect, and this one is a frank. So we have different objects. Basically, we have clusters, 0 dimension. We may have rod-like, that is one-dimensional defects of 2 types, and we have also dislocation loops of 2 types. So all these defects, they are just precipitates of silicon interstitial. There are different ways of clustering silicon interstitials, and we'll go together to understand why the crystal is doing such funny things. So what about the defect characteristics? Okay, we start with the rod-like defects. Okay, actually, you see them here. But these are the imaging conditions used to get them. I mean, these are very tricky imaging conditions. I will tell you later why this is used, because we see all the defects here. Okay. Actually, they are lying on the 113 planes. Why they are named 113 defect, and they are elongated in every 110 direction. Okay. So crystallography again tells you that you have 12 variants of the defect. Very often when you make images, you see only one part of them, not them all, okay? They have a constant width, okay? And they must be seen as a one-dimensional precipitate of silicon atoms. But actually it's a very loose structure. You see, these are the row, this is a row of the interstitial here. You have another row of the interstitial in this 110 direction. And so it's like a bundle of silicon interstitial chains, you know, but it's very lousy. And so we know that every nanometer in length, we have 24 atoms. Okay, these defects were well known in the 70s. Okay, these are the 113 defects. As electron microscope, again, you see them this time in the cross section. So you see this is a 113 plane, and you can analyze the strain which is around surrounding the defect. From the strain analysis, you can deduce the Berger vector. in crystallography, we like very much this Berger vector, not only because it tells us how to image the defect through some invisibility criterion, but also because basically you have to keep in mind that this Berger vector, which is a kind of virtual vector, is actually a quantum of deformation. It defines the strain amplitude. Okay, and in other words, also it's a large part. It is in the formula which helps you calculating the formation energy of the defect, because the formation energy of defect is, I would say, mostly due to the elastic energy, how the crystal deforms the crystal surrounding it, and also some kind of interfacial energy. But elastic energy is always very strong. So I think this B is important also because it allows you to calculate the binding energy or the formation energy of the defect. So that was my message here. When you have defect, please never trust one TEM image, because I show you this image which show all the defect. And again, it was a very complicated condition. This is a beam direction. This is the diffracted beam which is excited. And it's only in this condition that I'm getting all the 12 variants of the defect. If not, if I take just common imaging condition, these are the size histogram of the different variants, okay? And of course, they do not behave the same. I will not detail that, but I mean, if you make the analysis on image in which you have this defect, you understand that this will be very different. Your conclusion will be very different from that you might have, what you may have concluded from investigating these defects, okay? So please, when you deal with defect, you never trust one TEM image. Thank you. Okay, now about dislocation loops. Okay, we have dislocation loops. You see here, you have, it's again on plan views, you see them on the top. To make it short, you see them, some of them are elongated, some of them are more elliptic. Actually, they are circular, but they are bent. And so we can identify, it's our job, we know how to identify them. There are two types, faulted and perfect dislocation loops, 12 of the variant of the perfect, 4 variant of the faulted. That makes 16 different type of defects there. Again, imaging conditions are crucial for quantitative analysis. And the good thing is that if you make what I did when I was younger, to make us an image of one of these defects, you make some Fourier transform filtering of this image, and you can image the extra plane here of this interstitial defect. So this is seen in cross-section. So it is, the defect is like a plate. Again, it's a plate, it's round shape, like here, and it's a plate of excess interstitial atom. So this also is a precipitate of silicon interstitial. So now we have plenty of defects. We would like to understand how they grow and eventually how they transform from one to each other. Okay, so for the growth, the easiest work was done on dislocation loops. So again, you form dislocation loops and you look at how they evolve during for different annealing time and for different temperature. And what you see is that, as I've shown with hydrogen, you get the same behavior. That is, you have the size during annealing, the size of the defect decreases while the density increases. And defect density decreases, the defect size increases. And but actually, what is very interesting is that if you make the product of the square of the size by the density, that is somehow the volume which is occupied by the defect, or in other words, the total number of silicon interstitial which are clustered in the defect per surface unit, it remains constant, okay? So again, it's conservative oswald ripening. And I will not redo the same thing that last time. Now you are clever. I told you that already. We have small defects with a large supersaturation. So this is, for example, a small dislocation loop. In equilibrium during annealing, you have a supersaturation of self-interstitial silicon atoms. So you have to imagine that you have a vapor of silicon free atoms in the crystal surrounding the defect, and around the large defect you have the same thing, a vapor, but I mean the concentration is much less. So you have a net flux of interstitial from not really from the small to the large, but from the small to the mean field, and from the mean field to the large. And so very small defect, they dissolve. The large defect, they tend to grow, and that everything is driven by the supersaturation by the Gibbs-Thomson equation. And of course, you may have a surface, and if you make this representation of the surface here, you understand that the surface is somehow like a large defect. And the supersaturation, which is in equilibrium with the surface here, is actually the equilibrium concentration. It's a pure definition of the solid solubility limit, actually. So everything is driven, the growth is driven by the dynamical equilibrium between the precipitate population and the supersaturation in field. Again, like in every precipitation system. Okay, now I see you saying, oh, this man is selling Oswald ripening too much today. Should I believe him or not? Okay, I want to convince. Is it really Oswald ripening? Here I show you an experiment in which basically it's the same implant, the same energy, everything is the same. It was germanium, which is very pure, very beautiful. And the only thing, the same annealing condition, same time, and the only thing that was changed is the dose. And it's interestingly, one might think that if you increase the dose, you would increase the density of the defect. And actually, this is not true at all. And this is what I'm showing here. And this is a beautiful prediction of the Oswald ripening, that is the size of the precipitates within a population which is undergoing Oswald ripening does not depend on the initial supersaturation. Okay, it's the so-called invariance of the defect size. So this is kind of counterintuitive, but it's definitely a proof that it's really Oswald ripening. It's that, I mean, there is a size invariance of the defect size as a function of the dose. The dose only affect the density. If I have twice the dose, I have twice the density, but the size is unchanged. And actually, if you look at the diffusion of boron, okay, again, these are all this boron diffusion here are for all the sample having the same size of the dislocation, and while they don't have the same density. Again, you might think, okay, I have many more defects here than here, so I will have much more diffusion. This is not true. Actually, the diffusivity depends on the size, but not on the density. And so, actually, of course, it changes with the thermal budget, annealing time and annealing temperature. Okay, so as a function on time, it increases, but it is not a function of the dose. So this is really Oswald ripening. So what I'm demonstrating here is that all the defects which are seen in ion implanted silicon, they are precipitate of silicon interstitials, and they undergo Oswald ripening during annealing. Now, we would like to understand from where they come, all of these defects. And the first thing is that how do we get this 113 defect? Okay, the problem is that before the 113 defect, we don't see the defects, so we cannot use TN for that. So it was the idea of Nick Cowan, which is a very clever guy, who say, okay, if we will make the other way. If we can't see the defect, we will measure the diffusivity enhancement, how they impact the diffusion of boron, and from there we will deduce the formation energy of the defect. Okay, so the experiment is like that. You have a boron, you have a silicon material there, you have a boron delta layer, then you make some silicon implant, a low dose implant. So you say, okay, I'm going to make small defect here, and during annealing, what I will do is that I will help to grow these defects, and I will look at what is going on here to see whether I can learn something about the emission of the interstitial from this region. during they change in class, so they try to increase in size, for example. Okay. And okay, so that's how it works. So in principle, we have a supersaturation. We have a mean field here, and the mean field is the supersaturation of the interstitial in equilibrium with the population of defects. And this boron marker will be used to detect this as the diffusivity of this boron will be proportional to this supersaturation. And this is what we did. And actually, you get that. But this is for different temperature. We extract the supersaturation. That means by how much diffusivity has been enhanced. You see, it is not by 2 or 3. We are dealing with factor of 10 to the 6, 10 to the 7, or whatever. And in general, what you see, it's time dependent. What is very good news, because it shows that we are catching the size evolution of the defect, and it shows plateaus. So probably we have 2 different things. Okay. So what we did is that we took this result, we made some model. I will detail a bit later on this non-conservative Oswald ripening, that is Oswald ripening, but taking into account that we have a surface close to it, and we can deduce, and we could deduce the formation energy of the defects. And so we have you have here a sketch, a graph showing the formation energy of the defect as a function of size. This result is very well known. The paper has been cited more than 500 times because, I mean, it shows that the clusters of silicon interstitial, they have magic sizes, and this is very nice. What does that mean, magic size? Is that actually this is the formation energy of the I2, that is the D interstitial. And when you try to grow this D interstitial, I mean, the system doesn't like too much the 3 interstitial, but it likes very much the I4. And we have a very stable I4, which is even more stable than the I2. And again, I5, I6, I8, it does not like that much, but I8 is a very strong one, okay? And so we have at least 2 sizes of cluster, which are extremely stable, okay? Usually this is observed in nature. This corresponds for a precipitate. Would it be a large precipitate? It would correspond, for example, to the fact that the precipitate is fully faceted or not. One may understand that if you have a faceted precipitate, it costs you less energy if you incorporate one atom to finish a facet than to start a new one. That's more or less the same concept. Here, although that it's not, we cannot talk about facet, but it is not so surprising that there are numbers which are magic numbers for which, I mean, the material is more comfortable with incorporating special sizes of clusters. So that's the point with the silicon, that is with an I4 and I8, which are very, very stable, and which may be taken as the building blocks for the 1-on-3 defect. That is, if you take if you give me like a Lego, if you give me I4 and I8, I'm able to fabricate the 1-1-3 defect. Actually, the thing is that what is the point with the surface? Actually, when defects are close to the surface, what you may see is that you may see during experiment that the number of defects, they decrease. The number, not of defect, number of interstitial in the defect decreases, while actually the size still increase for a long time, but after start to decrease, and the density decrease also. And sometimes in literature, it has been said, it has been claimed, and there are even papers which I cited hundreds of times, which say, for example, this defect has a dissolution rate of this amount. And this is a very, very wrong statement, because, I mean, the dissolution is not an intrinsic character of defect. Defects are not born to dissolve. They can eventually dissolve if you provide them with a good sink close by them. So the dissolution actually here is not a characteristic of the defect, but is just due to the presence or to the proximity of the surface. It can be still described by Oswald ripening, but within a non-conservative growth description. Okay, so we had this 113. Okay, I'm glad they go 111. Okay, we have evidence that, so at some point, this defect which stands on the 113 planes, they prefer to go on 111 plane. Okay, we can calculate the formation energy, we can demonstrate that this is favorable. And the interesting point is that immediately after they go on the 111, they are still rod-like, elongated. But as soon as they see the 111 plane, somehow they transform into two-dimensional object, because this 111 planes is so symmetric that basically is so symmetric that the defect, the interstitial, they tend to wet on this plane, and from the rod-like they generate a dislocation, which is a two-dimensional object, as it is seen in this image. You see that at the edge of this rod-like defect, you start fabricating a dislocation loop. Okay, so the mechanism is that they go from 113 rod-like to 111 rod-like, and from 111 rod-like, they go two-dimension. Now, why the people, they say, sometime in literature, this is also the case well beyond silicon, is that, oh, this generates faulted dislocation, and the other one makes, oh, I'm getting perfect dislocation loops. Actually, both, in most materials, both exist. They have a very different structure, while they both show an extra plane of interstitial defect. Okay, so for example, here is a P is for prismatic. That's a perfect dislocation loop, and the round shape again are the faulted loop. But so there are many reports in the literature, not only in silicon, that people saying that, oh, with this temperature, I'm getting this defect, with this surface, I'm getting this over defect, or when I'm changing the dose, I'm changing the defect. Actually, if you are serious, you calculate the formation energy of these dislocation loops, and this is the result here, at least for silicon, and I expect the same type of thing to occur in every material, is that actually, okay, in dot line here is the faulted loop. Okay. What you see here is the size of the number of atoms which are contained in the dislocation loop. And okay, for a perfect dislocation loop, it goes straight, like that, at least on the logarithmic scale. And while for the faulted loop, it goes this way. Why it goes this way is there. For infinite size, you have here, a limit, which is given by the fault energy. So there is an asymptote here somewhere. And while for the perfect loop, the asymptote, the limit is 0, so it goes straight there. But what you see here is that at small sizes, the perfect dislocation loop are less stable than the faulty dislocation loops, while this is changed and this reversed when you go to large size. For large size, it's just the contrary, that is the perfect loops that are more stable than the faulty loop. So what I'm trying to show here is that, of course, the proportion depends on temperature, time, oxidation, surface proximity, whatever those, because what you have to deal with is that you have to deal with the Oswald ripening of two types of defects which are competing. Okay, so the funny thing is that at the beginning of Oswald ripening, for example, you may have a large perfect loop which is a source for a faulted defect, while it will be the contrary after they have increased in size. So it is not very direct, but you can understand everything because everything is related to the formation energy of the defect. Okay. Talking about formation energy of the defect in general. So what I have discussed with you is the fact that what we have defect here, it's an energy configuration. The diagram, you may think that when you have an intersection in a small defect, you are somewhere here, okay? And now when you are doing thermal annealing, you have the choice. You can go, binding, you go up to the migration point, then you migrate, and you can fall down, you fall in a larger defect. That is why you are getting deeper, or eventually you can go to the surface, which is a very, very, very deep defect, actually. Now, energetically, we are using many, many different terms like formation energy, binding energy, this and that. A simple representation of all that is, in silicon, is that this is the background energy. This is a zero energy, zero. That is, I would represent by my crystal, perfect crystal. When we talk about self-diffusion, okay, we are talking about the ability of the crystal to produce an interstitial and to have it migrating. So you pay for the binding energy, okay, how much I pay to have an excess, to have an extra interstitial, then after some migration energy. And this is defined as the self-diffusion energy based on interstitial, okay, or the interstitial component of self-diffusion energy. But when you have a defect, so you have somehow, you have somehow some gap here, which is kind of binding energy in the crystal. But when you have a defect, what you tend to occupy this gap. And of course, this is the size of the defect here. Of course, in a perfect crystal, the size has no impact. In the defect, it has an impact. And so the formation energy is as an energy shift you measure between the background and your defect energy, while the binding energy is a complementary, is a cost you have to pay to free an interstitial from the defect before it can go to diffuse. Okay. So this formation energy are always very important. It can tell you which defect, if a defect here is less stable than a defect here, it explains to you that the defect of large size is stable, more stable than the defect of small size. And so in general, the formation energy is easy to get. It's a cost of adding one atom to the defect. That is practically what you do is that you calculate the total energy of the defect and you make the derivative because it will be the cost. And in economics, the same thing exists. They call it the marginal cost. See, having fabricated 1,000 objects, what is the cost of the 1,000 plus 1? That's the same. So I insist on that because the same concept, Oswald ripening, binding energy, formation energy, they apply for all precipitate and solute systems. Okay, now see if we put everything together about the interstitial defect in silicon, we understand that, we put that everything on the graph. Here you have a number of atoms in the system, in the precipitate. We start at 2 because at room temperature is 2, okay? 2 here. And we see how it evolves as a function of the size, okay? So what we know is that we have a continuous Oswald ripening and transfer of interstitial from energetically more to energetically more favorable space. So in general, during annealing, what you do is that you transfer, you go this way, okay? So on the beginning, what you have, you fabricate, you cluster small clusters. You cannot see them by TM, but you can identify them by through diffusive experiment. So you have magic size that has been demonstrated, 4, 8, and then after you make this 113 defect. And there is an asymptotical limit here, which is given by the fault energy of the defect. But here, in this region, you see these are the formation energy of the dislocation loops. And you understand that starting from about 1,000 atoms is preferable for the system. Oh, I'm sorry. This was the 102 defects. So the 102 defect, they evolve there. But at some point, they may transform, as I've shown to you, they may transform in faulted dislocation loops, which are more stable, or at some point also in perfect dislocation loops, which for larger size are more stable. Okay. So this graph is very well known now. It tells you what is the range of sizes where a defect is stable. That means that you know that you can have cluster only for this size, or 113, they can accommodate only this size, range of sizes, and dislocation loop are there. But also, it tells you you can transform the formation energies into the supersaturation of free interstitial atoms. So it tells you that at some given temperature, you can change the temperature, again, through through the Gibbs-Thompson equation, you can say, okay, I have a dislocation loop of this size, it contains this amount of atom, so I can deduce that in my system I have a supersaturation of interstitial of, say, 200. That means that the concentration of silicon interstitial is 200 times the equilibrium value just because I have dislocation loops of this size in my system. Okay. And this is what is put into all this simulator. Basically, the graph is put into this simulator. Sherman, how long do I have before coming to some end?
Yeah. Ashokan?
Yeah, you can take.
Yeah, and 10 minutes. Yeah, 1 hour.
10 minutes. Okay,
Yeah.
perfect. So the whole picture is like this one, as I told you, that you have an exchange of defects of interstitial between the defect, and the surface can play a role. Actually, the surface is doing like that. It is what we take when we make the simulation of the diffusion, where you have a region where you have defects. So you have a supersaturation value here. You have a surface here, and the surface is the characteristic of the surface is its capability to recombine silicon interstitial, that is to incorporate this interstitial on the surface at atomic steps or at voids or whatever. And this, of course, this requires some time, okay? And this time you can transform into some length, because the idea is that once the interstitial has gone into the surface, it needs some time. It has to travel over some distance before finding a suitable site to annihilate. Okay. So, and this is a picture that we have. So this imposes the surface, the characteristic of the surface, that is atmosphere, roughness, this and that, is defined by a diffusion length. Okay, so it should be 0 here, and so it's the supersaturation midfield in the defect region, and in between you have a straight line because the system is not viscous. Diffusion goes fast, so you have a line, and so you see that the diffusivity is different. The supersaturation is different at each depth, so the diffusion of dopant will be different at each depth. So diffusivity is time and space dependent. Now, are we able to simulate this growth? I will not enter into detail, just the idea. It is kind of atomistic simulation. The idea is that you have a clusters, you have a precipitate, it has a possibility to emit or to capture. These are probabilities. You know, they capture the emission probability is proportional to the exponential of the formation energy, and through some geometrical factor. The capture also has something to do what is around the defect, that is a supersaturation, it is around the defect, because capture means I take atoms from the matrix, and so I can write down the growth flows, which is of course the change of size of the cluster is the difference between the emission and capture, okay, which I can calculate also there, but which has to be also equal to actually the transport, which is through the diffusivity and due to the concentration gradient between one single defect and the matrix. So we can do that. We need to have capture cross-section, okay? When cluster, you take something which is kind of spherical. When you have defects in general, you ask yourself, oh, let me think of this defect, from where could it capture the extra atoms? In principle, you conclude that it is the tensile region of the defect are more suitable to capture. So you put something which is the same dimension that the capture of the defect, that is circular dislocation line for a dislocation loop, or these lines along a rod-like defect. And in the end, you make a simulation with all input parameters. Energy, so the depth, those, it will give you the numbers. Temperature, this is for as well ripening. And the machinery is provided by the energetics, that is the graph which I've shown here to you. This is a machine which is feeding the system, and also some capture efficiency. And in the end, you are left with the evolution of the density, of the size, and of the supersaturation. And this supersaturation will be the one that will be coupling with the dopant diffusion. Okay, just to show you, I will not make publicity, but I mean, most famous experiment in this field are so-called Eagle-Shannon experiment. They describe as a function of time the growth and dissolution of this defect, and you see that the simulation in blue, they reproduce very well the experimental point. Okay, with this simulator, you can also reproduce the size of the evolution of the dislocation loops that you are observing for a variety of conditions. And you can also reproduce the Covern experiment, that is the diffusion on the Markov layer. That is when you don't see the defect, but you can infer that they are playing a role in the diffusivity. That is the case here, where these are experimental part and again the simulation. And okay, it was not a trick, but it's just to show you that if we want to reproduce all this diffusivity behaviors, it is not because we liked perfect science, but we do need to introduce two types of defect, and the magic size clusters were absolutely mandatory to describe the diffusion, because basically this stability of small size clusters somehow keeps the system for a certain amount of time before allowing going into extended defect. So it's kind of time decay, a time shift, which is thermally activated actually, and which you cannot reproduce without putting stable, small stable clusters. Okay, so now for the diffusion of boron itself, just to show you how the simulator works, basically you have your dopant somewhere, and you input this machinery, which I've shown to you. Yeah, this is a boron, for example, and then on the beginning, you know that you have clusters, for example, so a huge supersaturation in this gradient. So you treat the system, and you give the diffusivity at each depth. You give the diffusivity proportional to the supersaturation. So it's very large here, but it's smaller here, and smaller and smaller when you go close to the surface because of the decrease. So, and during time, it goes like that. So you make 113 decrease, and this is a supersaturation, decrease. And in the end, you are able to simulate all the dopant diffusion. Almost industry, but the good thing is that this science was not lost, because now it's used by the industry. I took only two examples. Chartered Semiconductor, which described this defect evolution using a KMC simulation. And you see, for example, here they talk about FD-SOI transistor, very small transistor, and they simulate the formation of the defect and of the diffusion of the dopant in the region. And for example, they were able to predict the difference by using bulk silicon here, or SOI silicon that is only with the SiO2 here. And you see the beauty of the SiO2. For example, after some annealing in bulk, I have defects, while after annealing with SiO2, I do not have defect. And this is because some of the dissolution of the defect takes place at the interface between silicon and silicon oxide, like I've shown here. You have the surface, but you have also the interface. And actually, this totally fit with the TEM observation that you can do. Second approach is so these chartered people, for example, they do that. They are able to get the dopant mapping, and from the dopant mapping, they do the transistor characteristics. But funny thing is that these transistor characteristics were obtained by taking into account the magic size of the small clusters. You have to appreciate. By ST also, it's the same thing, but analytical solution, or by FEM, they do more or less the same, some dopant mapping, and in the end, they are able to get the transistor characteristics and also evidence the change between the advantage of having SOI, for example, in this example. So to conclude as a summary, I've tried to show to you first, I mean, you have to be, to understand that dislocation loop in silicon, I mean, the result for the presence of free interstitials generated by irradiation, by ion implantation. From room temperature, where you have I2, you go to I4, I8, you make rod-like defects, then after you make perfect or faulty dislocation loops. You make many very different defects, but they are all the same type, not type of defect, but the same type of object. They are precipitates of silicon atoms. The mechanism which allows to go from one to the other is the Oswald ripening, but it's interchange of silicon interstitial. It is diffusion. They evolve through diffusion. The driving force for the system is, if you look at frozen interstitial, is that the system prefer to generate defects which have the smallest possible formation energy. Okay. And this is obtained through the size increase or through the change of type. But if you look at free interstitial, the driving force is just the fact that the system try to minimize, to reduce this supersaturation and go back to equilibrium. Okay. So the key concept I've shown to you is the analogy with a droplet vapor. You have always to think that the precipitate in the system is like a droplet in your bathroom, and everything is driven by the Gibbs-Thompson equation. So we can model that. And now if I'm going back to people maybe like you, working on uranium oxide in metals, on surrogates, on nuclear materials, when the question comes to do dislocation loop nucleate, my answer is no. What? No, they don't nucleate. Basically, you think that they nucleate because at some point you are able to see them in the TM. But what is important is that what you are not able to see in the TM, what is before. And in general, you cannot nucleate because formation energy is too strong. So is it frank or faulty or prismatic loops? In principle, in very generally, you have both, but depending on condition, you will see mostly one type or the other. What the growth mechanism, in general, there is, please stop talking coalescence. Everything is about diffusion. And what is the problem with the formation energy is that in formation energy, you cannot arrange the dislocation loops with a Burger vector to accommodate a small number of photons. So you have to imagine that you have a different configuration able to store single defects in the material. In silicon, everything happens at the temperature higher than 800. So you may think, oh, in my metal at room temperature or in my uranium oxide, I'm okay. No, you are not okay, because everything is not, it's not a question of temperature. It's a question of temperature, of diffusivity. And in many of nuclear material, the interstitial diffusivity are very large, including at room temperature. So everything may appear even during ion implantation. And also you have much smaller binding energy. That means that the system is, it's easier for the system to evolve through thermal energy. Okay, so the message I wanted to talk about is that in principle, when you talk about defects appearing after some irradiation, you have to keep in mind that in principle, the defect, they never nucleate. It's just the limit is just the instrument that you are using to evidence them. And so I encourage you to look at what is before what you can see, because at least in silicon and most semiconductor, what we have shown is that they never nucleate, they just evolve from the D-interstitial to the large dislocation loops containing 100,000 of atoms. It's only one mechanism, it's only the Oswald ripening, it's only the interchange of free spaces. Okay. And I have to acknowledge all the young people, because there was many PhD theses done to solve the case, and also many funding from the European Commission, which I want to acknowledge. Thank you very much.
Thank you very much, Alain, for excellent presentation. And at least I have learned so much from you. So for the participants, please ask questions.
Actually, I have a question, a written question by Taranga. I think it's pertinent. Sir, which type of defect can be determined from the FTR spectrum of irradiated films. That's a good one. Taranga, I'm not an expert at all on optical spectroscopy. There are modes, I think there are experts around you. There are modes which can be excited by infrared. There are modes which can preferably be excited by Raman modes. Some of them were excited by both. Some are excited by exclusively one type. I would say by putting together the two techniques, you are able to, at least in silicon, you are able to identify most, maybe all of the possible complexes that you can find, that you can generate between, by associating vacancies, hydrogen, and interstitial and hydrogen. I have another one. Explain how we can calculate energy from stacking fault. Okay. Again, as I told you, formation energy is just the marginal cost. That is, you have to calculate the total energy of the defect. So in principle, if you have a you have to add a different contribution. You put everything together. But if you have a dislocation line around, you put a dislocation line. If you have the stacking fault, you put the stacking fault energy, which is given by square meters, and you reduce it to the size of your defect. And so you put everything together, and you are in principle able to calculate the total energy of your defect. Once you have that, the total energy is for a given number of atoms. So you make the derivative of it. Okay, because what you want to know is how much it costs to add one. Jan Esvar, is that clear?
Yeah. Yeah, you can type in the, do you have any? Yes. Yeah, he is satisfied with the answer. Is there anyone else? Okay. If not, Ashokan, can we, yeah, anyone else want to ask question? Ashokan?
Yeah, I think no other question. You can thank him and we'll close the session.
Yeah, okay. Thank you very much, Alan, for this beautiful talk. And yeah, for my side, it was my, when I started working here, I wanted to do my research on diffusion and radiation enhanced diffusion. But anyway, this thing didn't work. But this is actually what I thought that I would be working. So for me, it is a wonderful, wonderful experience. And hope we'll in contact and learn more from you. And hope you can visit IUAC once and give us more of your knowledge, share with us. Thank you very much.
Yeah, it was it was my pleasure. And frankly, I really apologize for the mess I put losing the connection, and I hope that you will have good time. And all the young people, I'm eager to meet you sometime in India as soon as we get rid of this virus. I hope to be back on the route or the roads of India again. So bye and thank you.
Bye. Thank you.
It was nice. It was nice talk. Yes.
Bye.
Bye.
Okay, thank you very much, Ashokan, for giving me this opportunity to chair this session. And I think it was a nice session. We learned a lot from the speakers.
It's your area. That's the reason I thought I should put you.
Yeah. It is my, hardcore interest in research on this thing. Thank you very much.
Okay, thank
So,
you all.
shall we
Tomorrow,
quit?
9:20. 9:20 we'll meet again. They can sign in. 9:30 session will start tomorrow.
Okay, bye-bye.
Yeah, bye, bye.
Okay, Kaviraj, thanks.